Welcome to the ISRQI Circuit. So this is a series of 6 local conferences that will take place in Waterloo, Nottingham, Vienna, Stockholm, Bremen, and Sydney. I'm Rick Perche, I'm the ISRQI Outreach Officer, and we kick off the circuit with the Waterloo Conference, which was organized by José Polo-Gómez, Caroline Lima, María Rosa Preciado-Rivas, and Everett Patterson. So this series of local conferences, our goal with this is to showcase the research that is being done in each one of these places so that everyone can see what's happening, and also the career opportunities that happen in this place, the postdoc opportunities, the PhD opportunities, and everything, right? So everyone here will present their research. Thank you all for coming as well, for being a part of this. And I will give it to Everett right now, who will say some words about the conference, and hopefully everything will go well.
Wonderful. Thank you so much, Rick. Let me get myself mic'd up and pull out my remarks. So thank you so much, Rick, for taking this upon yourself to help organize this international circuit for relativistic quantum information. Thank you to all of you who are here with us in person and also virtually. We're fortunate to be hosted here at the IQC. We were so fortunate to have the Department of Applied Math sponsor this event. So for those of you who are joining us live, joining us in person, we have refreshments and food and snacks, and we'll have a lunch, all of which is funded by this Department of Applied Math. Before further comments, I would like to read the University of Waterloo's territorial land acknowledgement. So the University of Waterloo acknowledges that much of our work takes place on the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. Our main campus is situated on the Haldimand Tract, the land granted to the Six Nations that includes 6 miles on each side of the Grand River. Our active work toward reconciliation takes place across our campuses through research, learning, teaching, and community building, and is coordinated within the Office of Indigenous Relations. So for some specifics about today's iteration of the conference, I'd like to note, so we'll have food in the back of the room. We're going to have 2 breaks, one in the morning, one in the afternoon, and then also a lunch break. So we're going to have 4 blocks of talks before and after each one of these breaks. I'd like to note that there are washrooms in the building. If you walk around the stairs that you're on, there's a door underneath there. If you just go through, there's 2 sets of doors. And then you take a left. If you take another left, the washrooms will be there. If you have any questions, feel free to reach out to me and I can help guide you. But it's pretty self-explanatory. It's pretty straightforward. For our speakers today, you will note that there are some lines on the ground that have been marked with a black marker on top of clear tape. This is the range of the camera. So we ask that you please not step out of there. It's totally okay if you want to look at the slides, if you want to pace a bit, that's totally fine. But please, if you can try to stay within those markings, then we can ensure we'll have the best video quality for our viewers and for future rewatching of the talk. With the exception of our invited speakers who are giving 25 plus 5-minute talks, so 25-minute talks with 5 minutes of questions, all the other talks will be 15 minutes of presentation, followed by 5 minutes of questions. I will be chairing the first session. I will give you an indication when there are 2 minutes left to your talk, and then I'll give you another indication when you've hit your 15-minute mark. And then if you can hopefully wrap it up quickly, we'll get to our questions. We'll have somebody moderating the YouTube chat so that if there are any questions that are coming in virtually, we can address those and ask those for our speakers here. And then we'll also have a microphone to ask questions or take questions from the in-person audience here today. Maybe the last thing I'll note is you'll note I have a microphone on me. This is the microphone for the people who are joining us virtually. So every speaker will be equipped with this. I'll pass it to the speakers as we go forth. We also have another microphone for the room. So if you think you'd like the extra audio boost within the room, I'll give you the additional microphone. But everybody's going to be equipped with, at the very least, this one microphone that I have on me to ensure that the people online can hear us loud and clear. Okay, so I think that does the spiel. If we can maybe have our first invited talk, Dr. Robert Mann, come down and we'll set the talk up, and we'll get this RQI circuit underway. Thank you. Can I mic you up?
Yeah, just a sec here. Let me get that in here. Get that in here. And what's that thing for?
This is for the
gizmo, right?
Yeah. Set it down.
Here, let me try. Get a better angle.
Wonderful.
Okay.
Yeah.
There we go. That's good. So, when should I start?
Whenever you're ready.
Now is a good time.
Take a head start. Yeah.
Okay. All right. Well, it's 8:55. We're a few minutes early. So thank you for the invitation to speak at, I guess, the first RQI circuit. I think this is a very inspiring effort, student run, student organized. It's great. And I remember when I was a graduate student beginning, talks consisted of taking these acetate sheets and using colored markers and writing on them and putting them on overhead projectors. Now we have live stream all over the world. That's a big change. I was asked to speak about, not so much about a specific research project, but rather about research going on here at Waterloo in my group, and partially connected with the other groups here that work on RQI. So I thought I would say something about quantum probes of black holes, which is something that we've been doing a lot of here. But before going ahead with that, I thought I'd say a little bit about relativistic quantum information itself, which I like to think of in terms of this Venn diagram, which is the overlap of relativity, special and general, quantum physics, whether it's quantum field theory or quantum mechanics, and information, particularly quantum information, but in general the information sciences. And this subject is interested in all three of these things, and in particular, the overlap between them, most especially, I guess I can use this thing here, this overlap right here, but a lot of discussion goes along in these two-way Venn diagram overlaps. So we're interested in how relativistic effects influence quantum information tasks and vice versa, which really is right in the core of that. So now will this switch it? Oh, good. So my group, I've listed them here, and I've put them in the different categories in the circle. I work on all three of these areas, though the quantum area that I do the most in that's strictly quantum is in quantum chaos with Amit and Sanchit. And over here in gravity, I have Nicola DeCock, Michael Gammon, Braden Hall, Mengqi Liu, and Jiayue Yang. The largest fraction up here, though, is in RQI, as you can see, Dyuman Bhattacharya, Taylor Say, Lakshay Goyal, Ireneo Membrere, Max Spatafora, Dicky Suryatmadja, Jiayue Yang, Everett Patterson, and María Rosa Preciado-Rivas. There is also, I've got some former group members that worked on various things here, and some, like Lana Bozanic, will be speaking here. It's hard to know when you count as current or former. I tried to partition it by whether a project had been completed or not that I might give some brief mention to here. So what are the kinds of projects in broad brush strokes? I've got them listed here of the various things that we do in my group that are of interest, things like higher curvature gravity or black hole chemistry, which is a derivative of black hole thermodynamics, and tests of general relativity. In quantum chaos, we've done a lot of work on Wigner negativity and its meaning for entanglement on the quantum kick-top in recent times. That's work in progress. And in RQI, we think a lot about what it means for things to be quantum entangled and how entanglement can be extracted from the vacuum or how it's affected by curved space-time. We're thinking a lot these days about what it means to do superpositions of quantum superpositions of space-time. And we also work on, which is what I'll talk about here, quantum probes of black holes. And I thought of putting, a lot of these belong in the overlap regions here, and I tried to put them in, but it became too crowded, so I thought it would be easier to do it that way. So the recent research projects having to do with quantum probes of black holes are, I'm going to talk about 3 of them. One with Everett Patterson on estimating the parameters of a black hole using RQI methods. A second, which has been done with a number of people, Ken Yoshimura, who's here, Eric Joa, Keith Eng, Chen Zhang, and Yor Maluko. And current work with Maria Rosa, Manar Naeem, a recent MSc student, Max Spadafora, ongoing work, Yor Maluko, and beginning projects with Jiayue Yang. And then finally, I'll say a little bit about work on black holes and superposition. This is work with Shamila Arabachi, another graduated master's student, Dicky Suryatmadja, Matthew Robbins, Josh Fu, Magdalena Zeik. Now, I'm sketching these out. You're going to hear about some of these things in more detail at this meeting. So I'm not going to steal your thunder, Dicky or Maria Rosa, and so on. So, quantum detectors, you hear a lot about this in RQI, and you'll hear some throughout the meeting. They are model systems that couple to quantum fields. They are, if you like, the theorist's view of an atom or of a detector. And they provide us with an operational approach to probing quantum fields. And the standard example in the real world is indeed an atom. An atom, if you like, can be regarded as a detector that responds to an electromagnetic field. It can absorb a photon, which makes its internal state gain energy, an electron jumps to a higher level, or conversely, it can emit a photon when an electron drops down a level. This is something we all learn about when we first encounter not only quantum mechanics, but in fact chemistry. And the simplest atom for a theorist is a qubit. It is a 2-level system with a ground and excited state, ground and excited, separated by some energy gap that's a property of the object. It's often called an Unruh-DeWitt detector after Bryce DeWitt, who was responding in part to criticisms that the Unruh effect, which is the phenomenon that a uniformly accelerated object will experience being in a heat bath. Critics said that's a formal result. You'll never actually be able to measure it. Well, the introduction of this device showed that it could be measured in principle, and nowadays people are actually trying to directly construct such a device to see if the effect can be measured. So I'll often draw the UDW detector like this little box with 2 levels. It's like a quantum dot in some sense, and a key quantity of interest is what I call P, the probability that this thing will get excited if it begins in the ground state. So we deal a lot with 2+1 dimensional black holes in my group, and I thought I would say a bit about why. The main reason is that they are the simplest setting for exploring non-trivial black hole physics. They have a spatial structure, unlike 1+1 black holes where the horizon is a point. Here the horizon has length. It's got a perimeter. And the simplest version solve the Einstein equations. This solution was discovered 30 years ago in the early 1990s, 1993. And people have used it all over the place in theoretical physics to understand quantum gravity better, to understand various properties of black holes better, and here we use it in RQI. One of its key features is that the space-time has constant negative curvature, and the reason why this is of advantage is it makes calculations of density matrices, detector responses, all kinds of other things much, much simpler than they are in higher dimensional settings, typically. So, for example, the Whiteman function, which is the two-point correlator of quantum fields, perhaps the most commonly considered object in quantum field theory, it becomes an image sum instead of a mode sum because of the constancy of curvature. Now, in higher dimensional constant curvature spaces, that's also true, but what's not true is that black holes typically have constant curvature there, whereas in 2+1, the standard black hole does. That's why we consider it. And the hope, as is the case when you consider not fully physically realistic settings, is that what we learn about black holes, about quantum physics, about quantum information, will carry over in some sense to the real world. So let me sketch out a little bit for this. The 2+1 black hole is born out of anti-de Sitter space-time, which itself can be constructed by considering this flat space with two time directions, and what you then do is consider this constraint imposed into flat space. So you have this hyperboloid, and you constrain it to be embedded in that flat space, or rather you constrain yourself to be on that surface in the flat space. And then what you find when you incorporate those together and simplify the coordinates is you get this metric, which is the 2+1, well, the D plus one dimensional anti-de Sitter metric, where the quantity L is related to the negative cosmological constant lambda that characterizes the space. And you can actually visualize what this surface looks like if you are in 2+1 dimensions, so I drew it there. If you consider a scalar field that is conformally coupled, then there's an old result going back again some 30-odd years that shows the Whiteman function, the thing I had on the previous slide, is given by this expression that is a function of the geodesic separation between the points x and x prime. The quantity zeta refers to the boundary conditions of the scalar field, whether they're Dirichlet, transparent, or Neumann, out at spatial infinity. Now, you can compare this to what is typically done for a scalar Whiteman function. You would sum over all of its modes. And you can do this. It's relatively straightforward to construct the sum. What is not straightforward is to ensure the sum converges, by which I mean when you do it numerically, you need to be sure that you've added up enough terms in that sum that you've got convergence, and I speak from experience here. So that is one of the key advantages of this particular case. Now, how do we get to the black hole? Well, the BTZ black hole, I said you've got this covering space, you've got this hyperbolic constraint, and then what you do is, instead of rewriting coordinates to get the metric I had on the previous slide, you can insert this transformation into here, and you discover the constraint is satisfied. That's by design. The metric becomes very similar to what I showed, except you've got a -1 here instead of a plus. And you've got this quantity phi. If phi is unidentified, if it goes from minus to plus infinity, then this is what we call anti-de Sitter space, or more specifically ADS Rindler space. It's the anti-de Sitter version of the Rindler space that was constructed many, many years ago for a uniformly accelerated observer in flat space. These are coordinates used by a uniformly accelerated observer in anti-de Sitter space. However, if you identify phi by this particular amount, then you get the BTZ black hole more easily seen by rescaling phi to phi tilde and T and R likewise, and then you get this metric right here. And phi tilde varies from 0 to 2 pi. And so that's the coordinate system we typically use, and we often drop the tildes. So there it is, and the identification that ensures phi is periodic, you can call it gamma, a map from phi to that thing, if you like, when you're in this particular space. And so what you can do is, if you want to understand or make use of the Wightman function in this space, then you do it by it's been shown you can do it by taking the Wightman function for pure ADS and imposing these identifications on it and doing this mode sum. And in practice, the first of these, the sum over n, often factors out, canceling the term in the denominator, and so you get one of these, but the more general expression is what I've got down right here. The quantity eta refers to boundary conditions of the scalar field at infinity, whether they are twisted or untwisted. We generally consider untwisted conditions. All right, so let me talk in brief about the 3 projects that I thought I'd mention earlier. One is something that Everett and I did. Came out earlier this year in JHEP on estimating black hole parameters. And the basic idea of this project, I'm not going to go through the arithmetic too much. What I want to do is sketch out for you what we did, why we did it, and some of the main results. So the basic idea was to place one of these detectors, these UDW detectors, in some initial quantum state outside of a black hole. When you do that, the detector will experience Hawking radiation, and then after some time you can determine whether or not the detector is still, I've got it in the ground state, I meant to say still in the initial state that you set it in, not the ground state. And this will depend on the parameters of the black hole. And the idea is, let's say the black hole, well, let's regard the black hole as a system that is not that easy to probe. What can we learn about it just from monitoring this detector at a distance? And the idea is that if you do many repeated experiments of this type, or if you are rich and have like hundreds of UDW detectors, you place them around the black hole, and then you then can compute the probability depending on where it is and on when you looked at it. And from this, you can compute the Fisher information to yield an estimate of the parameters of the black hole. And so that's what we took a look at to see how this would work, and indeed it does. Here is an example, one of the many graphs in our paper. The quantum state in blue is the initial state of the detector, ground and excited, with some quantum amplitudes of cosine, sine, theta. We set the relative phase to be 1. And for a black hole at temperature 0.1, energy gap 1 in units of L, which we took to be 1. If theta is 0, you start in the ground state. And for transparent conditions, you can see that the Fisher information does indeed sensitively depend on the mass of the black hole. So what this means is, if you had an ensemble and you waited for a while and measured the probability of the black hole and use that to compute the Fisher information, which I didn't write down here, but it's a well-known expression, you would find that it would peak at various values of tau. And so you could imagine reconstructing this curve and then saying, oh, well, this black hole has such and such a mass, or such and such a temperature, and so on, as the case may be. So the point of this exercise is that it's an in-principle exercise to demonstrate that quantities such as Fisher information that are used in another experiment to estimate hard-to-access parameters can also be applied to black hole physics. All right, now another thing we're working on that's going to come out probably later this afternoon, if I'm really lucky, is falling into a black hole. In fact, I'm not going to talk about the main thing that will come out a bit later. Rather, I'm going to talk about the prelim to it. The equivalence principle, which says a pound of feathers weighs the same as a pound of lead, also says that locally space-time is flat. And that's true anywhere, even in the vicinity of an event horizon. And so, if you have a local enough experiment, which means if you're in a small enough region of space and time, as that region, of space, as that region crosses through an event horizon, nothing special should happen. Now, you hear these stories about getting stretched like a piece of spaghetti if you fall into a black hole. Well, that's true for a solar mass black hole, but it's true because your body is not a local object on that scale. The gravity at your feet is a lot stronger than at your head, so if you dive in feet first, yeah, you'll get stretched like spaghetti. You won't live very long, mind you. But if you had a black hole that was large enough, massive enough, so that its surface gravity were the same as the Earth, you wouldn't know. You'd feel the way you do right now, assuming all people listening are on the planet. So what that means is the response of a quantum detector should be monotonic or at least smooth, certainly not exhibit a thermal response. Now, this has been looked at in 1+1 dimensions by Erickson Joa, Ken Yoshimura and I in a paper that we put out a couple of years ago. But it's a limited sort of test because 1+1 metric doesn't really solve an Einstein equation. It's rather a truncated Schwarzschild metric. Recently, in this paper that came out last year with Keith, Chen, and Jorma, we actually tested this for a Schwarzschild black hole. This folklore has been around for decades, but only here and here was it actually explicitly tested. And I'll talk about that a bit. And right now, we're just finishing off with Maria Rosa, Manar, Jorma, and Max, various things on testing this for the 2+1 black hole. So here I'm showing you a result from the paper with Keith, Chen, and Jorma on the Schwarzschild metric. What we wanted to do was see if what everybody said was right. What will happen if you let a UDW detector freely fall into a Schwarzschild black hole? How will it respond? That was the question we asked. Will it do what everybody says? Because you can't find anywhere in the literature where it was done. And I always wondered why, and as I got halfway through the project, I knew why. It's because this is very painful, and the pain is that mode sum that I told you people about earlier. Getting that mode sum to converge for the various vacua, Hartle-Hawking, Unruh, or Boole-Ware, is very difficult. You add up thousands and thousands of terms, and you're still not sure it converges. The laptops run all night. They crash. You do it again. Anyway, we did it, but it's not easy. And here in the upper right is a diagram of what we did. The red part is where the detector is switched on. And what we do in this diagram is vary the center point of this red region along the trajectory, the blue trajectory of the detector. And we then measure the response of the detector at the midpoint of the region. So you can see all these discrete dots. That's what we actually did, and then the curves are just joined together by eye. Now, what should happen is these curves should just smoothly do this. But you can see they don't. There is, as we called it, a little excitement as it crosses the horizon. We do not know why this is. This is the point of testing the 2+1 case that Maria Rosa is going to talk about later. So let me finish off with black hole superposition. We still lack a quantum theory of gravity, and there's a general expectation that whatever the quantum theory of gravity is, it's going to let us put space-time in quantum superposition. At least if it should. If it doesn't, there better be a darn good reason why everything else does in quantum physics or has that capacity. So we specifically have been looking at the superposition of black holes, and in particular of BTZ black holes. And the reason why, again, the BTZ hole is useful is its constancy of curvature allowed us to use methods from the quantum reference framework of people like Czesław Bruckner and Flaminia Giacomini and Esteban Castro Ruiz, all these people and so on, to do this. And so our thing is, it's one thing to put it in superposition. How would you know what it looked like? Well, go to the store, buy a UDW detector, and see how it responds. So that is what we are looking at. And so the superposed BTZ black hole, here's that BTZ metric written in the other coordinates, so the identification is with root 2m. What you can do using the quantum reference frame method is superpose identifications for different values of m. One for mass A, one for mass B. And the Wightman function then, for the superposed case, more generally is given by this identified sum over the ADS Wightman functions. And in the superposed case, instead of the single gamma, you have a gamma for A, a gamma for B, and then you get 4 different quantities, AA, AB, BA, and BB, and you get the quantum amplitudes for each, and you have to add them all up, as per usual quantum physics. Here is what happens in the non-rotating case. We find as a function of the square root of MB over MA, and that'll have meaning later, as Dickey will point out in his talk, there are resonant peaks at integer values of these ratios. This is certainly consistent of a conjecture Jacob Bekenstein made decades ago that black hole mass should be quantized. And we are in some sense seeing a detector respond in this way. Recently, we have done work on rotation, but that's for Dickey to talk about, and I'll leave that to him. So, those are the 3 things I want to talk about, but there's lots more. I think you're going to hear from Ireneo about how you can extract tripartite in the environment of a black hole. Ken Yoshimura and Vaishant Thakur and I have been working on Unruh auto engines. Ken and Laura Henderson have also worked with me on the first one. Dyuman Bhattacharya, Laura, Ken, and Vaishant wasn't on that one. Sorry about that. Worked on the relationship between entanglement and gravitational shock waves, building on work Erickson and David Kubiznak did, and Finn Gray. Dyuman Bhattacharya has been working on how detectors respond if the inside of a black hole is way more complicated topologically than we generally naively expect it to be. I think you're going to hear from Lana Bozanic later about the circular Unruh effect. When you have a UDW detector orbiting in a circle, it experiences a uniform acceleration towards its center. And we carried out a study recently on quantum entanglement in that setting, and she will tell you about that work with Manar and Ken. We're thinking with all these people here, Everett, Maria, Lakshay, Josh, Magdalena, Dickey, Nayesh F. Shorty, on what it means to superpose space-times, and we're developing different projects to try and flesh that out. And we continue studying what happens when detectors fall across the horizon, and Sajia and Maria and I are beginning a project to try and understand what happens for entangled detectors in that regard. So I think actually I'm a little bit early, which nobody ever is bothered by at a meeting, so thanks a lot for your attention.
Turn this mic on. I'm probably outside of frame, which I think is okay. Do we have any questions either in person in the room or coming in virtually? We have somebody monitoring the chat. Are there any questions coming in person? There is a question in the chat. Do you want to read it or do you want me to read it? Okay, so we have a question from Almas Lafiz. The question is, does the Whiteman function for ETZ black hole converge for, and the LaTeX notation is x to x prime?
No, so I see, yeah, I think the question means if, let me see if I can go back to that Whiteman thing. If you, yeah, there it is. So I think the question means what happens in the limit that x goes to x prime? Well, there is a singularity. Although it's called a Whiteman function, it's actually a distribution. In the technical sense, analogous to the way a Dirac delta function is really what is called mathematically a distribution. So it has singular properties there, but what is relevant about it is its integral over various space-time regions. And those quantities can be made finite. That little quantity epsilon there is a regulating parameter that ensures that the Whiteman function is well defined in appropriate limits and is determined by the boundary conditions of the field. So I glossed over that, but technically it is a distribution.
Wonderful, thank you. I saw a few more messages pop up in the chat, but we have questions in person? Yeah, maybe I should run the mic up to you.
Thank you for your presentation, Professor. Very insightful. Regarding the superposition of black holes, do you know of any studies or you have any intuition about how the superposition would be observed would impact our observation of gravitational waves?
With gravity waves, no, not really. The probability that astrophysical black holes can be placed in superposition I regard as exceptionally tiny. We don't even know how to put macroscopic objects in superposition, really, though some would say buckyballs might count. They've been diffracted. So I don't know. I mean, however, if you're asking, would there be different gravity wave signatures coming from black holes that are in superposition? I expect the answer to be yes. I think that's an interesting research project, but I also think it's a very difficult one. So here I will mention a bit of dirty laundry about the 2+1 dimensional black hole, or a key limitation. There are no gravity waves in 2+1. That's one of the key limitations about 2+1 gravitational physics, that gravitons don't propagate. Most people believe that limiting feature is not fatal insofar as gaining understanding of gravitational physics is concerned, but honestly, it is a limitation. So the problem with the gravity wave thing is you'd have to do it in 3+1. However, you know, whenever I answer a question, I keep thinking of how I do the problem. One possibility might be superposed gravitational shock waves. They could be done. And somebody somewhere in this audience might say, I think I'll try that. That's a good question. Thank you.
Thank you. We have maybe time for one more quick question, either from the audience or online. I don't know if there's anything that came in. Yes, there is something that came in.
Well, as you can see from the picture, wherever the picture is, in the case of Schwarzschild, it happens right at the horizon. We didn't find any evidence it happened anywhere else. However, in the case of the 2+1 black hole, if you can wait a little while, María Rosa will tell you the answer there. One of the key differences is between the two is, apart from the constancy of curvature, is there's only one length scale in Schwarzschild, but there are, one scale period, which is m. Whereas for the 2+1 black hole, there's a length scale, but there's also a mass parameter. So there is more parameter space, if you like, and that does make some difference. But I promised María Rosa I will not steal her thunder, so.
Wonderful. Thank you so much.
Thanks a lot, guys.
Rotating black holes in quantum So, honestly, Maria could have done this. Signal 2 minutes on the back of my iPad. The floor is yours.
Okay, so I am here to talk about black hole mass superposition. And I feel like I'm just going to be repeating a lot of things that Rob just said. Okay. Oh, that's cool. So let's start with the background. Quantum gravity attempts to create a unified theory of QFT and general relativity. In the 1970s, Bekenstein conjectured the existence of black hole entropy. And this was later discovered by Hawking, which was the first convincing insight into quantum gravity. He also conjectured that the mass of a black hole can be discretely quantized, say akin to like the energy state of a hydrogen atom. Now, for the why are we doing this? Well, previous work have done what I'm doing, but they have only done it to non-rotating black holes in transparent boundary conditions. I'm here to further generalize the result by adding angular momentum and additional boundary condition, and see if there are any profound effects. Now, we don't have a complete theory of quantum gravity, so we will be taking an operational approach to the problem. And in this case, we will be taking a physically realizable measurement, which in this case is the excitation probability of the Unruh detector in the space-time. And by probing the space-time with the detector, we hope that to see if any unique property arises. So we have a superposition of two black holes. They have a distinct mass and a distinct angular momentum, and we have them in a symmetric superposition. So I will be representing a black hole with their mass and angular momentum, black hole A with mass A, angular momentum A, and black hole B with its corresponding variables, parameter. So what is a BTZ black hole? Well, it's a 2+1 dimensional solution to Einstein's field equation with cosmological constant -1/L squared, where L is the ADS length scale. The BTZ spacetime is taken by taking the ADS spacetime under the identification phi to phi plus 2 pi squared of m, where m is the mass of the black hole. And the advantage is that its field correlation is in an analytically closed form, whereas its 3+1 dimensional counterpart, say a Schwarzschild ADS spacetime, requires computationally expensive mode sum In other words, it's both mathematically and computationally simple, which is why we're picking it. The general metric is shown in equation 1. R minus and R plus is the inner and outer radii of the black hole, bound by the relation in equation 2. And more explicitly, we know what R minus and R plus is in equation 3. The UDW detector, we are going to use a UDW detector, which is a two-level system with the interaction of Hamiltonian in equation 4. The UDW detector is a simple model of the light-matter interaction, and because it's simple, we like to use it. Eta here is the Gaussian switching function, which we pick it as a Gaussian because it's physically reliable. Mu tau is the monopole moment of the detector, and phi is the automorphic field in the bit-set space-time. Tau itself is just the proper time of the detector. So how do we construct the field? Well, we take the usual mesoscalar field through the identification tr phi to tr phi plus 2 pi n square root of md. N here is an integer, and m, once again, is just the mass of the black hole. Phi can then be expressed in terms of the mesoscalar field in equation 5. Eta here exists only to preserve computational relation, and is -1 if it's twisted, and +1 if it's untwisted. Oh, sorry, I think it's the opposite. My bad. Now, you might be asking, if we're working with two different space-time, then how is it possible? Then wouldn't you have to evolve with respect to two different variables of time? And the answer to that is generally yes. But we have a workaround here, which so we have a time in one of the space-time and a different time in another space-time. But the difference between them is inversely proportional to the distance of the observer, which you can see in equation 8. And as you can see, if the observer is very far away, then the difference in time is very small, which means that we do not need to evolve the state with respect to two different times, and only need to evolve it with respect to one time variable, which is incredibly convenient. As for the excitation probability of the black hole, it's done by tracing the system with respect to the symmetric and anti-symmetric basis. And we obtain the transition probability shown in equation 9. PA and PB is just the excitation probability if they are in their own specific black hole. If they're of a detector in isolated only to black hole A without the presence of black hole B, and PB is the same thing but for black hole B. There shouldn't be a lambda square over 4 term there. It should just be 1. And LAB is a correlation term that's unique to PT. The general form are shown in equation 10 and 11. The Whiteman function, as I mentioned, we here work in different boundary conditions. The Dirichlet, von Neumann, and transparent. Previous work have only been done in transparent boundary condition. And if we insert it explicitly into the terms above, we have these following terms in equation 13 and in equation 14. There are a lot of terms here, so I will, they're provided in the supplementary slides. I will, however, be discussing some of the terms because they're important to analyzing the results. So this is a previous work done by Rob, Jamila, Joshua, and Magdalena. It shows that the excitation probability of two superposed black holes that are non-rotating does resonate at rational values of the square root of the mass of one black hole divided by the mass of the other black hole, which is interesting because it supports Bekenstein's conjecture for mass. But from here on, we will be using R plus B over R plus A in place of square root of MB and MA over MA. We could compare this with the previous work because R plus B over R plus A is equal to a square root of MB over MA if they are non-rotating. But if they are rotating, then they're different. By shifting the variables into inner and outer radii in place of mass and angular momentum, we could we could avoid dealing with pesky quadratic and square root variables and have something linear in place. And of course, linear is much simpler. So here is the transition probability at zero angular momentum. As I've mentioned, the transparent case in the middle, the blue line, have been done before, but the von Neumann case in the yellow line and the Dirichlet case have not been generated. Those results have not been previously generated. And as you can see here, their structure are similar. And the reason for that will be explained later. Now, what if the two black holes have equal angular momentum? Well, the resonance structure does not actually is not actually preserved when the angular momentum change. They are preserved across the different boundary condition, but as angular momentum increases, the amplitudes are dampened, and the peaks undergo some sort of splitting in that they previously singular peak just starts to move starts becoming two peaks that are some distance away from one another. But they do still, but the peaks do still occur at rational values, albeit they're much weaker when at high angular momentum. And in the Dirichlet case, computation is a bit more iffy just because the values are so low. But if we have the von Neumann at the transparent case and they have the same structure, then we could easily infer that the Dirichlet have the same structure, because the Dirichlet case, the Dirichlet transition probability is just a linear combination of the von Neumann and transparent case. And the reason why the resonant behavior are equivalent, as I've promised to mention, is because resonance occurs when values are, when the value of LAB is maximized. The PA and PB doesn't really matter that much. And the LAB have denominator term cosh alpha and m plus minus x. And this cosh term have another cosh term in it. It's a nested cosh. And that cosh term have an nr plus a minus mr plus b term in it. And this whole thing is minimized when the input of that inner cosh term is 0. And that occurs when r plus b and r plus a is of some rational ratio to one another. And this happens in all boundary conditions, which is why the resonance structure are identical. So we have been using angular momentum and have set them as equal in the past two figures. But now we will completely rid ourselves of mass and angular momentum and instead use inner and outer radius as our parameter, because once again, it allows us to rid of a lot of quadratic and root terms. We'll also fix the ratio between the inner and outer radius of each black hole. There's an explanation for that, but if you want to ask, you can talk to me after the talk. The detector behavior, here we have the plot of the detector if rho A and rho B, which once again is the ratio between the inner and outer radius of the black hole A and black hole B. If they're equal, then we have a very nice structure that is reminiscent of the non-rotating case. It spikes very nicely, and nothing seems dampened. But as they deviate, the peak undergoes splitting, and their amplitudes becomes dampened. Just in the square root of 6 case, it's very dampened compared to the rho B square root of 6 case compared to the rho B of square root of 7 case. Because we like what we see with the square root of 7 case, we will henceforth set rho A and rho B to be equal and see what happens, see if anything interesting happens. We've also picked some irrational rho A and rho B. It's not, they don't have to be rational. And of course, this same observation applies to all the boundary conditions. And here we see what happens when we change the energy gap. It's not that interesting. The resonance, it does dampen the amplitudes. It doesn't make them go through peak splitting which is to be expected because this should only change the amplitude terms. But this is the most interesting result, which is what happens when we vary the distance of the detector from the black hole. And what we see here is that distance does not affect the, you have an inset here, which is just the value at larger values. The location of the peak appears to be preserved, and increasing the distance only affects the amplitudes, which is to be expected because it only affects the amplitude, the value of the integrand, and does not affect gamma at all. And the domain is affected by the changes in R because the location in which the detectors become swallowed by the black hole changes. There's an equation for that if you want to see it. The resonances occur at rational values of gamma as per previous work, which is nice. And the transition probability converges to some value as the distance approaches infinity. This could be explained as the detector responding primarily to the spacetime identification rather than to the black hole. So in conclusion, what we have? Well, in conclusion, we have successfully generalized a non-rotating black hole to cases with non-transparent boundary condition and angular momentum. Adding angular momentum and energy gap decreases the amplitude, although adding angular momentum does make it undergo peak splitting. As the ratio of inherent outer radius of each respective black hole deviates from one another, they undergo peak splitting and also have a reduction in amplitude. But most importantly, the resonance structure of the transition probability acts uniquely at rational ratios of the radii, of the outer radii, as in the previous graphs. And if the inner and outer radii are equal, then it becomes similar to the non-rotating case. This support Bekenstein's conjecture with a slight modification. Bekenstein conjectured that mass can be quantized, but because we see here that special property when angular momentum is present occurs not when mass, not with mass, but with the outer radius, we theorize that what is quantized is not mass, but instead the outer radius of the black hole. And these are the terms that I mentioned are supplementary. Yeah, and any questions?
Do we have questions for Dickie either from our in-person audience or coming in via YouTube Live? So I might abuse my power as chair. So you say that you kind of rephrase Bekenstein's conjecture into believing that it's about the radii, the inner and outer radii. Do you have any sense, like, so this is in 2 + 1 dimensions. Is there a similar relation between radii and mass in 3 + 1 dimensions, in particular for rotating black holes? Do you have any idea of what might, can you comment on what might happen there?
Basically, most of the results here are computationally obtained. And with 3 + 1 black hole, it becomes very expensive. You might get like cubic or quintic terms, and it becomes, and computers might not be able to calculate that. So I'm not sure, but it would be an interesting thing to look at.
Cool, thank you. Any other questions? Otherwise, we're doing well on time right now. Maybe time for one quick question, if we have it either live or virtually. Otherwise, we will get our next speaker, María Rosa, to come set up, and we'll thank Dickie again for his talk.
Here you go.
Thank you. Maria, being one of the organizers, can get her stuff set up pretty well. Okay, and you need help getting it, or you have it figured out? Cool. So Maria Rosa will be telling us about quantum detectors freely falling into black holes.
Thank you, Everett. Good morning, everyone. My name is María Rosa Preciado-Rivas. I'm a PhD student at the University of Waterloo and the Institute for Quantum Computing. I am presenting a project titled Quantum Detectors Freely Falling into Black Holes, which is a work in collaboration with Manar Naim, Robert Mann, and Jorma Loco. Before I start, I would like to acknowledge that I stutter, which means that it might take me longer to say certain words, and that is why I thank you for your patience. Okay, so let's consider a quantum scalar field in a curved spacetime. In curved spacetime, and even for non-inertial observers in a flat spacetime, there is no distinguished notion of particles. That is why, in order to prove the physics of the field, we let a quantum detector interact with it. In this scenario, the transitions going on in the detector will correspond to absorption and emission of the field quanta, that is, of particles. This is how quantum detectors provide us an operational approach to describe particles in curved spacetime. In other words, we are saying that particles are what particle detectors detect. The simplest model for a particle detector is the Unruh-DeWitt model, which is a two energy level system that undergoes transitions between its ground and excited state. And the quantities that we are interested in calculating are the probability of the transitions between these states and the derivative with respect to the total detection time of this probability, which is known as the transition rate. So there are a few things that we have learned using these quantum detectors, and one of those is that for flat spacetime, the quantum state that is associated with a vacuum, that is with no particles, for an inertial observer corresponds to a thermal bundle of particles for an accelerated observers. Moreover, they will see that the temperature of these particles will be proportional to their acceleration. In the case of black holes, we have learned that for non-inertial detectors, like those that are static or that are co-rotated with a black hole, they will show this thermal response. And we expect that inertial detectors, like those that are freely falling into a black hole, they won't show this thermal response. And furthermore, that this response will be some monotonic, maybe some trivial function that will depend on their proper time. However, they recently discovered that freely falling detectors into black hole can show some little excitement across the whole horizon. I am referring to this work by N et al., in which they numerically calculated what is the transition probability for a detector that is falling into a 4-dimensional Schwarzschild black hole. They found that the transition probability as a function of this radial midpoint of the interaction interval has this local maximum and local minimum near the event horizon. So my research question is how general this phenomenon can be. can we find this little excitement across the horizon in other spacetimes? As I mentioned before, what we expected was to see this monotonic function, and that will also apply as the detector crosses the horizon. For general spacetimes like the four-dimensional Schwarzschild black hole, this is a very computationally intensive task. However, if we look at lower dimensions, then this task becomes tractable. This is why we are looking at the BTC black hole, which is a spacetime in only 3 dimensions, has a constant curvature, and can be understood as just ADS3 spacetime with identifications in its angular part. And we can also see that has a fairly simple line element. There's some previous work by Hodgkinson and Luco in which they calculated what is the transition rate for a detector that is falling towards a BTC black hole. However, they didn't calculate what is happening near the event horizon, which in this figure should be somewhere here. So what we did was to follow their work. And what they did was to consider, of course, a detector that is freely falling towards this BTC black hole with a trajectory that is described by these coordinates, which are going to depend on the curvature of the space-time, the mass of the black hole, the initial position of the detector given by this parameter Q, and of course, what is the proper time of the detector. They also consider that the detector has energy gap E, and that is interacted with a massless scalar field in a vacuum state. This is the expression that they found for the transition rate that will depend on the total detection time, the gap of the detector, and the Weidmann function of the field. One of the reasons calculating this response in BTC spacetime is that we can write the Weidmann function for the BTC black hole as an image sum of the ADS3 spacetime, taking into account what are the identifications. And this is the final expression for the transition rate, and we are going to see that it depends in a non-trivial way on the detector's gap, its proper time, its initial position, as well as the black hole's mass and the boundary conditions of the field. And this is what we calculated. There are a few remarks regarding this expression. The first one is that the n equals 0 term will be what is will be the rate for a detector that is on pure ADS3 spacetime that is no black hole. And the second remark is that this argument for this square root here will eventually become negative within the integration interval for the terms with n equal or larger than 1. As a result, we are going to see that our transition rate is going to have some points in which isn't going to be smooth, which are given by this expression here, and we have coined those points glitches. And now we are ready to see some results. Here I am showing what is the transition rate as a function of the detector's proper time. When it is 0, it is at its initial position, and when it is pi/2, then the detector is at r equals 0. First, I am showing what is the n equals 0 term, which is the rate for just a pure ADS3 spacetime, and Actually, here there are 3 curves, each one corresponding to the different boundary conditions of the field. Now, with these vertical dashed lines, I am showing where is the event horizon, and we are also showing what is the previous work by Hodgkinson and Luco, and we can see that it's enclosed to the horizon crossing. And now these are our results for the BTC black hole. We can see that there is something non-trivial, or these oscillations going on near the event horizon, and they are shown in more detail in this inset here. We can understand more about their behavior when we show where the glitches are happening here. Some of the observations that we made is that this rate will differ more from the pure ADS3 rate whenever the first glitch is reached, and the difference will become more pronounced as more glitches are reached. Because BTC is a fairly easy space-time to work with, we were able to explore a wide range of masses and the detector's initial position. I believe this is still working. And we can see that for the smaller the black hole mass, or the nearest the detector's initial position, then the more this transition rate for the black hole is going to differ from the pure ADS3 rate. Yeah. Sorry about that. Finally, we can see that our results for the BTC black hole show some similar behavior near the event horizon that is similar to what was observed for the 4-dimensional Schwarzschild case. Finally, I would like to talk about some future work that we would like to do. The first one is to look into other 3-dimensional spacetimes like the BTC Geon, which is a work that is actually already in preparation with Max Espadafora, and we also want to look at what happens at the detectors that are freely falling into rotating BTC black hole, which is a work that is in preparation with CGA1. Also, we also want to study or to look at what happens when we increase the number of detectors that we are looking at. In the first case, we want to look at 2 detectors that start entangled and then one falls in, which is similar to the work made by Ken, Erickson, and Rob. But in this case, they consider just a 1 plus 1 metric. And we also want to look at when 2 detectors start on the grounded state, and to look at how much entanglement can be harvested from the field. And we would like to study what is the entanglement amplification and shadow when these detectors are falling into the black hole. And to summarize, so we knew that there was this little excitement across the horizon for a 4-dimensional Schwarzschild case. Then we look at the BTC black hole, and we numerically calculated what is the transition rate in this case. We found that for certain parameters, we can also find a similar effect. There is some oscillations going on near the event horizon. However, you might have noticed that we describe what is going on, but we never answer to why. And that is part of some future work, is to understand why this is happening. And finally, we also want to look at what happens with the BTC Giant black hole and to our rotating BTC black hole, as well as what will be the entanglement and correlation if we look to detectors that are falling into black holes. That is everything that I wanted to say to you today, and I thank you for your attention.
Thank you so much, Maria. Do we have any questions from our audience here? I realize the live stream is a few seconds delayed, so as I ask for questions here, it will take me a few seconds for the information to traverse over to that. Yes, do you want me to?
So the detectors are freely falling.
Yep.
Right? So in principle, one could expect that because the detectors are freely falling, they shouldn't expect anything different than what an inertial observer in the semi-Minkowski vacuum would see. Now, like using basically arguments based on the equivalence principle, do you have anything to say about like how is the equivalence principle related with the result that there is excitement across the horizon sometimes?
Okay, thank you for your question. That is the question that I always get. So I will answer this in two parts. The first one is that the equivalence principle was stated for classical observers. And now we are having quantum fields and quantum detectors. So to be honest, I am not sure how the equivalence principle will apply to them too. And the second part of the answer to this question is that we actually see that we can get, because we can tweak both the mass of the black hole and the initial position of the detector, we can tweak these two parameters in order that these oscillations or these peaks or this little excitement that we are seeing can be as far or as close as we want from the event horizon. In that sense, I will say that there is actually nothing special about it. Yeah.
Thank you. Do we have any other questions from people?
Hi, thank you for your talk. Yeah, so this is like particle Hawking back.
Yes.
Yeah. Now, you're looking at or asking about the equivalence principle, right? Like, in this case, you have like bath, like Hawking temperature or Hawking radiation, right? So, like I would compare to like Bohr vacuum or something like that. And since you're using like transition, were you using transition rate?
Yes, transition rate.
Like you can stop the interaction right before entering the black hole, so that everything will be like well defined or something like that, right?
Okay.
Like, or yeah, so and there's a paper by this study and others in 2018 that they did let the detector fall into the black hole and Bohr vacuum and that kind of stuff. So if you are willing to do like equivalence principle stuff, maybe you can take a look at it.
Okay. Thank you again. Good.
Wonderful. Thank you so much. There's, I'll ask, are there any other questions here in the room? Before we move on? There is another question online from Natalia. It's a bit lengthy, so keeping in mind the time, I think I'm going to let our speaker maybe take a peek at that and answer you, Natalia, asynchronously or in the future. our next speaker to come down, Dyuman, if you can come down, and we'll get you set up. Thank you so much. Let's
Thank
thank
you.
Maria again.
Thank you.
No, it's okay. I'll just. Thank you. Okay, but it still does the slides. So laser is this button, and then slides back and forth. Is that one? Okay. Thank you very much.
So our next speaker is Dyuman Bhattacharya, who will be talking about probing hidden topology with quantum detectors. The floor is yours.
Hello. Today I will be presenting work I did along with Dr. Mann and Dr. Luco of the University of Nottingham. So we should start with a very simple question, which is what's inside a black hole? And the interior of a classical black hole is predicted to have a singularity. But the black hole could also have non-trivial topology hidden from external observers by the horizon. And this leads to the question, can an external observer probe the interior topology? And the answer, as you might expect, is yes, with an Unruh DeWitt detector. And we will gauge the response of the detector with its transition rate. So we'll work with 2+1 dimensional black holes because they are a simpler problem than their 3+1 dimensional counterparts. And specifically, we'll work with the BTZ black hole, which is a quotient of 2+1 dimensional anti-de Sitter spacetime. And other quotients are possible, however, and they give rise to different interior topologies. This is constructed using a discrete group of isometries, which is general for creating quotient spacetimes. So the BTZ black hole can be generalized to form the RP2 Geon, named because the identifications switch the singularity from being a singularity to the real projective space. And this is formed by identifying points in the BTZ black hole spacetime. And the object that results is similar to a black hole whose interior is like a Klein bottle. No external observer can perform a classical experiment that will determine whether he is in the BTZ or RP2 Geon spacetime. But this changes if he's given a UDW detector. So the major difference between the RP2 Geon and the BTZ black hole is that the RP2 Geon is not stationary. It does not admit a globally defined time-like killing vector field. And this non-stationary feature is concealed behind the past and future horizons of the black hole. So classically, no external observer will be able to see this dynamical characteristic. But the UDW detector is sensitive to the dynamical character of the Geon. Now, a Swedish group has constructed the next simplest non-trivial case for a Geon spacetime, and we shall call this the Swedish Geon. It has a single asymptotic region like the RP2 Geon, but a very different interior. And you can picture its construction by identifying points on the Poincaré disk, which is a representation of anti-de Sitter spacetime. And crucially, there are two generators to the discrete isometry group that produces the Swedish Geon spacetime, which complicates matters numerically relative to the RP2 Geon, as we shall see. So the transition rate is a functional of the Whiteman function, which is the two-point correlator of the scalar field we work with.
And we'll obtain the Whiteman function of the quotient spacetime from a parent spacetime using the method of images, so an infinite image sum. And the parent spacetime we consider, as you might have guessed, is anti-de Sitter space, which has a known closed form expression for the Whiteman function of a massless scalar field. And the transition rate that we will consider is for a detector that's switched on in the distant past and is a function of the readout time, which is to say the moment the detector stops interacting with the field. So the Swedish Jian, having two generators in its isometry group, complicates matters. So any combination of the two generators must be included in the image sum. So read out any string of generators, they don't commute, and that will have to be included in the image sum. So Dr. Luco and Dr. Hodgkinson of the University of Nottingham derived the following general expression for sharp-like switching when the detector is switched on in the distant past. And usefully, I mean, numerically speaking, it only involves one integral, which is great considering how complicated the integrand is. We can work pragmatically by grouping the terms in the image sum by the number of generators that are acting on X prime. Now, because the generators in the RP2 Jian are involutive, there's only two image terms. But the Swedish Jian has an exponential growth of image terms. The number of image terms with n generators acting on X prime grows as 3 to the power of n. And a finite term approximation is going to be used when evaluating the transition rate because owing to the complexity of the matrix forms of the generators, no closed form expression for the Whiteman function can be found, nor even a very clean, nice-looking infinite sum. And we check the validity of our approximation when we include n generators by comparing the transition rate under the approximation with n plus 1 generators. Now, this, luckily, because of the specific matrix form of the generators and the form of the Whiteman function in anti-de Sitter spacetime, terms with a large number of generators are suppressed by successive factors of e to the negative square root of m, where m is the mass of the black hole. And we consider only suitably large masses. A very crude reasoning shows that you can find a rough relation between how the mass of the black hole and how many terms you want to include in the image sum. But this is something that's only pragmatic in nature. So in the following, we consider Neumann boundary conditions for the field, but what is to follow is quite general and holds for all three possible boundary conditions for the scalar field. And the mass of the black hole is kept the same for all spacetimes. We are considering the anti-de Sitter, BTZ, RP2, and Swedish Jian spacetimes. And the UDW detector is external to the horizon and is kept stationary. So, as you can see, the RP2 Jian spacetime crosses the preferred spatial slice at t equals 0, and then is constantly different from that of its parent spacetime, which is BTZ. And the Swedish Jian, on the other hand, experiences a bump. It approaches what a preferred spatial slice at t equals 0, crosses it, and then dies back down to ADS3 spacetime. And this is for a gapless detector. So the behavior of the detector in RP2 Geon spacetime is as expected. In the distant past, it's not on the preferred spatial slice, which is created from the construction. As a result, if it's read off in the distant past, our experimenter will be unable to tell whether he or she is in BTZ or RP2 Geon spacetime. But as the preferred spatial slice at t = 0 is crossed, the difference in the transition rate turns on and asymptotes off. And in this way, the UDW detector is a probe of the dynamical features of the black hole interior. But the Swedish Geon spacetime is indistinguishable from ADS3 spacetime in both the distant past and future. So there's a limited window in which our experimenter would be able to differentiate between the two spacetimes if he was only using the transition rate to differentiate the two. So in a nutshell, we can characterize the difference as being a bump versus a plateau. And as I said, the same behavior is observed in all possible boundary conditions, and the modification of the detector to have a non-zero energy gap also does not change this phenomenon meaningfully. As you might expect, all that occurs is that the transition rate acquires an oscillatory behavior, and a smaller mass black hole exhibits the same behavior. This has been checked to thousands of image terms, which, while no means definitive, is very strong numerical evidence that this is a real distinguishing feature of these two geons. So here you can see the same transition rate, but for a gapped a gapped UDW detector. So again, there's an oscillation, but the envelope is a bump versus the rise and plateau. So we found that quantum detectors do probe black hole interiors, and the qualitative difference is due to the different topological identifications made to construct these two spacetimes. And these distinct interiors would be accessible to an external observer, even though the metrics are identical outside of the event horizon. And I'd be happy to take any questions now.
Thank you so much, Dyuman. Do we have any questions, either from our live audience or from our YouTube audience, for Dyuman and the hidden topologies? Yes, I see one in the back. I will.
Yeah, thanks for the talk. So I was wondering, you said that when you're looking at these Swedish geon, you have to make an approximation just because of how many times show up. I'm wondering if you've looked at, or you know the answer to this, if you took, let's say, a higher order approximation,
Yeah.
does that change much what the result looks like? Because it looks like initially in the Swedish geon, the kind of, you had a plot up there. The slope of the growth is very similar to the slope of the growth in the RP2 geon. Yeah, this one right here. The slopes are very similar. I'm wondering if you took a higher order approximation, does this bump kind of grow for longer? Does it shrink, or is the shape basically the same, and you kind of determined the approximation you're making is good enough for your results?
Yeah, the bump grows for the beginning as you increase n, but as you keep increasing n, qualitatively no meaningful change occurs past a certain point. And this curve, for example, is n equals 4, so that's some hundreds of image terms. But if you go to n equals 5, 6, 7, even 8, though there's no curve for n equals 8, you'll not see any visible difference. And at n equals 8, there are some tens of thousands of image terms that are being included. So like I said, that's strong numerical evidence that this is a real feature.
Thank you very much. Thank you for that question. Do we have any other questions live or virtually? It is interesting how they do kind of grow at the beginning at that same rate. Yeah, I'll maybe ask one question. So here this is 2 + 1 dimensional space-time and black holes, and we're looking kind of at the differences in the interior topologies. Are there similar things that happen in other dimensions, or is 2 + 1 dimension special? Like, are there like higher order geons for like 3 + 1 dimensions, or that sort of space-time?
Yeah, there is a higher order geon, like there's the RP3 geon for, I believe it's a geon of the Schwarzschild black hole, though I could be mistaken. 2 + 1 dimensions is easier because mathematically it's a lot simpler. As Dr. Mann said earlier, instead of having mode sums, you end up with image sums, and that greatly simplifies matters. Yeah.
And are there other interests? So like somebody obviously developed these geons. I mean, the Swedish group did it like it was like 25 years ago or whatever. Was it just like, do people construct these and say like, oh look, this is like a neat thing that satisfies certain equations, or are there other kind of applications to these geons? Yeah, like are they purely like generalizations of black holes, or like specific cases of black holes, or are there other kind of areas of physics where people are interested in these? Like, have you come across any of that as you tried to understand what geons were and how they behave?
In my review of the literature, it seems that this was done for its own sake, as special, as non-trivial generalizations.
Okay, cool. Any last questions before we cap off this first part of the Waterloo stage of the RQI circuit? Looking at my online moderators, I don't see any notifications. If there are questions, please do feel free to write it in the comments of the YouTube video, and we'll try to get to it and flag it to the speakers and
Okay, welcome everybody to the second session of the RQI Circuit at Waterloo. To start this session, we have Eduardo Martín-Martínez, who is also the co-chair of the ISRQI, to talk to us about career development.
Thank you. Just 1 second while I adjust this. Hopefully you can hear me both here and online. Hello, nice to see you. I'm going to talk a little bit about career development in RQI. I'm going to start talking about academia in STEM, and then I'll try to particularize to our context. Now, let me give you a little warning before we begin. I'm going to start with very bad news. You'll hopefully get better as we go, but I think it's really important to be aware of the reality of the situation in academia. So we go there knowing what, what we're up against and what our expectations are, right? So again, a little dose of reality first, and then we talk a little bit about how to handle academia, or career development in RQI, academia or not academia. All right. So let me first say, I want to talk only for like 10 minutes, and I prefer to have 10 minutes of discussion and questions, but we'll see how we get. This talk is definitely aimed at PhD students and mainly junior, let's say, people who just started their PhD. Of course, is, I think, hopefully be helpful for master students and also PhD in the later stage and even postdocs. At the time that you reach the postdoc stage, you tend to be more aware about some of the things that I'm going to talk about, but just in case, the main aim is people who are in the first half of their PhDs. All right, it's not moving. Wonderful. The remote stopped working? Yeah. All right, I have an interesting article, a really, really interesting one. There's a lot of research, serious research. This is from his blog post, right? But it's a researcher in economics. And this person, among others, analyzed the economics, the way it works in academia, right? And how similar, not only academia, actually analyzed several professions that are similar. And it's an interesting read. It basically says how academia resembles a drug cartel or drug gang. Academic systems rely on the existence of a supply of outsiders ready to forego wages and employment security in exchange for the prospect of uncertain security, prestige, freedom, and reasonably high salaries that tenure positions entail. Okay, so what's the message here? Let me summarize it for you. How do drug cartels work? Drug cartels work in a very pyramid kind of scheme, right? You have the bosses of the cartel at the top, very few people. In fact, typically one family, but very few people. And then you get more people the more you go up, all the way to street dealers. And the street dealers, why do they do it? Those are the ones exposed. It is dangerous. They make almost no money as compared to the people on the top, right? Why do they do it? Well, because maybe they can go up the ladder. And there's the expectation that they will become big in the ladder eventually. Other professions, other careers that are like that are, for example, acting in Hollywood. People who go to Los Angeles, right, and go to Hollywood and say, well, I'm going to start doing small things and I'll make my way up. There are very few people at the top of that and many people at the bottom, right? So sadly, the economics of academia is like that. The outsiders are you. And by you, I mean PhD students, postdocs, not professors, people with tenure. This is just the terminology that is used in these economic papers. People inside the system with a secure position versus people who may or may not have a secure position there eventually. And the more time it passes, back in the day, if you've watched, for example, Oppenheimer, right, they show how everybody there got positions and everybody, well, there was a time that it was much easier because the rate there was increasing, the number of academics, and the available positions were increasing accordingly. Those times are long gone, and now we will discuss those proportions now. Let's talk. I don't know why. Sorry about that. Maybe the adapter. Yeah. So the first question that one needs to ask at that stage in the PhD is, well, should I do a postdoc? Should I continue in academia after my PhD? And let's make the case about it. So academia right now, and this is related to this article that I mentioned, is not designed for a large proportion of graduate students to become researchers. It is not. Sadly, academia is definitely not designed for that. And I know when you do theoretical physics, in general, above all if you're a theoretician, right? Maybe in other fields of STEM is different, but if you're a theoretician, Most people start a PhD thinking that they want to be academics. They want to do research. System is designed, this pyramid scheme that I mentioned is not really designed to absorb every single PhD student in research, at least within academia. Now, oops, I didn't want to say that. I wanted to, well, whatever. So the question that I wanted to actually ask the audience, but apparently I also have the answer here, is on average, this is in STEM. STEM is counting, I'm going to be quoting studies from the Royal Society 2010 and 2015. How many PhD graduates are supervised totally during a professor's full career? The average is 30. Of course, it varies a lot with groups, right? It varies a lot in the experimentalists versus theoreticians, but the average is 30. So if you do a very, very fast Fermi estimation of what is the chance that a PhD graduate ends up being a professor, well, I mean, it's 1/30, right? The professor retires, releases one position, and after releasing that position, there's 30 potential PhD students. Maybe we need batteries for this. PhD students that may compete for that position if they all wanted to be professors, right? So the Fermi estimation, if you want, would give you a 3%. Let's see real data. Okay, this is real data for STEM, including math as well. So this is a study from the Royal Society 2010, and basically what you have here is everybody who finishes a PhD is the 100%. That's what the 100% means here. So of all those people, 53% go careers outside science. Okay. Now, 47 of them continue. They get into this early career research. That would be the postdoc stage, if we want to call it within the more familiar terms that we use. And then among those people, some of them go to non-university research within industry or government agencies. And the rest go, a lot of them, the immense majority of them, after postdocs, go to careers outside science. And then 3.5% basically make it here, which is the equivalent to the tenure stage or stabilization, either tenure or indefinite contracts. Okay. And now they have this, and the criteria for professor that they use is kind of irrelevant. This stage, if you make it here, you've made it, let's say. Okay, of course, getting full prof is tougher, but that's not what we want to focus on. So the one thing that we see here, right, is that if you want to go outside science, the moment is after your PhD. And this is something that is often not talked about, and this is what studies tell us. If you do a couple of postdocs, well, it depends a lot, right? If you are an experimentalist working on, let's say, you're doing a quantum technologies postdoc and you work with Microsoft, doing postdocs is fine. It's not going to affect your prospects of being hired at the same level as other people that are your age. But you are less hireable the more you continue outside of science, the more you continue in your postdocs. And the reason is because companies tend to want people who are young and they can mold, and tend to like people who don't really, that will not leave them, that haven't seen that much of the world, let's say, and they can secure. Those are the two factors that make people more hireable here, more desirable for the private sector if you want. So this is something that should be talked about, that during your PhD you need to decide. If you are going to not want to continue through this, and we will talk a little bit, the moment to actually leave is PhD. And there is the bias, we will talk about several biases here, that you are overexposed to academics. We all are. As you grow up in university, all that you see is academics. You have an immense exposure to survivors of the system. And you know what? You see the professor, you see us, and you go, this dude is not that clever. I can do that stuff. So of course I'm going to make it. You see, the problem is that you are right on that, but the factors that characterize your success are not that much related only to how good you are. All right? So there are many people who are very good. And that's it's neither necessary nor sufficient to actually make it to that stage. All right? So it's something that you need to consider and take into account. We will talk a little bit about that. All right, so yeah, that's what I was talking about. So be aware that you overexposed to tenure academics. You are very overexposed. So when you make your career decisions, your environment is nice to, and we will talk about talking with people, but typically in theoretical science in general, options outside academia are not even contemplated because people think they're not cool. And they are extremely cool. And they're, let me tell you one thing, they're extremely much better paid than options within academia, by far. We're talking an order of magnitude. People like theoretical physics outside, that's what I want to say. People hire theoretical physics outside academia. People want people who are clever and can model things in many, many fields, all right? So this is something that you should not overlook while you're doing your PhD and looking for career prospects, all right? Second, luck. Being at the right place at the right time, meeting the right people. And we will talk about how to play with those odds a little bit, right? That's the second part of the talk, the not so green part of the talk, hopefully. But it's important to acknowledge that being good is not enough, okay? Being good is certainly not. I've seen many of my colleagues that I consider extremely good leave. And that's not because they were bad or they weren't working hard. It's because they didn't have the luck to be at the right place at the right time, meeting the right people, applying for the right places, or applying at the same time. You see, the number of applicants for positions tends to be of the order of the standard deviation, meaning that fluctuations play a big role in a given application. You may have gotten an application one year, but the next year, no, because you know the people who applied, right? So this is something to be aware of, the role of randomness in actually making the cut. Now, that's it, okay? When do you have to decide? Well, what I would recommend is that you don't wait until the very end, okay? We will talk about when to apply for a postdoc if you want to go, but don't wait until the very end of your PhD, all right? It's very important that you start thinking about it, not before you start, when you know a little bit what it's like, but think about your second half. Like when you finish your first half of your PhD, start thinking about what you want to do, okay? And start thinking how you can, you know, prepare yourself better for what you want to do, okay? So this is very important. Don't wait until the end of your PhD to think about this. We'll talk about the particular case of Waterloo because we're in Waterloo. Waterloo is particularly good and lucky, I guess, lucky with these things, but wait till until the end is a recipe for disaster, stress, you know, and sleepless nights. So you need to start thinking about it and taking steps towards whatever you decide around the half of your PhD, okay? Now, we're going to make an assumption here. We are aware that academia is a pyramid scheme, very similar to drug cartels. We are aware of that. It's not rainbow land. I thought it was rainbow land. Always did. It's not. But we know that the probability of making it is low on average, but we are decided to continue, okay? So that's the assumption I'm going to make from here on, all right? Okay. You want to continue. You want to stay in academia. So I'm going to give you a little bit of general advice or ideas, and we can talk about them. So these are the good news. Even within academia, if you're working in RQI, you're appealing to many people. What is nice about it, we will talk about it, at least statistically. Statistically, RQI, we have Rob here, for example, who actually keeps really good statistics of what his graduates are doing. They're really good. They're above that threshold that we talked about of the 3%. In my limited experience, all my graduates so far are within academia. Again, arguably, there are not that many, but Achim's graduates as well, the rates that he has. RQI, at least in Waterloo, has good numbers. So that is not more than 50%, not more than 40%. So I'm not going to tell you the exact numbers, but it's better, certainly. Some of you may know. And you know, your skills are liked. I can tell you about my own graduates. My own graduates have gotten positions all the way from high energy physics to quantum optics, from gravity and quantum gravity and quantum information. So people like the skills in RQI. Now, the issue here is how do you make sure that they know they should hire you, that those skills are what they want. So I'm going to talk about some general advice and hopefully finish soon so we can discuss a little bit about it. Advice number one, piece of advice number one, know your field. Don't just limit yourself to knowing what your group is doing, or your group are doing, right? No, know your field. Know who's working on things that you like. Check the archive, participate in journal clubs, talk to people, talk to your supervisor, know your field. Know the people that you would love to work with. That is very important. And also know the people you would not want to work with. This is very important. Know the field. Get some knowledge of the field. Supervisors are going to help you with that. Your Fellow PhD students are going to help you with that. The archive is going to help you with that. Discuss. If something interesting, bring it up. Okay, discuss, talk, check, see what other people are doing. In conferences, check the talks that you like the most. Don't skip a talk because your talk is next. I'm very nervous, I understand. I'm going to skip the previous talk. No, don't do that. It's okay. Your talk is not going to change that much if you are there that hour or not. Be in touch with what people are doing. Very, very important. Now, here's an interesting one. Networking, right? Like in many fields, this is, I think, arguably even more pronounced outside academia in high-level jobs, right? But the value of networking, the value of being known, the value of people knowing, oh, that's the student that did that. Oh, okay. Being known is extremely important. One thing I recommend to all my PhD students is that in the second half of the PhDs, they go and visit some other group, a group that they like, and they spend some time with them. Even better if you have the chance to travel to see several groups. Now, arguably funding is tough. The University of Waterloo has some funding for that, so be aware of those things. But, you know, sometimes you can just contact the group and say, look, I'm doing this. I'm going to be flying because of this conference. Can I visit for some days? And sometimes those groups will be able to help you and host you. There's no harm in asking. So try proactively to reach out and visit other groups. Again, above all in the second half. Luckily, it's true that Waterloo is very privileged. People visit Waterloo. There are many people who come through here. But it's very different when somebody's visiting and meet, I don't know, 50, 60 to 100 people than when you are the visitor from Waterloo that is there and everybody wants to know what you're here and what you're doing and how does it relate with what they do. Be known. In conferences, when professors are talking, you don't go, I mean, it's great to talk with the students, it's really great. Networking within students is fantastic. But make the effort to also network with non-students, with people above your stage in academia. Talk with the professors. It's very intimidating, I understand. You need to make the effort to join the circles and talk about it. For that, your supervisor can help. Your supervisor will introduce you. I know you can be shy, you can feel nervous. I've been there, everybody has been there, but it's really important. That's how I met Achim Kempf or Mann and all these people that inspired me to come here. Okay, so it's really, really important in conferences, in visits. Talk to people, don't be shy. Don't just go with the students, okay? It's really nice to go with the students. Don't just go with the students. Make sure you participate in conversations with the people that are in higher stages of your career, the people that will be responsible for hiring eventually. Be interested in their work. Ask, participate, okay? Super important, the support of your supervisor, except for extreme cases that can always happen because, you know, the tales of Gaussians are, we like to say many times in RQI that they're almost compactly supported, but they're not. You do get low probability events happening, but for the general part, your supervisor is not only going to support you, if he's doing it too, okay, if the supervisor is doing his job, or their job, sorry, they are going to have to support you. Don't be afraid to ask. If there's a problem with your supervisor, people can help. So if you have a problem with your supervisor, talk with your supervisor. But if talking doesn't make it better, try to, you know, talk to other people. We are here to support each other. Nobody is going to use it against you. That's the main thing. If you come with a problem to a professor, they're not going to use it against you. It's easy to think that you have things to lose by doing it, but no. Always ask. If you have concerns, don't keep it to yourselves. Talk them out. Talk them out. Don't get burned out. I wanted to talk a little bit about that, but maybe I'm going to leave that for later. The difference between different kinds of postdoc applications. Maybe my recommendation would be here. It's nice to apply for things, for groups that are hiring people, but it's much better to apply for fellowships. Fellowships are postdoc applications where you have funding to do with a given group, but you are free to do your research. And you're not a burden to any group, so you don't owe things to the group leader. The postdoc stage for you should be a stage of exploration and getting your own line, slowly establishing your own line. Of course, working together with wherever you are, that's why they're there. But you need to establish your own line. Now, this is very important, and I really want to talk about it. Confidence versus skill. There was a time in the evolution of the humankind where the two were correlated. Now, if you were really confident that you can deal with a wild lion that appears in front of you, if you don't have the skill, nature will take care. I think this is why our tribal nature tends to identify confidence with skill. News, probably you all know. That's not true. They're not correlated. Above all nowadays, you can be extremely confident and have very little skill. I'm pretty sure you've met people like that. What is the sad part? The sad part is that in interviews, your skill and your confidence count almost equally. If you start saying in the interview, no, I'm the worst, I'm not going to be able to do this, the interview is not going to go well. I know several interviews where that was the factor while they weren't hired. They were going to hire the person. Then in the interview, they say, oh, but you also know this in RQI. No, I really don't know much about that. And then people told me, well, this person was great. Why wasn't that person hired? Well, they weren't really, I don't think if they were that good. They weren't really sure. They didn't project the impression that they were good. So be confident. This is very important, and I want to mention it when we consider the role of gender dynamics here. When I'm teaching, you know what I notice a lot? In general, males are very likely to want to answer questions whether they're wrong or right. Typically, let's say, even if they're wrong, I found many cases where they're wrong, but it's blatantly wrong, and they say it, no problem. And it so happens that people who are not male do the opposite. They tend to know the answer. Many women in my classrooms are really good, know the answers to things they don't offer them. Because, I think the socialization that we have is very different, and we're not really socialized the same way. Men are socialized in a way that is, you need to show off. You need to be confident, no matter what. Whereas women are socialized as in, well, you don't need to disturb. So, and actually people are going to judge you if you do it wrong, so let's not. You need to overcome that. Sadly, it's tougher. This is a tougher thing that you have if you're not a man, right? In academia, outside, or whatever. Confidence versus skill will affect you. You need to display confidence. You need to be sure of yourself. You need to make sure that your confidence, I would recommend, doesn't go above your skill, but also doesn't go below your skill. Okay? Match your confidence with your skill, as if you were fighting lions. Back in our days when we were tribal. We're still tribal, But I think it's a residue of those times. And finally, and that's how am I gonna end? I'm gonna tell you to be ambitious. Like, don't think that you are not gonna get things as applied. Let people tell you that you're not gonna get them. They will, and that's okay. And they will tell you that you're not gonna know. Sorry, you're great, but we have so many applicants that we're great. That's the typical answer you would get. It doesn't matter. Let them do it. Don't do it yourself. Apply for things that are good. That's why I'm saying fellowship versus being hired by a group. And finally, the last thing that I want to say is that RQI is extremely diverse in topics. Take advantage of that. People in quantum gravity struggle to be hired. People in high energy physics may struggle to be hired. The reason is that they're very specialized. The nice thing about RQI is that it covers, when people tells us, what are the main lines of RQI? Say, okay, do you have a couple days? Then I'll tell you, because RQI is extremely diverse. There are people working on extremely different, people we've been calling, they're different. Are they the same field? Just yesterday, I was talking with a colleague of mine, and I was mentioning what groups work in RQI, and that person said, oh, that's RQI? People don't know what RQI is. And when they figure out what it is and what you have and what you've done, they're like, wow, okay, I'm doing quantum optics, but I'm really worried about short-time stuff, and this person knows relativity. Cool, I'm going to hire this person. Oh, I do relativity and so on, but I really want to do experiments. So this person actually is closer to what this Marcus Astelmeyer and people in Vienna are doing. I'm going to hire this person. Make use of this. When you sell yourself in RQI, don't talk about the particular thing you've done when in an interview you're asked, like, what do you do? What is your field? What have you been doing? No. I've been computing the second order correction to, no. Oh, I'm working in RQI. It's a field that encompasses, general relativity, quantum field theory, quantum optics, and experiments. And they're like, sorry, what? How? And then you tell them the story and you explain the field. Okay? Anyway, that's pretty much. I'm sorry I was running out of time. Those are some messages that I wanted to tell you. Ideally, I would love to discuss more. I don't think there's going to be much time, but during lunch, I'm very happy to discuss. You have people here that are extremely knowledgeable about this career prospect. We have Rob here. Rob is probably the expert in Waterloo, the person that knows the most about it. Use us. Use us, okay? And when you talk to us, be also aware of our biases. You're talking to survivors of academia. That is not the most common outcome if you're in grad school, okay? So keep all your options open, talk to people, play your strengths. All the advice that I gave you for academia works also outside academia. Above all, the confidence versus skill issue. And I think that's pretty much it. I don't know. If there's time for questions, I'm happy to answer them. Sounds good.
Nice, very good talk. My question, I know it makes sense, but it's more shorter. I would like to hear your opinion on that. Do you have any intuition about what might happen in the future? Do you think that the academia market might crash in a sense that it's going to collapse and then we're going to have a burst of positions?
Well, let's go to the Lagrange. No, not really. The academia market is going to crash. Okay, let me tell you a couple of things, right? I don't think it's going to crash. That's to begin with. What I don't think it's going to be doing anytime soon is expand. You see, there's an exponential law involved here. The 3% thing comes because it's an exponential law. We can assume that the number of academics is not going to eventually overcome the population of Earth. So what we know for sure is that not everybody that do PhDs are going to get into academic positions. The number of PhDs is increasing. One thing that I didn't have time to show you is how the age of first tenure position has been increasing in time. All the way from the 60s to nowadays. It's crazy how fast. Is the number of PhD students have been increasing crazy. There are many, many, many people doing PhDs these days. So while that is something that may tell you, oh, it's kind of a bubble, there's too many positions, the number of positions at the top relative are not growing. So I think the academia has been like this for a long time. It's not going to crash. The reason nowadays, the big change that happened from the 50s to now is that now postdocs exist. And postdocs are mainly the workhorse of academia. We have a lot of, let's say, less paid temporary people that do the good science, and maybe people get burnt out, but people typically do at least 2 postdocs on average before they start getting burnt out and leave academia. So no, I don't think, if the question if it's going to crash and there's going to be a lot of open positions, I don't think so. It is true that the age of professorship is going up, so I guess at some point it's going to be close to retirement, and maybe that's the crash that you're looking at. We're far from it. So now the average age for first tenure position is, I don't know if I should say it because I don't want to discourage people too much, but it's past 40 and past 42 and past 43. But you see, I think that academia, if you ask me, should change the model, the way that we're doing it. Create more research positions that are indefinite without being leaders of group. Right now it's structured that if you want a permanent position, you need to be a group leader and have students and teach and so on. We should probably create, this is my opinion, positions that are not postdocs, that are permanent positions, that you can hire people after a PhD and then let them do a postdoc, go around the world, and then get them hired back when they're back, right? Things like those. But if you ask me if it's going to collapse, are there going to be a lot of openings suddenly? I don't think so. I don't know what that would be based on. The trends don't suggest that. It will become more difficult perhaps to get an academic position from PhD. Yes, that's the trend. That's the trend. But the number of academic positions at the top is constant with the population for a long time. So. Okay, this is a problem. This is certainly something that happens, right? People tend to value, we see it already in peer review. We see it already when we submit papers, depending on who the referee is, right? How close to the field they're going to value it differently. Of course, people, when we put together committees, they try to have a very varied and diverse committee. But that is true in a way that funds and where funds go are decided by what's trendy and what the people who are being in the committee think is trendy. That is for sure. There are some fellowships that are outside that. There are fellowships that look very little to how cool your field is, and look very much to how much potential you show in what you present. So while it's true that that happens, it's also true that there exist fellowships that are not like that. I don't know. For example, Marie Curie, they have extremely diverse in Europe. Here, Banting Fellowship in Canada. The fellowships that they have in the big universities like Caltech, Harvard, Princeton, those are like that. So yeah, it is an issue. Endogamy in academia is an issue. We all like what we do, and therefore we tend to value more positively what we do than what somebody else is doing. But you shouldn't, there's another challenge, but you shouldn't let that stop you, right? I don't know if there was a question, just a comment, because Cisco knows well. That's why he says, yeah.
Thank you very much.
Thank you. Thank you. María, no sé si las pilas están gastadas o...
So our next speaker is Matheus Hrabowec Zambianco. He's a student of Achim and a PhD student of Achim and Eduardo, and he's going to talk about duality between amplitude and derivative coupled particle detectors. The floor is yours.
Okay.
Oh, sorry, I can't pin it.
Thank you so much for introduction, Jose. Good morning, everyone. Thank you so much for being here today. So today I'll be addressing a duality between two families of particle detector models. Here's what I planned today. So the talk is based in this paper that I published this year with Thales. The outline will be as follows. First, we're gonna give a quick overview about a topic that maybe you are not familiar with, or maybe you are having some dreams with, particle detector models. Then we are gonna consider instance where we have the particles coupling to the amplitude of a quantum field, instance where we have the particle coupling with the derivative of the field, and then we are gonna see how we can get a duality between those two models. Finally, some comments on how this duality translates for cases where we can study entanglement harvesting, and the concluding remarks after that. So, particle detectors, what they are. Essentially, we are talking about models where we have a finite dimensional quantum system that is interacting with a quantum field. Here we have infinitely many degrees of freedom, complicated, but here we are at home, we are safe, we know how to deal with those systems. So we couple them, we can apply local operations here, like measurements, for instance, and hopefully we can learn something interesting about the field. For instance, using such kind of models, we can implement quantum information protocols and quantum field theories. We can quantify entanglement present in quantum fields. We can even establish outstanding results like entanglement harvesting, where you have two particles that, even though they are space-like separated, they can become entangled because they are interacting with the field. There's also the phenomena of quantum energy teleportation. It has been known for a while that we can teleport states of quantum systems, but now using such kind of models, it can also be shown that we can teleport energy over long distance in a time which is way shorter than the time that, let's say, the typical dispersion of energy to travel from a place to another. And last but not least, such kind of models can also be used to probe the geometry and the topology of the space-time. So the simplest model is the so-called Unruh-DeWitt model, where we have simply a scalar quantum field coupled to a qubit. But don't be foolish by its simplicity. Despite its simplicity, it's a very, I would say, it's the solid block where we build our intuition about mostly of particle detector models, and it essentially captures all the essential features of how an atom can interact with the light in the absence of angular momentum. So the setup for the model is as follows. We have a field in a n+1 dimensional space-time, and this is a scalar field. Here I'm asking that this field satisfies the Klein-Gordon equation that might be coupled to the curvature, the scalar, the Ricci scalar of the space-time. So we have the field, and we have the qubit, which is simply a two-level quantum system, a quantum system that can have two possible energy levels. Here I'm employing the notation G for the ground state. Then we have the excited states, and those levels are separated by a fixed energy gap, omega. And how do we set up the interaction? How we can put this qubit to interact with the quantum field? So we have simply this type of interaction. Here I'm giving the expression of the Hamiltonian density that's going to define the interaction. So I couple the field with this operator here of the qubit. This is an operator that acts on the Hilbert space of the qubit. Here I'm defining the ladder operators, the operator that takes the excited and lowers to the ground, and the operator that takes the ground and raises up to the excited state. And in order to address more general models, it's usual in the literature to consider a space-time metering function, which is to say physically that we are saying that our interaction is going to be localized on space-time. And the essential, now talking about physics. So we have this model, we have the interaction, what we can learn from it. So the usual setup, we can start the field on both the field and the detectors are initialized on its respective ground states, meaning that the field is in the vacuum, there's nothing there, but you know that nothing can be complicated in quantum field theory. And the qubit starts on its ground state. Then we evolve it according to the interaction that I described in the previous slide. And after that, remember, we have the field infinitely many degrees of freedom. It's complicated. We don't like that mathematically. So we trace out, we ignore the degrees of freedom of the field. And then we get this object here, the reduced density matrix that can allow me to predict statistics on measurements that I might perform on the detector. In particular, there is this celebrated result where is the matrix? Oh, I believe there was some porting issue here to Windows for Mac, but trust me, there was supposed to be a matrix here. Probably you know this by heart. It's a good exercise. Try to imagine which matrix is here. So, but essentially, we have, to lean the order on the coupling constant, you can show that to have a matrix, essentially a 2x2 matrix, where the probability that the detector gets excited, you'll be given by the square of this number here. So we have this integral here, which relates the Whiteman function with the space-time smearing of the detector. And then by squaring this term, you get the probability that the detector can be excited. So pay attention here, what we learn here. Even though the detector started in its ground state and there was nothing there, the field was in the vacuum, due to the vacuum fluctuations of the field, the detector can become excited. So that's the message here. Okay, so here we saw a simple model where we have a detector coupled to the amplitude of a field. Of course, in the literature, you can consider, people have been considered many other models with more complex quantum systems, more complex fields in the sense it can be a complex quantum field, it can be a spinor, a fermionic field, but one other model that I would like to call attention to is a model where we couple our detector to the derivative of the same field we considered before. And by derivative, you can imagine that I'm taking the derivative with respect to the proper time of the detector. Remember, the detector is in space-time, following a trajectory, so I can define derivatives with respect to its proper time, for instance. And this kind of model is particularly interesting because in literature, people use it to avoid some infrared divergence that can appear in 1+1 spacetimes, or even more, in the work of those gentlemen here, they have shown that if you have a derivative, a model, where you couple the detector with the derivative of the field, you can use this model in a lower dimension spacetime to mimic a model where you have an amplitude coupling in a higher dimensional spacetime. Okay? So, mathematically speaking, what we have now, mathematically speaking, what I'm saying by changing the model is exactly this. Instead of coupling the qubit with the amplitude of the field, we are going to couple it to the derivative of the field, right? Here we need to be careful just to redefine what we mean by redefine our quantities. Here I'm going to take both coupling constants going to remain the same. But here, since we are changing the units here, we are going to redefine things in a sense that now this mirroring function in this new model is going to have one last dimension of energy. And also here, again, since we are not sure just to keep generality here, we are going to also allow that in this new model, the qubit might have an energy gap which is time dependent. All right? So now I ask you the main question of this work. When we change, we start with a model where we couple the detector to the amplitude of the field. And now we move for a model where we couple to the derivative of the field. What's the change in physics? Mathematically, the change in physics will be represented by how this term here changed. Because remember, if we take the square of this term, it's going to give us the probability that our detectors are going to become excited due to the interaction with the field. The idea here is that we can employ some mathematical trick in the sense that notes that we can pull out time derivatives here, and essentially, to make a long story short, you can apply integration by parts here as to try to relate this term here with the original term we had before. So now I'm going to impose that the physics is the same. I'm going to say, okay, I wanted the same physics on those two models. So what's the condition that my detector, described by this mirroring, needs to satisfy? Okay, mathematically we have this condition. It's a nice looking equation, but it doesn't tell us that much. We need to learn something else. So as good physicists, what we should do? We should make additional assumptions. So I'm going to make 3 assumptions in order to simplify this expression. I'm going to assume that the space-time volume around the trajectory of the detector is constant. I'm going to assume that this mirroring can be split into 2 terms, a switching function, a function that controls, that turns on and off my interaction, and a shape function that describes the shape of my detector in its rest frame. I'm going to also assume that both detectors have, for both models, they have the same shape and the same couplings. So under those assumptions, we are able to relate the switchings between those 2 models. So don't lose track. 3 minutes? Oh, time is relative. So don't lose track here. Here we have imposed that the physics is the same on those 2 models, and then we got this relation between the switchings, right? Now I ask you, can we go further? Yes, we can make yet another assumption, and we can obtain a very nice relation that essentially is the core of our work. So, if you consider the limit where the energy gap is infinite, is very large, it can be shown that the two models, the linear coupling one and the derivative coupling, are going to yield the same physics provided we essentially rescale this. So what's the lesson here? If I start with a model, an amplitude coupling model with this switching, and then you have a model with derivative coupling, but you use this switching, then they're going to have the same results. And then you say, cool, but you are assuming that omega needs to be infinite, right? So this mathematically is okay, but physically doesn't make that much sense. So the question we should ask ourselves now is that, okay, is there any value, any feasible value of omega that can make this duality to approximately hold? It turns out that yes. For our friend here, this friend that appeared maybe 3 or 2 times today, for a Gaussian switching, which is very physical, it's used in literature, it can be shown that if you pick values of the energy gap that are as physical as 5 times the time scale of the interaction, you have the chi tilde, the general switching for the other model is going to respect the rescaling. And if we have the rescaling behavior, we can be sure that the linear coupling model and the derivative coupling model yield the same physics, right? Just to finish, just a quick comment here. If you work with non-smooth switchings like this one here, you need to pay a high price. You see some inflation here that you need to pay on the energy gap. And before finishing, I would just like to quick mention that this result that we just presented, it also carries out perfectly for the case we have 2 detectors, meaning that it has also an impact on entanglement harvesting, right? I don't have that much time here. I'm going to leave just as a material that you can check maybe on the paper. So here, believe me, this result is also valid when we are in the context of entanglement harvesting, okay? Maybe I'm a little bit over time. Okay. I'm going to stop here, maybe to take 1 or 2 questions. Thank you so much for your attention.
But the derivative coupling is used to make it an inverse polynomial. Is the duality still true there? And if so, how does it work?
Yes, in this case, it would still be true because the theorem that we have here, it only assumes that the switching needs to be well behaved in the sense that it needs to vanish. It needs to vanish at the boundaries, right? And it needs to be a function that you can, you ask that both the switching and the derivative of the switching they can be integrable over the line, and they vanish in the limit where you have time going in the infinite or.
What would happen to the log divergence of the lightning function? But maybe we can discuss it privately.
The log divergence, yes.
Rob, the log is still the integral of 1 over d, right? So basically, the same relationship will still apply in exactly the same way. The only thing that happens in the case that you have some sort of, you need to introduce some IR regulator or something is, once you fix that regulator, once you have your Weightman function with that, then the result is valid. That's the only thing.
You have to fix the regulator.
Yes.
Following the same question as well. So in the very case where the one thing that, if you just don't use a regulator, and the probability of transition is divergent for the case of the regular coupling, the amplitude coupling, certainly analogy doesn't carry, right? Because the one that you, in that case, no regulator, probability of transition is divergent with the amplitude coupling. Probability of transition is not divergent for the derivative coupling, no matter what substitutions you make of things that are finite, you're not going to correct for that. So I'm still skeptical, same as Rob, or at least puzzled, that it would work for a regulator that's very close to zero, if you want, right? I mean, definitely at zero, it doesn't work.
You are saying a regulator that, in the case of the amplitude coupling, is going to give like a divergent amplitude infinite, and like a Gaussian switching.
I'm repeating the point that Rob made, just making it very explicit that it's actually infinite in the amplitude case, and with the substitution that you make without a regulator, it's not infinite. And then if you do it for a small regulator, very small, it's going to be huge. In fact, could break even perturbation theory depending where you are. I don't see how a finite correction can correct for a finite map like that doesn't involve any singularities can correct for that. It's basically what Rob said. It's just making it explicit that it's actually infinite if you don't have a regulator in the amplitude.
Yeah, maybe in this case because mathematically we are only safe in the limit of infinite energy gaps, which is not physical. But we do have instances where this is physical, but maybe in this case of 1 + 1, this would only be valid in the non-physical but mathematical limit. I'm not entirely sure, but I would say that.
It'd be nice to check it.
Yes. We can discuss that.
If I prime the moment 12, 1 is going to save in this case. I'm pretty sure.
You can do that. Please let's stay Matheus.
Yeah. Okay. Thank you, Jose. Okay.
Take it out.
Okay.
Okay, so our next speaker is Bruno Torres, and he's a PhD student of Eduardo Martín-Martínez and Benny Yoshida. And he's gonna talk about particle detectors from path integrals of localized quantum fields. Bruno, the floor is yours.
Where's the clip? All right. Thank you, Jose, for the introduction. Thank you all for being here. It's a pleasure to be talking to you all today. So today I'm going to be talking about work that's fresh out of the oven. If you checked the archive on Thursday, you probably saw that. And it's basically a follow-up on work that I did also in collaboration with Thales, Jose, and Eduardo a few months back. So basically the motivation goes along these lines, right? This is a talk about particle detectors, which you've heard a lot about by now. These are our favorite way of talking about localized systems that can couple to a quantum field in a finite region of space-time. And like the typical example, the paradigmatic format that we use is we have some word line that describes the trajectory of the detector, and you have an interaction action that couples. I'm writing this in terms of an interaction action instead of a Hamiltonian because I'm going to be using path integral, so this will fit better with the framework. I'm going to have some integral over the space-time volume form of some space-time mirroring that dictates the location of the interaction between field and detector in space-time, some probe observable for the detector, some field observable, and a coupling constant that I keep for bookkeeping purposes and perturbation theory. Our most common example of particle detector is, as you've heard a lot by now, the Unruh-Dewey detector, which is a two-level system coupled to a scalar field. There are a few variants that we can also consider, such as a free particle in a box, which was the first example considered by Unruh, a harmonic oscillator detector, which is the one that is going to be most relevant for what I'm going to be discussing today, among many others. And since I'm talking about particle detectors, I have to say that they are a very useful tool for several aspects of relativistic quantum information, such as a measurement framework for quantum field theory, that can be made consistent with the requirements of locality and relativistic causality, an operationally motivated characterization approach to entanglements in quantum field theory, and a framework for extracting features of space-time geometry and topologies in QFTs, possibly in curved spacetimes. And I'm not making justice probably to many papers that could be cited in this case, but I couldn't fit them all here, so I had to decide on a few. So now, it is a generic feature of most examples that we use that the detector's internal dynamics is approximated as non-relativistic, which is fine for most applications because the paradigmatic example is something like an atom that can be, to a very good approximation, be treated like a non-relativistic Schrodinger equation that determines some wave functions for an electron under the effect of a nucleus. But in the more fundamental sense, if the detector is not point-like, if it's smeared, the non-relativistic description of the internal dynamics of the detector may lead to issues with relativistic features of the theory more fundamentally, such as microcausality and covariance. And the easiest way to understand why that's the case is because you essentially will have a single observable of the detector coupling to multiple space-like separated points at a given value of the detector's proper time. This has raised a lot of interest in measurement schemes and general models for probes in quantum field theory that are fully based on a relativistic description of the probe itself. And perhaps the most important or the most relevant example of that for my talk is going to be the Fuster-Varg framework, where the probes are given by relativistic QFTs, fully formulated in terms of algebraic quantum field theory. And they can be made exactly compatible with relativistic locality and causality as well. Now, the goal of the talk now is going to be basically to reconcile these 2 points of view in a way. So I'm going to describe a simple model of a localized probe in terms of a fully relativistic quantum field. This is going to basically mimic the first paper that I mentioned with Jose, Thales, and Eduardo. I'm going to show how to formulate the dynamics of probe and target field, where the target field here is the field that I'm trying to extract information from, via a path integral technique, more specifically the Schrödinger-Keldysh path integral. I'm going to show also how the theory can be reduced to a finite number of Unruh DeWitt-like detectors given by harmonic oscillator degrees of freedom that you can just obtain systematically by just tracing out part of the degrees of freedom of the probe. And that will essentially draw the connection between field theoretic and detector-based formulations of local probes in a somewhat systematic manner. Okay, so the toy example of this probe that is fully relativistic is what we have been calling localized quantum fields, which is the easiest example of something that satisfies the basic constraints of a local probe in RQI. That is also a quantum field. So basically the idea is you are going to take some quadratic field theory with an external potential that acts like a position-dependent mass term, let's say, just because I'm writing the total action of the probe as something like this, where now U is some external potential that can depend on spacetime. And I'm going to require basically two things. To make my life easier, I'm going to assume that a metric is static. If you're more relatively inclined, I would tell you that I'm assuming the existence of a time-like Killing vector field that's orthogonal to a family of Cauchy hypersurfaces. And I'm just writing the metric here in the coordinates that are naturally adapted to the Killing isometry. And I'm going to assume that the potential in those coordinates doesn't depend on time. So it is invariant under the flow of the time-like isometry. And it is confining. And the easiest way you could imagine that is if there's some finite region where the potential takes a minimum value. And then as you go further away from that region, the potential grows to infinity. Now, if I do that, then I can basically, at the level of the action, all admissible field configurations have to decay sufficiently far away in spatial infinity. So I can basically integrate by parts the spatial parts of the Lagrangian. And what I get is an operator that looks like this. And because I assume that the theory is stable, I'm basically guaranteed that this operator E squared that shows up here, that's purely spatial, satisfies the property that its eigenvalues are all positive, so I can write them as these manifestly positive definite quantities that I'm denoting by omega squared. And the set of eigenfunctions that I'm selecting here, which I can always take to be real, satisfy this orthogonality condition with this modified inner product that is chosen such that E squared is Hermitian now with respect to this inner product. Now I can just expand any field configuration at each time slice in terms of that basis. And with that, I just plug that into the action. And what I get is that the action becomes the simple decoupled sum of a discrete number of modes of the field, which are just each of them described by a simple harmonic oscillator Lagrangian. Now, the property of the potential means that each of those VNs, those mode functions, is localized around the minimum of the potential. And in that sense, I could say that each mode is localized. And the trajectory of the mode is essentially dictated by the location of where the potential is. OK, now I'm going to introduce the second piece of the puzzle. That is this path integral technique that I'm calling the Schwinger-Keldysh path integral. And I'm going to describe the basic elements of how the story goes so that we can all understand how my proof technique will work. So basically, the story goes like this. Take a system. For simplicity, I'm going to assume one bosonic degree of freedom that I'm denoting by Q here. Just for simplicity, the equations are going to be shorter if I write it like that. But I hope it will become evident how it generalizes to the case that we're actually interested in. And I'm assuming that it starts in some density, in some state described by an arbitrary density matrix rho. And I'm going to do the following. I'm going to define this operator here, which looks like the adjoint action of some unitary, except that now this unitary can be different from this one. And the way I'm defining this is by just time evolving. Like this is a time evolution operator according to the Hamiltonian of the system with a source term. And I see two different sources here. This is why this at the end will not just be a density operator. It's just a useful mathematical construct that you'll understand the significance of in the next slide. Now the next thing you do is you represent the initial state in the basis of position eigenstates. So this is just adding resolutions of the identity on both sides. And now you compute the trace of the final operator, also in the position basis. And the reason why you do that is because you want to make these matrix elements of time evolution operators in the position basis appear. If you do that, then you know that each of those terms can be represented as path integrals in the Feynman sense. So integrals over all configurations that start from a given position and end at another fixed position, with now the source term that you added in each of the Hamiltonians. And that quantity, that trace that I defined before, that included two sources now, can be written as something like this. And this is what we call the Schwinger-Keldysh path integral. It's basically an upgraded version of the Feynman path integral that is naturally adapted to evolve density matrices instead of computing transition amplitudes. So yeah, the reason why this is most relevant in this case is because typically we're going to be dealing with time-dependent scenarios, and we're mostly interested in computing directly expectation values. And for instance, once you have this, the Z, the Schwinger-Keldysh path integral, you can compute, for example, arbitrary expectation values just by the usual trick of taking partial derivatives or functional derivatives with respect to the sources. Now I just draw attention to the fact that those are now two independent currents or source terms, and these expectation values are not necessarily time ordered, and the state rho can be arbitrary. The Schwinger-Keldysh formalism has a long history in many-body physics and open quantum systems. I would also like to point out that it has been recently proposed as a central element in developing a field theory-based approach for local measurements in RQI. And for our purposes here, the reason why it's important is because it will provide a natural framework to see systematically how to obtain Unruh-Dewitt-like detectors from field theories. Okay. The idea is, at heart, very simple. Now you remember that we had a probe field that was a localized quantum field. You have some field that you want to probe, and you have the coupling between the two. We're just going to apply the same techniques that we had before. The field is going to be taken as just a free Klein-Gordon field. And the coupling will be the usual linear coupling between amplitudes of both fields. Using the mode decomposition of the probe field, then we already know that the action of the probe decouples as a sum of decoupled modes. And you can just rewrite the interaction term now as a sum also over those modes, where you can interpret the operator that each mode couples to as this smeared version of each field operator with a particular smearing that depends on the mode profile corresponding to that mode. Now, we also need to allow source terms generically to define the Schrödinger-Keldysh path integral. And we can just do that by adding the usual source term, as you always would. Now you can associate the source term for the probe field with a tower of source terms for each mode in the natural way. And now we're going to reduce the theory to a finite number of degrees of freedom. The way we're going to do that systematically is just we're going to assume that we only have access to a subset of degrees of freedom that I'm collecting by some set A here. So the index n that labels the modes that I'm interested in only ranges over a discrete set. And at the level of the path integral, we restrict the probe sources to only be non-zero for the modes that are included in that set. And the last assumption that I'm going to need is just that I'm going to take the initial input state that I had as this uncorrelated state between the field and the probe degrees of freedom that I have access to, and the vacuum state for the inaccessible modes. Now, this is just a calculation that you can do in full, because everything is Gaussian now, and you're just computing Gaussian integrals at the level of the inaccessible modes. And the resulting dynamics for the effective probe system, after you integrate out and trace out the inaccessible modes, is something that morally looks like this. I'm omitting a few other integrals here that don't make a difference for my argument, where this thing here should remind you precisely of the Schrödinger-Keldysh path integral for just a finite number of modes. And there is this effect of integrating out the inaccessible modes that can be solved in full and exactly. And the obvious thing that I should point out here is that this term is second order in the coupling, because you integrated, you did a bunch of Gaussian integrals, and then you ended up with something that was quadratic in the sources that were turned on with the mode. Now, the contributions to first order in the coupling are precisely what you would expect from just a finite number of Unruh-Dewitt-like harmonic oscillator detectors with this select choice of space-time smearings. And the corrections to the naive results are only going to be important at higher orders in perturbation theory. So at leading order, the dynamics is precisely reproduced by just your favorite finite number of Unruh-Dewitt-like detectors. Now, a few comments about this. I made a statement about the leading order behavior of the theory, but the calculation that I performed was exact, thanks to the fact that I assumed the theory to be quadratic and the initial state of the inaccessible modes to be the vacuum. So as long as that assumption is true, I basically solved the calculation exactly, and deviations from the naive Unruh-Dewitt model under those assumptions can be computed now systematically because you have the full Schrödinger-Keldysh path integral. The assumption about the states of the inaccessible modes being in the vacuum can also be relaxed, and the conclusion that the leading order behavior would still be reproduced by the Unruh-Dewitt model would still hold, as long as the first moments for the quadratures of the modes that were integrated out are 0. And from this point of view, the non-locality that I commented with regards to smeared particle detector models is very natural and very intuitive. It just comes from the fact that you restricted a field to a finite number of modes, and that is known to potentially lead to mild non-localities and violations of causality and the like. Now, I'm running out of time, and I'm getting to my conclusions. So the takeaway message is that we have drawn a connection between field theoretic and detector-based approaches to local probes and particle detectors in RQI. We have shown a systematic way to reduce or to deduce the effective dynamics of the probe field to any select finite number of modes using the Schrödinger-Keldysh path integral. We've shown that at the leading order, the result that you would have obtained by just pretending that you had a finite number of unruled DeWitt-like detectors coupled to the field in the usual unruled DeWitt coupling would lead to the same dynamics for arbitrary input states of the probes and the field. And you can compute the corrections between the two models systematically at higher orders because you know how to solve the Gaussian integral for the inaccessible modes. Now, a few comments on things that are interested to mention in relation to that. The fact that the unruled DeWitt behavior or the unruled DeWitt prediction for the probe fields at leading order is precisely matching the calculations that we do with particle detectors means that you can basically trust to leading order all the calculations that you have already done with harmonic oscillator particle detectors, and those turn into statements about modes of a localized quantum field. And in particular, you can do fully relativistic entanglement harvesting using local fields as the probes. And this is also a work in preparation that you should keep an eye on arXiv for next week. It should come out soon. And I should also say that this method, one of the reasons I like this method as well, is because it also draws a potential connection between particle detector models and effective field theory approaches to particle detectors in general. And things that I would like to think about include an effective field theory approach to other kinds of probe descriptions, maybe based on toy models for bound states of interacting QFTs, maybe. And maybe you could ask something about the normalization group of interactions between probes and fields, which seems a bit out of reach with what I know so far, but doesn't seem that out of reach technically, I think. And this is pretty much what I had. Thank you for the attention.
Is that intended to be a different explanation than like smearing of the detectors, or would you see those as being compatible? Like you're thinking about like introducing an ungrouped DeWitt detector as being a non-relativist, like in the original model, right? Of the non-locality being due to the smearing, and perhaps having like superluminal signaling possible in that finite region for having detectors, something like that.
Yeah, I think in the way that the formalism that I used works, those two are definitely linked in the sense that if you restrict to a finite number of degrees of freedom, but your spatial profile is still smeared, then you're definitely going to have some violation of causality. Because if you're probing the field in a spatially extended region, the only way, like at least the natural way for you to not violate causality would be if you had 1 degree of freedom at each space-time point. So that would require infinitely many degrees of freedom necessarily. So, yeah.
Okay, so our last speaker of the session is Boris Ragula. He's a master's student of Eduardo Martín-Martínez, and he's also working with Eric Snetter. He's gonna talk about dynamically obtaining localized quantum fields from free field theory. So, thank you, Boris.
Probably. There we go. Should be fine, right? That should be good. Yeah.
All right, thanks for the introduction, Jose. I know I'm the last speaker before lunch, so hopefully you can bear with me for just a little bit longer here. Like you mentioned, I'll be giving a presentation on some ongoing work that I have in collaboration with Bruno Torres and Eduardo Martín-Martínez on dynamically obtaining localized quantum fields from a free field theory. So the quick outline for this talk, I'll give a little bit of an introduction. I'll talk a little bit about the formalism for classical and quantum scalar fields, or localized classical and quantum scalar fields. I'll do a little discussion on most people's nightmare on numerical methods. I'll show some preliminary results that we've obtained so far, and then talk a little bit about where we want to go with this project, and then some conclusions. So as we all know, QFT has been a remarkably successful theory up to date. But one of the main questions that we ask when studying QFT is how can one probe these quantum fields? Now, we've had a number of talks so far that have shown that UDW detectors have been used as incredibly effective tools in studying a number of different quantum field theoretic phenomenon. Well, with UDW detectors, we all know that they're non-relativistic. And so a natural question arises in what if we want to generalize our detector to a field theoretic probe. And as we just saw from Bruno, one of the things we can do is we can utilize localized quantum fields as our probe. And so that's kind of what we want to do in this project in a little bit of a different light. And we want to connect this class of QFTs to things that can be constructed dynamically. And really, we aim to answer how can one dynamically create a localized QFT and some of the consequences that arise when we do this. So the model that we'll be using will be just a scalar field. And so we'll start by just analyzing the classical case. So we'll have a classical scalar field, which we know is described by the Klein-Gordon equation. We'll be working in 1 + 1 to simplify some of our calculations. And we'll assume that this field is massless. And we'll implement a time-dependent confining potential well given by this v of x and t term. And so the general solution will just be written as a sum over as a wave equation, essentially, where these phi k's represent mode solutions to the above equation. And we just leave it very general. And so what we might ask is, well, what's an example of such a confining potential? Well, the example we're currently working with is the sum of arctangent functions, which is a smooth mimic to the finite potential well with discontinuous walls. And we can kind of see that over time, this is what we're growing. This is kind of how our potential will be growing, where A kind of controls the height of this potential. The little l controls the width of the minima. So this kind of right here is the value of little l. And the script L is kind of the speed at which this will mimic the finite potential well. So it's kind of how fast we'll go from this minimum up to the maximum. And so what we kind of expect is that outside of the minima, we have a classically disallowed region. And so we would expect that over time, and as the potential is growing, that the initial profile, f of x, will become confined within that minima of the potential. And we'll also need some ways to visualize this. And so one of the ways we can do this, we'll be showing some of the energy density plots of the field. And then as some sanity checks, we'll also be looking at kind of how the energy changes over time with the addition of this dynamically growing potential. So having looked at the classical case, we'll move on to the quantum case, where we quantize the scalar field from the previous section just using a canonical quantization, where we'll promote the coefficients of the wave equation that we saw earlier to creation and annihilation operators. And these creation and annihilation operators will satisfy the canonical commutation relations. And our quantum field will then satisfy this equation of motion that you see here. Now, this is an operator-valued equation living in a Hilbert space, which can kind of become a bit cumbersome to solve for numerically. And so we can kind of work around this by instead evolving the two-point correlator or Whiteman function of the field. Now, in our case, this will contain all of the necessary information about the field because we're starting in the ground state for a free field theory. And we also get the added benefit when evolving the two-point correlator that it satisfies the same equation of motion in both of its arguments. And so if we've created a numerical method to solve for the wave equation, we expect that applying this method to both arguments of the Whiteman function will yield good results for the evolution. So we do make a few assumptions for the numerical purposes. The first is we assume that the field will start in a cavity whose width L is significantly larger than the width of the potentials minima, in which case we're still effectively modeling an initially free field theory. And the other thing that we do is we'll regularize the two-point correlator to remove vacuum divergences by just smearing each of the arguments by some Gaussian function whose width will be roughly on the scale of the discretization that we use to solve the PDE equation of motion. So with that in mind, how are we going to go about actually doing this? Well, first off, all of the simulations that you'll see have been done in Julia, and they do ask for the recognition. And we start doing this by discretizing the spatial and temporal domains. So if we have a cavity of width L, we'll denote the grid points for the width L by these xi, and we'll evolve it for some time t, and we'll discretize that by points denoted ti. And we'll define the grid spacings as the distance between any two adjacent grid points in both x and in t. And we adopt a notation where our approximate solution will be written by this phi super n lower I, and it's approximately equal to the exact solution of the field at the point xi and tn on our grid. And just to kind of keep some consistency between what we'll be writing down, we define v super n lower I to just be the value of the potential at the point xi and tn. So we'll also need a way to talk about derivatives on this grid. So how will we talk about the derivatives? We'll use second order finite differencing operators that most of us have probably seen somewhere in an undergrad course. And those expressions are given here, where we just do a second order finite differencing in time and in space. And we adopt this formalism to the PDE system written in full here. So in our case, we prescribe some initial field profile f of x. We assume that our field has an initial momentum of 0, and that we will use Dirichlet boundary conditions at the edges of the cavity that we've implemented. When we do adopt this formalism, we see a discretized version of this PDE, which contains all of the information we'll need to actually set up and evolve all of our simulations. What this equation allows you to do is you can solve for the phi n+1 time step, and all you need to do is save any information you have about the two previous time steps, which we can see we'll need some time step just before, and we'll need the one initially before that as well. Using this, we can then evolve the PDE starting at a time of 0 all the way up until we decide that we don't want to wait anymore. And it's easy to show that under some certain restrictions for the value of delta t squared, this numerical method is stable. It doesn't start to gain spurious oscillations anywhere. The solutions are nice and smooth, and they stay nice and smooth if that's how they start. And we also define the solution convergence order using this equation here. And this is a necessary check to ensure that no numerical error has been pushed through the simulation, and that if there is any numerical error, we can assume that higher and higher grid spacings will force this away, and we can feel confident in what we're looking at when we do get any results out of our simulations. Now, all this notation means is if we define a grid spacing delta xc, we'll solve the PDE, and then we'll half the grid spacing and call this delta xm. We'll solve the PDE again. We'll half delta xm. We get a delta xf. Solve it one more time. And then we plot the ratio of these differences, and we do expect to see that at some point we do get a stabilization, and we can say that any numerical error will converge away. And what we find is that the method that we're using is indeed convergent, even in the presence of this time-dependent potential. And so we do have a solid confidence that what we're working with is working and not giving any extra error in our solutions. So with that, we kind of extend this method to the two-point correlator, and we discretize now both of its arguments. So we discretize x and x prime, and we denote these points in a very, very similar fashion to what we did earlier. The grid spacings will be defined as they were in the previous section, and we'll just take delta x and delta x prime to be equal, delta t and delta t prime to be equal. And we again approximate the two-point correlator using the same notation. The only difference here is that we now pick up this m and j term to account for the primed arguments of the two-point correlator. And now you might ask, well, how, if you have two time components, how are you going to actually evolve this in a similar fashion to what you did earlier? And the idea goes as this. You can fix a point. Let's pick x prime and t prime. So we're fixing the points in the second argument here. And then we'll evolve just the first arguments of the function using the same kind of wave equation evolution that we saw from the previous section, where in this case, we keep m and j fixed, and we evolve just the n+1 time steps in terms of the n and n-1 time steps. And this is just kind of an example of what it would look like. You would, in principle, have to fix at some point the xi and tn values and evolve in the primed coordinates as well. But just to kind of give you an idea of how this would work. Now, using this, we do have some nice preliminary results. And so for the classical case, I could show an example here where we start with this initially delocalized field profile within the cavity. It's just the sum of the first 5 modes of the cavity. And what we see is that this initially delocalized field profile over time, as the potential grows, becomes confined within the minima described by that little L, which in our case is, again, just about 1/2. It's the same potential I showed you in the earlier slides. And we see that it almost looks as though the boundary conditions are now set at the minus, in this case, 0.5 and 0.5 values. And so we can actually see that our field has been localized within the minima of this potential. Now, what we can also do is, if this isn't fun enough to watch, and you like something a little bit more solid, we can look at the energy density of this system. And what we see is that in this plot, it's very clear that you have an initial delocalization across the cavity. And over time, as this potential grows, you start to see that the energy density becomes centered kind of within the middle of the minima of the potential. And as one more sanity check, we can plot the energy as a function of time, where we've just integrated over the spatial domain at every time step. And we see that, as expected, the energy does grow as the potential grows, and actually stabilizes, and we get no additional energy and no loss of energy if we turn the potential off, which I've done here at a time step of about t equals 10 light crossing times for the cavity. And we do see that we don't gain or lose any energy in the system after that potential has stabilized. We also have an initial test for the two-point correlator, in this case without the presence of a potential, just to ensure that we're kind of seeing expected results. And so on the left here is the initial condition where we've smeared the two-point correlator for the large cavity. And we can see over time kind of how this system evolves. And we do see, in this case, to be very clear, the t prime variable is fixed at 0. And we simply evolve in the first coordinate of the unprimed variables. And what we do see is that the maxima of this function over time does stay along the lines of x equals x prime and x equals negative x prime, which is kind of to be expected. And so what do we want to do with this? Well, we aim to utilize these methods to check the validity of the adiabatic limit by looking at the ground state of this localized QFT and comparing it with the ground state of the vacuum for the delocalized theory. And we would expect that if this holds, if we start in the vacuum, as this localized QFT is created dynamically, then we don't expect to see any particle creation happening because, again, we've started in a vacuum, and if the adiabatic theorem holds, we shouldn't see anything over time. We also want to measure the mixedness between any two localized canonically conjugate variables, which we define here, and they are also written exactly in terms of the two-point correlator and the time derivatives of the field in that two-point correlator. And we can measure the mixedness over time using this expression here. Now, what these two canonically conjugate variables can define is an effective harmonic oscillator particle detector. And we could, in essence, use these localized quantum fields as particle detector models in this case. And if we're able to decrease the mixedness, then these particle detectors become even better tools for protocols such as entanglement harvesting, where the lower the mixedness, the more effective as a detector model these localized QFTs will become. And that is what we would expect, is that as we localize these, the mixedness should decrease between any of these two modes. So what we've shown now is we've shown a toy model for how we can dynamically create a localized scalar field. We have numerical methods to study the effects of these localizations. We've obtained preliminary results on what the evolution looks like and how to obtain the evolution of the two-point correlator. And we're now in the process of adapting these methods to test the adiabatic limits and mixedness of any two field modes. Thank you.
Thank you so much for the talk. I just have a couple of questions, if you don't mind. First, if you could go back to the log convergence plot, right? So if you're,
There it is.
yes. So if you're starting or you're using a second order finite difference scheme, right? It seems that the order of the plot goes from first to second. If you could like.
Yeah, so initially it does look as though it starts, first order, and we do eventually arrive at a second order convergence. The reason for this is when we discretize the temporal domain like we've done, the initial increase in the potential is much larger than starting with no potential, and so it does introduce a slight error in the way the solution evolves. However, what we can see though is that as that potential gets bigger, the changes become much smaller on the discretization. And so this does eventually converge to second order. And it still gives you the confidence that any of the numerical error that existed here over time will get pushed out and dampened out by the existence of the potential having grown to a large enough value.
Numerically calculate Weinberg functions in this way. Have you, when you're performing the finite difference schemes, trying to calculate this, have you run into any issues dealing with like coincidence limits or?
Yes, so initially that's kind of why we are, as first steps and first tests for this project, that's why we've kind of done this regularization. I believe I showed, yeah, it was just a little earlier. It's kind of why we do that regularization right here. Is because this will, in this case, if you evaluate this integral, you can remove the divergences at the coincidence limit and get nice finite values everywhere, in which case you can now substitute this in as a well-defined initial condition for the PDE system, and you don't have to deal with the numerical problems of coincidence limit divergences.
Thank you so much. Yeah, I think it's quite interesting. I'm just trying to understand a little bit more about what you're doing. So you've got this potential that's got a bowl and flat outside the bowl, and then it grows with time, correct?
Yes.
Now, does that stabilize eventually with time, or does it just indefinitely grow?
Yes. So what we in the I think I showed it a second later.
I saw it linear in T.
Yes, yes. So the potential does grow linearly in T. We do stop growing the potential after a point. So in the cases of some of the simulations you saw earlier, the potential will grow up to a time of about 10 light crossing times, and then it stays at that value. So it grows for a bit, and then we... Yes, yes. Yes, that's it. If we did keep growing it, you would expect to see the energy continue to get higher. We do stop it at some point, and that's kind of, we would stop it at that point and say, okay, this would be the localized field that you can now use as a particle detector.
So one of the things, obvious applications of this is in a cosmological setting. Have you tried to thought about this?
We actually, Bruno and I actually just talked about this a couple days ago, that there could be some nice applications in cosmological settings. We haven't explored any of them yet, but I would be very willing to look into them in the future.
Quick comments about things that have been said. This regularization method has been used by Marcus House, Waterloo. People have developed methods like this, the blurring of the coincidence limit in Wayman. It's well studied. People know that it works well and what the limits are. It's a very good method for this kind of thing. It actually has been used in cosmology. They have developed it to some scenarios. I haven't talked yet with Bruno and Boris about this, but it has been. I think that one thing that is that you said, but I want to emphasize too, like here, what the intention, or at least this particular, although this can be used for many things, but still the intention is, okay, what happens when you build a particle detector from a quantum theory? So you have a theory that is completely localized, and then I want to grow a potential so that I have a bound system, a system that is localized in space. So I want to build a particle detector. There was some work saying, well, the mixedness, because of Ricker's theorem, mixedness is going to kill you if you do that. Here we can show that if you do it adiabatically and slow enough, you can actually build a particle detector out of a full relativistic QFT dynamically. It's like, creating a potential, putting together your atom if you want. That's what I'm doing. But indeed, these tools are, and Boris is becoming the expert of this, so these tools are expected to have many applications. And yeah, the regularization in particular of the Wayman is not new, it's not ours in a way. Even though it's been used in the past and it's been used in many scenarios, including dynamical spacetime.
So Sister's asking, could you please reiterate the relationship between the localization and mixedness? Does your characterization imply purity constraints for traveling wave speeds?
Sorry, can you repeat that? I think I missed some of what you said there.
Could you please reiterate the relationship between delocalization and mixedness? That's the first one. And then it also says, does your characterization imply purity constraints for traveling wave states?
To answer the first part of the question, as you localize this field, again, because you have that disallowed region outside of the minima of the potential, you would kind of expect that there becomes less and less correlation between the state of the field within that potential and with the state of the field outside of the potential. And so you would likely see a decrease in the mixedness between these different regions of the field. Can you repeat the second question again? Because I apparently seem to have a hard time remembering it.
Does your characterization imply purity constraints for traveling wave states?
Periodic constraints. Not that I can see now. I don't anticipate that this would imply any periodic constraints on the waves themselves. I would imagine that given the fact that we're using particular boundary conditions, that the same boundary conditions would be satisfied on the edges of the potential, or approximately the same boundary conditions satisfied on the edges of the potentials as well.
Let's thank Boris.
Now we finally have for lunch, so for this day, I would also like to remind the in-person attendees and the viewers in YouTube that the event here has been funded by the AMAT department. And yeah, now we can head for lunch. Thank you very much. This is the end of the second session.
So good afternoon, everyone. We are starting the third session of the RQI Circuit here in Waterloo. And we were going to start with Professor Eduardo Martín-Martínez, who's going to talk about perspectives into RQI research, quantum energy teleportation, from theory to experiments and space-time engineering.
Thank you. All right, thank you. First of all, thank you for the invitation and the efforts in organizing. Want to give a shout out to Thales Rick Perche, who's organizing this at the international level, and the local organizing committee. This is María Rosa, Carol, Everett, and Jose, if I'm not, hopefully not forgetting anybody. Thank you very much for this. I'll try to be, I have to tell you one thing. This talk ends with a picture of Boris and Thales. So if I don't get there because of time, you just look at them, and it's going to be very similar to the last slide, okay? All right, what am I going to talk about? So it was difficult to select a topic that could be entertaining for everybody, for a wider audience. So I decided to go with this, which is nice. I'm going to talk about quantum energy teleportation. Quantum energy teleportation is a protocol of relativistic quantum information that does something that we couldn't do without taking advantage of quantum information, and in particular, when you apply to quantum fields, a fully relativistic one. That has been recently proven experimentally. So I'm going to talk about what quantum energy teleportation is, how it connects a little bit with thermodynamics, with quantum thermodynamics. We're going to talk about the basic example of it. We're going to talk about the experiment, or at least the ones that I've been part of, how the experiment that was done here at the IQC, that the first proof, experimental proof of quantum energy teleportation. And we're going to talk about the consequences in field theory and future avenues of research that we're pursuing related to that. All right. So by the way, this is written by, oh, man, there's no pointer here, huh? Here, oh yeah, there we go, my bad. This actually was written by him. I asked him how to say quantum vacuum in Japanese, and he wrote it for me, which is nice. So that's why I have it there. Masahiro Hota, if you didn't recognize him, by the way. Professor Masahiro Hota from Tohoku University in Japan. All right, so basically this is the outline of the talk. Let's proceed because time is limited. Let's talk a little bit about thermodynamics. Now, passivity of thermal states. What's passivity? Passivity basically is the property, passivity, you want to call it unitary passivity, is that, well, no matter what operation I do in some system, imagine the system is in a thermal state, a passive state in general, I do some unitary operation, there's no way that I'm going to be able to extract energy from the system. So the cost of the operation, if you compute on average the expectation of the Hamiltonian after the operation minus the expectation of the Hamiltonian before the operation, you're going to get that it's going to have a positive energy cost. Okay? There's no possibility of extracting energy from it. As you know from your thermodynamics, basic thermodynamics course, if you have a thermal background, there's no way to extract work from a thermal state. Agreed? All right. Now, of course, we know that there are ways to extract energy from a thermal state of some finite temperature, right? Typically, you can couple it to something that is in a thermal state of lower temperature, for example, right? So if you couple your system to something that has lower temperature, then there's going to be an energy flow from the hotter system to the colder one. Agreed? Heat flows are established from hot to cold. There's the second law of thermodynamics. So we know that it's possible to do it. And indeed, if you relax the unitarity and then you say, well, if I do a CP-TP map on the system, so in general, I could extract energy. However, something that I want to note is that the thermal flow, right, when energy flows from a hot system to a cold one, you need time evolution. So you see, time evolution is not local in the sense that it's not a local operation on one side. I'm doing a contact here, thermal contact. I touch the corner, and energy comes to me, but it's certainly through time evolution. That involves, you need time evolution and you need energy flows. Internally, if you want energy flows, you need to involve everything in the system that you're talking about. It's certainly not only the site that you're touching, right? So in particular, one question you can ask is, can you actually extract energy purely locally in the sense of, I want to touch B, and I don't want anybody else to participate in the operation. The operation I'm going to do is only a local channel on B without letting time evolution do anything. Okay? I want to do something very fast, let's say. So the idea is this. I have a hand here. That's Masahiro's hand, for example. And it's colder than the system. The system is at some temperature T, and the hand is at thermal state of some temperature T hand. Okay? And then we do this. Imagine this is the sun, for example, and we touch the sun. The question is, will the hand get burnt or not? Would you get burned if you touch the sun? Well, the answer is not in general, no. In fact, the hand could get cooler. If you touch something, if you touch something very hot very fast, you don't necessarily get burnt. You need some time to establish thermal contact. In fact, the study of these properties is talking about these properties called strong local passivity. Strong, as in not only unitaries, but any CPTP map. Local, it only involves one element of the system, one subsystem of the lattice that we're considering. And passive, meaning that no possibility of energy extraction. So these two papers here prove a sufficient condition for strong local passivity, which basically, if the ground state of the system, think of the system, contains max rank entanglement. Max rank entanglement means that it spans, the mixed composition of the ground state spans the whole Hilbert space. Then there always exists a temperature T star strictly larger than 0, for which, for the temperature T below T star, it is not possible to extract work from the system. So a system whose ground state has max rank entanglement, there always have some range of temperatures for which it is strong local passive. You cannot, by touching very fast, you are not going to be able to extract energy. In fact, you're going to have to pay energy if you do it. Make sense? That was, I have to say, we did work on this as well. We found that's a sufficient condition. We found the sufficient and necessary conditions for this. And just a shout out, this is in this paper by these people. I like to say it to show the people. Álvaro Martín Alhambra, currently in Madrid, in Autónoma. Giorgio Stilaris, I actually don't know where he is now. Nayeli Rodriguez Briones, that's in California. And here we have Jen Sikora, who was at Perimeter at the time, a postdoc at PI. So if you want to check that, that is with some interesting examples, that's sufficient and necessary conditions for strong local passivity. Anyway, so the idea is that you can have a strong point contact interaction, something that lasts for very, very short times. And because the system, keep in mind, is T below T star, meaning that for T equals 0, if you have a T star different from 0, and any temperature below that, the state is strong local passive, that means that the vacuum is indeed strong local passive as well, the vacuum, the ground state, right? So yeah, it could happen that you can touch the sun and you can become colder if you touch it very fast. Disclaimer, I haven't computed T star for the sun, right? So I don't know. It may be or maybe not. But what I mean, you can definitely touch something hot with something cold and not get burnt and actually lose energy by doing it. Okay, that's the core of the strong local passivity result. All right. Now, can you break strong local passivity? Well, it turns out that, of course, with local operations of any kind, you can't. That's the definition of strong local passive. But if I add CC, if I add classical communication to the mix, I am able to break strong local passivity. For example, I'm not going to show you the calculations because of time, but because imagine that you have a system of two interact. This is the minimal QET. You have a system of two interacting qubits. You make a measurement on the first system. The measurement costs you some energy, EA. Then you send the information. You generate a bit of classical information that you send over to B. Then B does some unitary operation that depends on the outcome, and that can be made so that the energy cost of that operation is negative. And that is, of course, in time sufficiently fast so that energy doesn't travel from A to B. There's no traveling of energy from A to B through their coupling. It's just the fact that you unlocked the access to the, if you want, the local, let's call it vacuum energy density, and you can extract it by noise. Okay, that's an intuition idea. Let's just show you the intuition. The intuition idea is, well, if you randomly measure, think of a vacuum or the ground state of something, it's a quantum system. If I randomly measure, sometimes it's going to cost me energy. Sometimes I'm going to have to give energy because the thing is fluctuating. So sometimes I'm going to, imagine it's rotating like this, the fluctuations are moving, sometimes you push it in the right direction, sometimes you don't. The fluctuations can be positive or negative. However, if somebody measures something else that is entangled with your system, that something else, by measuring the thing that's correlated like that, you're going to learn about the fluctuations, then you know exactly in what way to push to always extract energy from it. Suddenly those fluctuations are no longer considered like random fluctuations in both directions. You know how to take advantage of them to actually measure in the right direction and extract energy. It's a bit of intuition behind the protocol of quantum energy teleportation. The protocol of quantum teleportation goes like this. So we start from the system ground state, for example. It doesn't have to be the ground state. It just needs to be some state with some temperature below some threshold. Then Alice carries out a projective measurement on her qubit. The result is announced to Bob. Bob carries out a unitary operation that depends on the result, and Bob can extract energy. Don't have the time to show you the math. It's very simple math. I actually cover it in my PSI course in quantum information or relativistic quantum information. So if you want to go to PIRSA and see it, it's a very simple example to see the minimal model. All right. So that's quantum linear teleportation as its simplest, if you want. Now, let's see an application of quantum teleportation by introducing a new idea in quantum thermodynamics that's called algorithmic cooling. Algorithmic cooling is precisely this thing. You have a fridge with an H-bar somewhere, right? And the idea is this. OK, I have the following problem. I want to cool down these qubits, maybe this one in particular that is hot. And I have access to a thermal bath. And the thermal bath is colder than the system. Nice. But my problem is I actually want to cool down this qubit below the temperature of the thermal bath I have access to. So then it's a little bit, it's a little bit different than the fridges that you're used to, right? With the fridges that you're used to, you can only cool to the cold source of the fridge. You cannot cool below that. But, doing some quantum manipulations, you can actually cool below. The idea is you can cool below the temperature of the thermal bath. How? Well, you do something called entropy compression. This entropy compression is a non-local operation on these qubits. What this entropy compression does is, here, I don't know why. You start from these guys, and then I do a unitary operation involving all these guys. And the unitary operation, what it does, it puts all the entropy, or as much as possible of the entropy, on one side. That way I have something that is hot in here, and something that is colder in here. Then what I do afterwards, I replace this qubit, or I put this qubit in touch with the thermal bath. When I do it, that qubit becomes as cold as the thermal bath. Agreed? Then what do I do now? Well, I do another entropy compression, and I put all the entropy in here. I dump some of the entropy to the thermal bath, and by rearranging the entropy in the system, by doing non-local operations, I put as much as possible of the entropy here, in a way that this guy actually ends up being colder than the thermal bath. So using manipulations of quantum information, if you want, using the fact that you can apply a non-local unitary here, you can reshuffle the entropy of the system to put all of it in a partial state of the system that you reset with the thermal bath. That way you can cheat. The more of this you have, the more you can cheat it, and you can cool partially part of your system colder than the thermal bath that you're in contact with. There are several techniques of algorithmic cooling that were developed, but almost all of them are designed to apply to systems that don't interact. So you cool down the system. If the system actually in mind that I want to cool, in mind that these qubits that I had here were interacting with each other. So if they're interacting with each other, this becomes trickier. And the reason is that, well, I'm going to have to go through the whole animation. It becomes trickier because if they are interacting, if you cool down the whole system, you have a problem. The subsystems are going to be mixed because the ground state may be entangled, and in general, it's going to be entangled. So if you want to cool one of the qubits, and you say, OK, let's put everything to absolute zero. Well, no, you don't get a pure state anymore in the individual qubits because, the ground state contains entanglement. So they're going to be mixed states, the individual ones. Then, OK, fine, we can break the entanglement through, make it interact with that environment. Sure, but that implies actually including mixedness in your system. It's going to be bad for you. OK, we can apply local operations on the subsystem. If the system is local passive, as most, by the way, those conditions are fulfilled. For example, in a lattice of qubits or harmonic oscillators with first neighbors interaction, T star is definitely much larger than 0, which is saying nothing. It's much larger than that small amount. It's not small. That's what I mean. So yeah, indeed, if you apply local operation of the system and the system is local passive, you're not going to be able to extract energy from just interacting with the system. So you're going to actually put more energy into it that goes against cooling it down. So interacting systems, cooling down interacting systems with the usual algorithmic cooling algorithms is not ideal. It's not optimal. They're not designed for that. So we had this idea of applying quantum energy teleportation to do algorithmic cooling, because quantum energy teleportation precisely uses the correlations to extract energy from a part of the system. So that worked out. I did that with Ray Laflamme, Nayeli, Achim Kempf, that he will give a talk at the end of this session, and Ray Laflamme. And yeah, this is a bit of a comparison. Let me just show you the comparison with with a little bit of interaction. Now, of course, the more interaction here, you see that the more interaction you have, the higher the interaction K. This kappa here, which is what K says here, this kappa here is the strength of the interaction. This is an interaction between qubits, right? The stronger the interaction, the more you can purify using QET. The less you should use the usual algorithm, and the more you should use QET. And in fact, you do a comparison here in a case with a coupling of 0.2, strong but not too strong. And you see that QET cooling, which is these two curves, destroys HVAC. If you apply the usual heat bath algorithmic cooling, the methods using QET are much better. So you can actually use this protocol for algorithmic cooling when the systems have interactions. Nice. So hopefully I convince you that quantum teleportation is cool. Now, it's kind of interesting, right? Because what I'm telling you is this. Why is it called quantum teleportation? People don't like this name. I have to give you this disclaimer. Some people don't like it, and people confuse it with quantum teleportation too, which is not the same at all. I'm telling you that you put some energy here in one system. You don't let the energy travel to B. But the energy that you put in here, you use it to measure. You measure something, and that costs you energy. Of course, if you're in the ground state, anything you do is going to cost you energy. So that costs you energy. The energy that you put in doesn't travel to B. Only the classical information of the outcome of the measurement travels to B. And armed with that information, I'm able to extract energy from the ground state locally. It still looks like the ground state locally. I'm not able to tell it's not the ground state locally, because whatever perturbation I made here by measuring has not propagated yet to where I am. Does that make sense? So something that looks like the vacuum. This is going to be important when we go QFT and cross spacetime. It's very important. Energy has not propagated from A to B. And yet B, looking like the local vacuum, like the local ground state, I still can extract energy from it. That's so incredible that the first paper that Masahiro sent about this was rejected, saying that it's crackpottery. It was not. But the idea sounds very similar to extracting 0-point energy. And that's why some alarms were triggered, let's say. The one way to actually see that this is the case, right, you just do an experiment and check if you can actually do that. And indeed, we did it. The experiment was done, again, there's a group of Ray Laflamme, there's Hemant, was a postdoc at the time with Ray Laflamme, was also a student of Ray. Nayeli, I didn't say, but Nayeli was a shared student between Ray, Achim, and I. One recommendation, if you ever become a professor at UW, don't ever do triple supervision. It's a bureaucratic nightmare because the system is prepared only for 2 supervisors. Anyway, so the experiment here was using a molecule they know well. In fact, you can tell that Ray has the molecule in his hand, or rather a representation of the molecule in his hands. So this is the molecule, transcrotonic acid. Details are not that important. The details that we implemented is that, well, here you can identify 3 qubits. We have an ancillary qubit, A and B. And the idea is that we're going to do an operation on A, the equivalent to a quantum measurement. The measurement is coupling the ancilla. Then we're going to decouple the ancilla. The nice thing about this is that we have full control in nuclear magnetic resonance. They have full control. They can engineer pulses that couple and decouple everything with each other, which is great. A and B are never coupled. They couple. There's some coupling always, of course, through the structure of the molecule, but the coupling is much weaker than the coupling between A and the ancilla and B and the ancilla. So the idea is we make a measurement. Instead of doing a classical measurement like a projective measurement, we do a quantum measurement. We let the ancilla interact with A, right? Then that causes some energy. And then what we do now is, without letting energy propagate from A to the ancilla and B to the ancilla, just the information, we apply a unitary operation on B based on measurements on the ancilla. So this is a scheme of the diagram of the circuit. That's the minimal QET. In any case, the nice thing is that if you do the calculation, the theoretical prediction is this red line of the amount of energy that you can teleport doing that. The dashed line is a simulation where they actually take into account the inefficiencies of the experiment that they have modeled really well. And as you can see, the experiment kind of fits. I always ask them, but the error bars don't fit. They don't care. So it's not that important. I don't care either, because the important thing is that the real experimental value is different from 0. So you are extracting energy. And the nice thing is that you can actually check if this was teleported or if the energy actually propagated, because you can still say, oh, come on, you put some energy in A and propagate it to B, right? No. The total duration of the experiment is 30.6 milliseconds. This is is the sum of the pulse duration, the duration of the pulse that prepares the interaction, and the duration of the different unitaries. And the energy propagation time is based on the coupling strength of this molecule. The time that it takes from let's say, 10% of the energy of A to travel to B is 1 second. And the whole experiment was 3.6 milliseconds. So certainly there hasn't been enough time for energy to propagate from A to B, and that's why this was regarded as the first experimental proof of quantum energy teleportation. All right, how much time do I have? 5? Poof, let's run. Here's an idea that came out of quantum energy teleportation. Can we use quantum energy teleportation to prepare exotic states of gravity? So the idea is doing something. This is with Nick Funai, who's here, was a PhD student of mine, now in Australia, in Melbourne, a postdoc, doing something like that. That's what I want to do. So I don't know how familiar, but I'm going to assume that there's some familiarity here with general relativity, but in particular, Einstein equations. General relativity is not reasonable, really, if you think about it. Put aside that general relativity predicts its own demise, right? But not only that, general relativity can produce monsters. There are some solutions to Einstein equations that are not that reasonable, right? Solutions that contain, I don't know, closed time-like curves, wormholes, a lot of things that are not really that reasonable. Warp drives, that kind of stuff. Well, there's a series of assumptions about matter, the matter that sources gravity, that make your life much easier, or make the theory much nicer, in the sense that they forbid to different degrees the existence of these exotic solutions that have closed time, like time machines, or warp drives, or wormholes, these kinds of things. In particular, those are the energy conditions. The energy conditions, you have modos by the weak energy condition. There's no such thing as negative energy density. Strong energy condition, gravity is only attractive, dominant. Energy must not flow faster than light. Null energy condition, positive null flow or stress energy density. Well, this is a difficult one to get intuition on for the time we have. But they seem reasonable enough. But keep in mind, general relativity does not guarantee any of this. These are things that you can impose on top of general relativity, because it so happens that the matter that people knew kind of satisfies that always. So people were okay with that, with imposing that. Now, of course, you violate, you get exotic solutions, we know that. But it turns out that, at least on average, quantum fields can violate the energy conditions. So the moment you do quantum field theory, the energy conditions no longer apply. They can violate all of them. I'm showing you an example of violating the weak energy condition, but they also violate the null one. That means that they violate every single one of them. You can prepare states of matter that in principle violate those conditions, so it's not guaranteed that if you use QFT, you're not going to be able to prepare, at least on average, those exotic spacetimes. So what's the back reaction of spacetime to that? That's not known. So let's turn to quantum energy teleportation. Masahiro did something. When Masahiro first proposed quantum energy teleportation, he did it in the context of QFT. Masahiro did the following: 1 + 1 dimensional quantum field, and I'm going to couple Alice only to left-moving modes of the field. You can do that in 1 + 1D massless field. The modes they couple, the right and left movers, so he did that. Couple Alice to left movers, and then what happens is that Alice makes a measurement by coupling something to the field. This is the energy density, okay? So after doing the measurement, the energy is dumped in here. Then the energy propagates to the left, because again, Alice is not coupled to right movers. Alice is coupled to left movers only, right? So the energy never reaches Bob, but then Bob gets some information of the outcome of Alice's measurements, and then Bob can actually do energy extraction, here, without having received any energy from Alice. Now here we're not going to focus on the energy extraction. We're going to focus on the fact that the energy density is that of the vacuum initially. The energy density, except for 0-point terms that are renormalized away, compatible with flat spacetime, right? It's 0. The energy density is 0 at Bob's position. So if Bob can extract energy from the position where Bob is, the energy density around Bob will be negative. Here's violation of the weak energy condition. So the idea is, and I'm not going to go through the details, what we did, instead of that, we did the case where, of course, you don't couple only to left movers, and you don't do it in 1 + 1D. If you don't, of course, both the information travel at the same speed as the perturbation. So if you really want to create negative energy density, you need to compensate for the positive energy density. I'm not going to bore you with the details. I'm going to tell you that we actually found a protocol based on quantum optics using atoms, like clouds of atoms, that couple to the field, and then you transmit the information from those atoms to another set of atoms where you actually can do it. In principle, at least in a sci-fi experiment, you can address these atoms with lasers at the positions they are. They are realistic probes. And the idea is, this is an example in 1 + 1D. You can tell that the calculation in the end gives you some terms that can be negative. In particular, this term, the expectation value of the original state on sigma y can be negative or positive. So these terms are the energy that it costs you to couple to the field, but then there's some contribution to the stress energy density that can be of negative sign, and at some points this can overcome these terms. So I can show you, this is the one, we did it in 3+1, not going to show you, but this is the 1+1 dimensional example. So Alice couples to the field. When Alice couples to the field, this is the energy density distribution on the field. After it couples, then it evolves in time, and then at some point, it gets to the position where Bob is. Now Bob is going to couple to the field. After Bob couples to the field, notice the rescaling of the axis, right? Bob puts more energy into the field by coupling, right? But when you let things propagate away after Bob does the thing, you get this distribution of negative energy surrounded by positive energy, something like this. Now, of course, I'm not going to talk, there's some complication of doing it in 3+1D, not going to get into them. But the idea is that you can actually overcome it. You can actually approximate a cloud with some density of atoms of detectors by a model that is simpler, would allow us to do the math, and then some equivalence between LOCC and LOQC for the communication of the information. But the point being that these kind of protocols, when used, quantum energy teleportation, when optimized to generate optimal negative energy distributions, can violate the quantum interest conjecture and the quantum inequalities optimally, the same way that something like the extreme dynamical Casimir effect. And you can scale it, the total amount of negative energy is unbounded. What you need to do is increase the density of your detectors and increase the strength of the coupling. If you rescale the strength of the coupling and the density of the detectors, you can get arbitrarily negative energy densities with this. Of course, the pay-you price is that they're in a tighter region of space-time. Now, the one thing that I want to tell you to end, this is the last slide. As I promised, we end up with pictures of Boris and Rick and Eric's netter here. What we're trying to do now, so we prove already that you can use quantum energy teleportation to generate the stress energy densities associated with a warp drive, for example, at least the ones that you need in order to build a warp drive. You can, with a protocol that you can do in a lab, or a protocol that's experimentally tested. You can, in principle, use it to generate exotic distributions of matter. Now, the problem with this is that, well, I mean, you've done the whole protocol assuming a static, flat space-time scenario. If you really want to tell me that you can build a warp drive with this, by the way, I never said that, but if you really want to tell me that this is going to generate exotic solutions to Einstein equations, what you need to do it is turn on gravity while you do it and see how the metric reacts when you try to do this. You're trying to bother the metric so much, annoy the metric so much. Oh, are you going to give me that matter, very exotic matter that general relativity doesn't really want to deal with because it's going to look very bad in the eyes of physicists? But then we force it using quantum energy teleportation. How is gravity going to react? Is gravity going to allow you to do it, or is it going to dissipate the whole thing and it's not going to work? What kind of metric backgrounds can you generate dynamically with these kinds of protocols? So this is a question that we're in the first steps, because it's not very non-trivial to do, as you can imagine, with Thales and Eric Snetter, who's the person, one of the most important people who developed what is called the Einstein Toolkit, a set of tools to work with numerical relativity. And then Boris, who's the local expert in numerical calculus. That is the person that when we discuss the physics and we say, oh man, but that's going to be so tough. And I say, well, that's Boris' problem. That's the kind of thing. So we hope to actually give you a very nice movie next time where we see the metric change as we try to force general relativity to produce exotic space-time with exotic matter generated through quantum energy teleportation. And thank you for the patience. That's it. Thank you.
All right. Thank you, Eduardo. Questions?
I have a question regarding the order of magnitude of the energies that were measured in those experiments. I mean, I know that the energies involved there are very tiny for us to think about using that to create space-time with a wormhole or warp drive or isotonic space-time that would allow time travel. But what would it take for us to try to make an experiment where we can enlarge the amount of energy extracted and therefore enlarge the amount of negative energy produced?
Yeah. So the nice thing, so again, first of all, I'm not saying if we prove mathematically in a computer that we can have exotic spacetime, doesn't mean that we can do it in the lab now. This would be The difference is that it changes from a science problem to an engineering problem. Engineering for 500 years in the future, maybe, but engineering nevertheless. The laws of physics we know can allow it, right? The interesting thing is this, the scaling. So we looked at how much we can force the machine with the protocol. If we have ability to couple stronger and to increase the density of the probes that we're using for that, in principle, you can scale the negative energy as much as you want. So the total amount of negative energy can be scaled to the ability to engineer the couple. So there's no limit to the amount of negative. Of course, it comes at the price that there's more positive energy around it as well. But the total amount of negative energy, as you can tell, scales. Jesus. I don't know why there's no pointer, but scales is the second to last mathematics line there. Scales with sigma to the n. And sigma, as you see, is how much you increase the coupling strength and how much tighter you make the distribution of atoms. So you make the distribution, the scaling is tighter distribution of atoms, tighter cloud, more dense cloud, and then the coupling strength increased by sigma to the n-2 for 1 and to the n half. N-2 divided by 2 and n halves. And then doing that, you scale the total negative energy by a sigma to the n. So in principle, you can do as much as you want. Again, it's an engineering problem maybe for 600 years in the future or whatever. But at least you would be showing that within the limits of semi-classical gravity, this would be the prediction. You may have exotic spacetimes, if that's the case. Thank you. You could have asked me if I'm in semi-classical gravity. Am I using coherent states or what? How is this semi-classical gravity valid? But the answer is that yes, we're using coherent states. So. Oh, no, I don't want. It's a clamp, yeah, I don't know.
Oh, actually, I need to introduce you. Do you want to test the pointer as well? Is it working? No. Okay, it is. All right. So for the next speaker of the session, we have Lana Bozanic, and she's going to talk about correlation harvesting between particles in uniform motion. Okay, sure. All right, hello everyone. Like it was said, I'm Lana Bozanic, and today I'll be talking to you guys about a recent work that I did with Manar Naim, Kensuke Gallic Yoshimura, and Robert Mann about correlation harvesting between particles in uniform motion. So first, we'll begin with some background. So there were two main motivations for this project, the first being the Unruh effect, which I'm sure many of you are familiar with, which is a remarkable prediction of quantum field theory that tells us if we have a linearly accelerated detector, it will experience a thermal bath with temperature Tu that is proportional to its acceleration. Now, because of its significance, there has been a lot of interest in trying to experimentally prove this effect. But there are a lot of hurdles in trying to do so, one of which is that you would need an acceleration of about 10 to the 20 meters per second squared to even see 1 Kelvin of temperature. Now, because of the experimental implementation interest, there has been a lot of different studies done in the different trajectories that we can sort of see the Unruh effect or Unruh-like effects in the lab. So, for example, the circular trajectory is of interest because we can manifest it in the finite lab setting. So many studies have been done about the Unruh effect and similar effects for different types of trajectories. And then we also have the correlation harvesting protocol, which is less understood compared to the Unruh effect. And this essentially states that two detectors will become entangled through local interactions with a quantum field. Now, what we wanted to do in our paper was to investigate this correlation harvesting protocol for the most general type of uniformly accelerated detector. And what we found out is that there are 5 different classes of motion, or 5 different classes of uniform motion that were characterized by Litaw. So we want to understand correlation harvesting just in this more general way, because there have been studies done for linear trajectories and circular trajectories, but we want to understand it from the most general perspective. So I know the next few talks are also about the correlation harvesting protocol, so I'll briefly review it here. So like I said, this essentially states that if we have 2 UDWs in a quantum field and each have energy gap omega between their ground and excited states, and they are traveling along certain trajectories in the field, after a certain time, they can become entangled with one another. And so the Hamiltonian that describes each individual detector is governed by this equation, where lambda is the coupling strength, chi is the switching function, which controls the duration of the interaction between the field and the detector. Mu is the monopole moment. And then finally, this last term is just the value of the quantum field along the trajectories that we send our detectors on. And then with this, we can define the total interaction Hamiltonian for the entire system. And then if we start with some initial state, we chose everything in its ground states, so detectors A and B in their ground states, and the field in its ground state. We can use perturbative analysis with the Hamiltonians described in the previous slide to evolve our state. And then finally, when we trace out the field, we're left with this density matrix that describes the joint state of detectors A and B. And this density matrix gives us all the information we need to understand the correlations harvested from the field. So these LAA and LBB terms are our transition probabilities, so the probabilities that our detectors will transition from the ground to excited state. And then this LAB term is used in quantifying the total amount of quantum mutual information. And then this last off-diagonal M term is used in quantifying the total non-local correlations that are extracted from the field. So in all of these terms, this Whiteman function, or the 2-point correlation function, comes up. And in 3+1 Minkowski spacetime, which we consider, it assumes this form. And throughout our entire study, we use Gaussian switching to control the duration of the interaction between the field and the detectors. So using all the information from this density matrix that results from the protocol, we then have a measure of the extracted correlations. So for now, we'll just talk about the entanglement. And for our study, we used concurrence as the measure of entanglement, which is defined using the M term from the density matrix, which once again quantifies the non-local correlations and the transition probabilities. So now that we've reviewed the correlation harvesting protocol, we can talk about the different types of uniformly accelerated trajectories. So Litaw found that there are actually 5 different classes of uniform motion that can be characterized just using 3 different parameters. So the first parameter is the curvature, which describes the direction of the acceleration. And then we have 2 torsions, B and nu. And these can intuitively be understood as a sort of rotation in axes perpendicular to the direction of the acceleration. So these 5 classes of motion are linear motion, which is characterized by non-zero acceleration, but the 2 torsions being equal to 0 with this trajectory. Then we have catenary motion, where A is greater than B and the second torsion is equal to 0. Then we have cusp motion, where A and B are equal and the second torsion is equal to 0. And then the last case where the second torsion is equal to 0 is the circular case, where A is less than B. And then finally, the most general type of uniform motion is where we also consider the second torsion being non-zero. But we don't consider this case in our paper, so I'll skip over this section here. So like I mentioned, this in 3+1 Minkowski spacetime, the Wightman function assumes this form, and obviously it's very heavily dependent on the trajectory we take. And what we found is for all the different classes of motion where the second torsion is equal to 0, we can find a stationary and a non-stationary version of this Wightman function. And so what we mean by stationary is when the Wightman function is time translationally invariant, so it only depends on delta tau. And non-stationary is when we also have this delta plus tau dependence. And so for all of the 4 uniform motions that we consider, we can find this stationary and non-stationary scenario. So for example, in the linear case, the stationary motion is when the 2 detectors are traveling parallel to each other, but a non-stationary configuration is when they are following each other. And then, like I said, for every single type of motion, we can find this stationary and non-stationary scenario. So that was catenary, then we also have cusped, and finally circular. So just, So the interesting part about all of this is that although all these trajectories seem very different at first, we can actually categorize them with a master Wightman function. So for the stationary scenario, we have this one Wightman function that can use to be described all those different motions: linear, cusped, catenary, and circular. Similarly, for the non-stationary scenarios, we have this one master Wightman function that only differs by this term here, which has this delta plus tau dependence that makes it non-stationary. And what you'll notice in these 2 generalized or master Wightman functions is that they have this new parameter b bar right there that is just defined as b over a. So for linear, it's 0. For catenary, it's between 0 and 1. For cusped, it's 1. And for circular, it's greater than 1. So these Wightman functions, if we just tune the value of b bar, we get the different types of motion, which is really interesting. We have just these 2 Wightman functions describing the stationary and non-stationary scenarios for all these different types of motion. So now we can understand the correlation harvesting protocol as a function of the different types of motion. So just to summarize all this background, so we start off with the correlation harvesting protocol, and this yields these 2 terms to calculate. Then we have these master Wightman functions that describe the Wightman functions for all these different types of trajectories just by tuning the parameter b bar, which is b over a. And then finally, to measure the amount of entanglement extracted from the field, we use this correlation measure of concurrence. So now we can move on to the main results of our paper. So the first thing we did is we tried to understand how acceleration affected concurrence. And what we'll see in both the stationary and the non-stationary scenarios, the concurrence will die with finite a. Another thing that we noticed is that for b bar less than or equal to 1, so for the linear, catenary, and cusped motions, the stationary case will always harvest more entanglement than the non-stationary case, but this pattern doesn't hold anymore for the circular regime. And although it's a bit hard to see on these figures, and it'll be more clear in the next, the non-stationary scenario actually oscillates around the stationary scenario. And then when we plot the concurrence as a function of b bar, this is a bit more apparent. And so when we analyze how the harvested entanglement as a function of the trajectory, or b bar, we see that as b bar grows larger, we can harvest more and more entanglement. And once again, we see this pattern that the non-stationary case will always harvest less than the stationary case if we're in the linear, catenary, or cusped regimes. And we see this oscillation behavior in the circular regime when b bar is greater than 1. And this oscillation is a lot more pronounced for larger accelerations as well. Now, another thing that we were interested in understanding was when can we actually harvest entanglement? So in the case of inertial detectors, it's known that no matter how far you separate your detectors, you can always find an energy gap omega so that you can still harvest entanglement. So we wanted to see if this was still the case, if our detectors were uniformly accelerated, and unfortunately this is not the case. So this figure shows the regions to the left of all the curves in this figure shows the regions where we can still harvest entanglement as a function of the separation distance and omega. So we see that we can't always harvest entanglement. We can't always find parameters that allow us to harvest entanglement. In particular, one implication of this is that we can't always, or we can't at all, causally separate our detectors and still harvest entanglement. And so that leads us to our next question of if we're ever genuinely harvesting entanglement. So in the entanglement harvesting protocol, we can break up our Whiteman function into two parts, an anti-commutator part and a commutator part. And these separate parts essentially tell us about how much entanglement is actually extracted from the field and how much entanglement comes from communication between the detectors. And so we know that if we causally separate our detectors, all the entanglement will always come from just the field. But if they are in causal contact, they can potentially still communicate, and entanglement can arise from this communication and not just the field. So yeah, this Whiteman function can get split up into its real and imaginary parts, or the Hadamard part, which we call the genuine harvesting, and the Pauli-Jordan part, which is entanglement from the communication. And then we can split up that M term, which quantifies our non-local correlations, and introduce concurrence quantifying both the genuine harvesting and the entanglement from communication. And what we ended up finding is that even though we can't causally separate our detectors, even though we can't causally separate our detectors, we can still tune our parameters so that the harvesting is genuine harvesting. So this figure shows the solid lines. The red is linear, the blue is circular, and the solid lines represent the genuine harvesting, and the dashed lines are the entanglement from communication. And so on this figure on the left, we can see that this region where the dashed lines are 0 and the solid lines are non-zero, that is genuine harvesting, even though our detectors are still in causal contact. So yeah, that is, oops, forgot to put that up there. But that is all I have for you guys today. I just wanted to end with a brief land acknowledgement. Much of the research conducted for this project took place on the traditional territory of the neutral Anishinaabe and the Haudenosaunee peoples, and I just want to say how thankful I am to get to work and do what I love on this land. Thank you.
Thanks, Lana. Does anyone have any questions?
Thank you for the presentation. My question is, if you compare I'm wondering if you have compared the fall off entanglement or faster accelerating observers, if you compare that to the temperatures you expect from the impact, and how those your plot compared to just simply a stationary observer in a thermal where it does consistent or if you're getting different effects here depending on your motion.
So that isn't something that we investigated. Could you repeat that a bit?
Just if you go back a couple slides to your to when you first presented your like concurrence versus acceleration. Yeah, here. You expect a graph that looks somewhat different if you look at just concurrence based on concurrence and temperature. So I wonder how that if you compare the acceleration and the temperature based on it, compare that to what you're seeing here. I'm wondering if it would be interesting if it would be
looking at similar effects, or if it's completely different?
So I guess for the linear case, you could do that because the temperature would then be proportional to the acceleration. But for the other types of motion, I'm not entirely sure.
Okay.
Yeah, sorry, I don't know if that's a very satisfying answer.
Yeah. As a follow-up, I'm not sure if it's something you know off the top of your head, but like looking at this scale
Here, can you convert this scale to a temperature to say what temperature field with, say, look at this current or the energy stream over the parameters you're looking at here translate to temperature?
I think you would have to like consider the different types of motion like individually if you wanted to understand it as a function of temperature as well, because that will change depending on the different trajectories, but it isn't something that we considered in this.
Thanks for the talk. In your thoughts of genuine harvesting versus just I'm wondering, you have this region here where you see the actual genuine harvesting is bigger than once it's bigger, right? You have solid line is larger than the dotted line. Does it stay larger than the dotted line even past L over sigma over 2? Or is there a point where it drops back down below the dotted line? It's just kind of hard to tell what's happening larger than
I mean, past that point, it's. Wait, sorry, could you repeat that?
Yeah, sorry, I'm just wondering, what happens past this point
like here?
Does the solid line stay larger than the dotted line?
I think they both go to 0. They both go to 0, yeah. Yeah.
Okay, another question?
Thanks for your presentation. You have like laws or compare the actual whole group with the single one?
Oh, no, we, just for this part, we separated them, but do you mean like plots similar to, oh, that's me going forward. No, we just for this part, we separated them.
Do you have any vision what happens? I mean, is this going to be larger or smaller?
I can't say for certain. I'm not entirely sure.
I just wondered.
Sorry about that.
Yes,
Do you want the PDF or the PowerPoint?
The PowerPoint.
Okay.
Do you want to test the pointer? Also test if. Do you want to test if it's the slides are pointing? Okay, perfect. Okay, for the next talk, we're going to have Ireneo Membrere, and he's going to talk about tripartite entanglement extraction from the black hole vacuum.
Yes, thank you. Hello, everyone. My name is Ireneo James Membrere, as stated, and I'm here to tell you about the first investigation of tripartite entanglement harvesting in the black hole vacuum. So this research was done in collaboration with Kensuke Gallic Yoshimura, Laura Henderson, and Robert Mann. 2 points in a quantum field are known to be entangled, and this entanglement depends on the space-time that the quantum field permeates. We can measure this using the entanglement harvesting protocol. So what this entails is multiple qubits locally interacting with a field, extracting correlations from the field, and becoming entangled. And so we measure the entanglement of these detectors as a proxy for the entanglement of the field itself. This is important to study because not only does it give us clues into fundamental physics problems, such as the origin of black hole entropy, but it also gets us one step closer to reconciling quantum mechanics and general relativity. A qubit is normally modeled by the UW detector. This is a two-level quantum system with a ground state and an excited state that models the light-matter interaction when angular momentum is conserved. Most of the research done so far has only looked at two detectors. For example, there was a study on two detectors in ADS. There was a study on two detectors in black hole spacetime, and they discovered the bipartite entanglement shadow. Basically, what this means is that when one of the detectors is too close to the event horizon, there's too much noise from the black hole, such as Hawking radiation, and this prevents the detectors from extracting any bipartite entanglement. And another study was rotating black holes amplifying entanglement. Comparatively little is known about multipartite entanglement. One exception would be a study done recently on 3 detectors in flat spacetime, and they discovered that you can harvest tripartite entanglement when bipartite entanglement is 0. So we asked the question, what happens to the entanglement shadow of a black hole when we introduce a third detector? We consider 3 static UDW detectors in a 2+1 dimensional BTZ black hole spacetime. The line element for this spacetime is given here. For the coordinates of the detectors, time, radius, and angle. L represents the ADS length, M represents the mass of the black hole, and the event horizon is given by the ADS length times the square root of the mass. We consider a quantum scalar field obeying this field equation, and so we can calculate the correlations of the field using the Whiteman function. Since BTZ is conformally equivalent to ADS, if we consider the black hole to be in thermal equilibrium with its exterior, then we can calculate the Whiteman function on BTZ as an image sum of Whiteman functions on ADS. The interaction between the detectors and the field is governed by this Hamiltonian here. Lambda represents the coupling strength. Chi represents the switching function, so it controls whether the interaction is on or off. Tau is a proper time. Sigma is the width of the switching function. We have our lowering and raising operators. And omega represents the energy gap between the ground state and the excited state of our detector. We initially start with the detectors in their ground state and the field in its vacuum state. And then we can use the time evolution operator to calculate the final state. But for a small lambda parameter, we can do a Dyson series expansion of the time evolution operator, truncate to a few terms, and calculate that final state explicitly. We trace out the field to get the final state of our 3-detector system in this basis, where the matrix elements P represents the transition probability of one of the detectors, C represents the local correlations between 2 detectors, and X represents the non-local correlations. To measure entanglement, we look at a couple things. The negativity of entanglement is defined using the trace norm on a reduced state partially transposed. This is equivalent to taking the negative eigenvalues and adding their magnitudes for this reduced state. In 2x2 systems, the negativity is positive if and only if the 2 systems are entangled. So the negativity of entanglement exactly quantifies bipartite entanglement. The pi tangle, defined here as a various sum of differences of squares for negativities, exactly quantifies tripartite entanglement, but only for pure states. In a more general case, we can only treat the pi tangle as a lower bound. So this means that a positive pi tangle means that we are genuinely extracting tripartite entanglement, but a pi tangle of 0 or a negative pi tangle means that the results are inconclusive. The first configuration we consider are the detectors in an equilateral triangle around the event horizon of the black hole. we use identical detectors, so the coupling strength, the switching function, and the energy gap are all set equal to each other for the detectors. This is for mathematical simplicity. And for the following parameters in a Gaussian switching function, here we plot the negativity between any two pairs of the detectors and the pi tangle as a function of the black hole mass and the distance from the horizon. Looking at the negativity, we see that as the detectors approach the horizon, the negativity goes down to 0. This is, again, the bipartite shadow that we talked about earlier that was discovered in one of the previous papers. Looking at the pi tangle, we see that the pi tangle is positive at larger masses and longer distances as compared to the negativity. This region where the pi tangle is positive and we have no bipartite entanglement is a case of GHZ type entanglement. For the triangle configuration, we also considered other parameters. Here in the plot, we considered the energy gap varying and the distance. And we again found a region where we can harvest genuine tripartite entanglement. We looked at the ADS length, which looked very similar to the density plot shown in the last slide. And we also calculated the pi tangle for different boundary conditions, such as von Neumann or transparent. And it was very qualitatively similar to what we already have shown in the slides. But for all cases of the triangle, the pi tangle is only positive in a very small region of the parameter space. So as far as we know, it's relatively difficult to harvest tripartite entanglement when your detectors are arranged in this configuration. The second configuration we considered were the detectors on a straight line with the center of the horizon. The distance between A, B, and BC is fixed and set to be equal. And all three detectors move as one unit closer or farther away from the horizon. Here we plot the pi tangle as a function of the distance from the horizon for varying energy gaps. And we see that when we make the energy gap large enough, then the entanglement shadow of the pi tangle completely disappears. So this means that when, for a large enough energy gap, A can get arbitrarily close to the horizon, and we were still able to harvest tripartite entanglement. This actually happens within the bipartite shadow, and we can see that explicitly. So in the bottom plot, we plot the various negativities for an energy gap of 0.01. And looking at the bipartite negativities, they're all 0 from about the horizon to 0.6. But the pi tangle is positive between 0.2 and 0.6. So this region between 0.2 and 0.6 sigma is where we can harvest this GHZ type entanglement. The pi tangle also asymptotes to a constant value as the distance gets to infinity. And this is expected because BTZ is asymptotically ADS. And in contrast to the triangle case, majority of the parameter space for the line yields a positive pi tangle. And so it's relatively easy to harvest tripartite entanglement when our detectors are arranged on a line. We consider the line again, but for larger detector spacings. So at a detector spacing of about 5 sigma, the detectors are nearly causally disconnected. Here we again plot the pi tangle as a function of the distance from the horizon. And what we see this time is that the pi tangle has a spike near the horizon larger than the asymptote. And this spike occurs within the bipartite shadow, as we see below, looking at the negativities again. The spike also occurs in the tripartite negativities. So where is this spike coming from? Here we plot the matrix elements, P, C, and X, versus the distance. And one is able to calculate the negativities as direct functions of these matrix elements, P, C, and X. So looking at any of the correlation elements, C or X, involving the detector A, we see that these elements have maxima near the horizon. And it's these maxima that are responsible for the spike in our tripartite negativities, and thus the spike in the pi tangle. We can also calculate the bipartite negativities as direct functions of P, C, and X. And NAB, NAC both have a negative PA term. Looking at the transition probability here, PA is extremely large near the horizon, driving these to 0, and the high transition probability of detector A is what's actually responsible for the bipartite shadow that we see. In summary, we looked at the tripartite entanglement harvesting protocol for 3 UDW detectors in a BTZ black hole spacetime. We looked at an equilateral triangle configuration where we found that we could harvest tripartite entanglement at larger masses and longer distances as compared to bipartite entanglement. We saw the bipartite shadow for the triangle case, and we also found that only a small region of the parameter space guaranteed us the ability to harvest tripartite entanglement for our triangle configuration. We also looked at a straight line configuration, and in this case we found for a detector separation of 1 sigma that we can drive the energy gap large enough in order to eliminate the entanglement shadow in our tripartite entanglement. We found that at larger detector separations of 5 sigma, there is a near horizon spike in the pi tangle, which comes from the pairwise correlations overcoming the noise near the event horizon. And we also found, in contrast to the triangle case, that the majority of the parameter space allows us to harvest entanglement in the line configuration. An interesting avenue for future research would be to classify the harvested entanglement into the categories of GHZ, W, biseparable, and fully separable states. Thank you for listening to my talk. If you want any more information, please see our publication.
Thanks, Ireneo. Does anyone have a question? Also, if no one has a question here, perhaps during the coffee break, I hope you stick around. Thanks again. Let's thank again Ireneo for the talk.
Thank you.
Do you want to test if it's working? Oh, yes. Do you want to test the pointer as well?
Thank you.
Yeah. So the last speaker of this session is Adam Teixidó-Bonfill, and he's going to talk about experimental entanglement harvesting, bridging the gap between theory and experiments.
Okay, thank you, Carol. Sorry. Okay, thank you. Okay. Yeah, think jacket. So, hello everyone. Today, as Carol was saying, I'm going to talk about how we can bring RQI a bit closer to experiments, so bring it into the lab. And one of the possible experiments would be doing entanglement harvesting. And so first, I want to acknowledge the collaborators in this project because it takes quite a bit. And first, there is my group is the theory group of Barry RQI with my supervisor, Eduardo Martín-Martínez. And then the group without these experiments would not be possible is the superconducting quantum devices group at IQC. And this is led by Adrian Lupascu and students of his. Elena Kornick, Lucas Hack, Noah Jansen, Shidai, 2 of which are here in the audience, and Lucas Hack and Noah Jansen up there. And also there is also other students from Adrian Lupascu that work on this in the past, and master students like Shihao Ji and Sean Ren. So first of all, well, today I'm going to go first on why we want to do these experiments, how can we use superconducting devices for this, and we also look into, in theory we have the Unruh-DeWitt model, we also have the experiment, the superconducting devices that can do the experiment, but we can have an intermediate step between these that can bridge the gap between these two
different scenarios, and then what would be the consequences of this intermediate model for an entanglement harvesting experiment. And we'll finish afterwards. Okay, so first, why do we want RQI experiments? Obviously, in RQI, we usually use theoretical tools, mainly the unruly width detector that appeared a lot today. There were great introductions about it before lunch, like Matheus and Bruno. And also, these unruly width detectors, we use them for a myriad of applications that also appeared today: entanglement harvesting, unruly radiation, or exploring black holes or curved spacetimes. These tools, we already can explore all these scenarios. So why would we want to have an experiment? Well, first, of course, to verify these predictions that RQI has, like actually perform them in the lab. And then, because experiments can bring us to places where theory cannot, like having regimes with strong coupling, where it's just non-perturbative, so we cannot do many calculations there. Sorry. So why why the superconducting circuit is one method of doing these experiments, and why are they useful? Well, first, they are very good technology. Superconducting circuits. This has been developed already in the 1999. The first qubit was done for quantum superconducting circuits. And since then, control over these qubits has improved a lot. And right now, there's a recent article even with qubits that can last for a coherence time of 1 millisecond, which is actually impressive. And also then, the fabrication of these devices is as chips, which is a widespread technique. And relatedly, the largest quantum computing currently is with superconducting circuits. And it's 433 qubits of IBM. So it's a powerful technology. And but being powerful is not enough. We also need characteristics that allow us to make RQI devices. And mainly what researchers here in IQC were able to do in Adrian Lupas's group was to, like last year, they put out this article in arXiv, which is long title, but basically it consists of a tunable coupler, so we can change the coupling between two-level systems, so a qubit, which we are very much used to use, and a waveguide, which is basically equivalent to a one-dimensional quantum field. And we can bring this qubit and one-dimensional quantum field from decoupled to strong coupling, so very strong coupling regime. This is what the superconducting devices team were able to do. And this interaction, we were able to turn it on and off very fast in the matter of nanoseconds. So this is actually great to do an experiment like entanglement harvesting, because we need, if we want to make the most impressive claim, we want to have space-like separated interactions that get two qubits entangled, even though they did not have time to interact between them. So very fast turning on and off of the interaction is needed. So here to have just an image of what is the actual device that they built in the lab. This would be only one detector, one particle detector. This is on the left, I think the pointer, oh yes. There's lots of elements of it, but there is mainly the qubit loop, so a two-level system, which is coupled to the transmission line, which here only appears a little bit, but on the right-hand side, you can see a zoom out. The transmission line is long, goes from one side to the other, and the other lines are control that allow you to change this intensity of the coupling between the transmission line and the qubit. So, yeah, and this was the image from their article. And so now, what is this circuit made of? Let's go start with the simplest element, which is the core of every superconducting circuit, which is the Josephson junction, which is surprisingly simple but very powerful. And it's basically superconducting, two superconducting bits, which are separated by a gap or an insulator. And what makes this special is that these two superconducting parts can couple to each other through tunneling. So charges, like Cooper pairs, can tunnel from one superconductor to the other. And this coupling allows for qubits and all the tunable coupling that we have, I have mentioned before. And now just to use this on the next slide, I will use this diagram to represent the Josephson junction. This is just a cross on a cable, a superconducting cable, and represents this here up there. So this, which is pretty much more complex, is the actual full device. This would be one particle detector. And we have to go step by step. We have here on top the waveguide. So this is the one-dimensional quantum field. And here at the bottom, we have what in the superconducting devices research is called a flux qubit. So here, this would work as our two-dimensional level system. And in between them, there is this tunable coupler. And all over it, there are the Josephson junctions from the previous slide. And so here, just with Josephson junctions, we cannot achieve any variable coupling. In order to be able to control this, there is another element in this picture, which is here this F beta and F epsilon, which are actually external magnetic fields that go through these loops here, through this loop of the bottom and loop on the top. And through this, they were able to change the coupling between this qubit and the waveguide. And in this matter of nanoseconds that I was saying before. OK, so all this circuit is certainly more complicated than a Hrabowec detector. The Hamiltonian of that circuit is, I did not include it here, but it's quite longer. So using that for a theory, it would be complicated. It's not good for analytic calculations, as the Hrabowec detector is. But it's what we actually need to get an accurate model of the experiment. So there's some work from the Adrian Lupascu group, like from Dai, which modeled the Hamiltonian of the system, and were able to extract the energy levels of the Hamiltonian through numerics. You need to do numerics. And they analyze the Hamiltonian. And then for each of these parameters that can be turned as a knob in the experiment, he can add the energy levels, the lowest ones, which is the ones we care about, and the coupling strength between these energy levels and the waveguide, which is what we also care about. OK, so these, when we get these outcomes of the code from this gives us several energy levels. But if we want to get something more simple, a simpler model, we can restrict ourselves to the two lowest energy levels of the superconducting detector. So we actually look into a qubit. And this is a valid approximation, just looking at the lowest energy levels when the interaction of the qubit, like the change in the coupling intensity, is low enough over time. And slow enough, I mean slow enough compared to the energy gap. And specifically, more importantly, to the energy gap of the higher energy levels. And also, another feature that comes out of this numerical diagonalization that I was saying before is that the gap between the energy levels depends on the intensity of the coupling. So this is just an expression for the coupling that we can change over time. And the gap of the detector actually has a constant term when it's uncoupled. But there is also a variation proportional to the intensity of how strongly coupled the qubit is to the waveguide. So this is a feature that we usually don't have in Hrabowec detectors, and we would like to include it. As we're looking here, which is these two features that I have described, or all the features, some features of the experimental model can be added to the Hrabowec detector so that we have a model that's closer to experiments, but still not the full Hamiltonian of the superconducting device. And this would be having this variable gap that I was just mentioning. And then the detector actually is considered point-like in the experiment because what dominates over the detector size is the cutoff of the field. The modes are attenuated when they are very high frequency, and this is actually the main contribution. And the last thing is that instead of coupling to the amplitude, that is the most common choice for Hrabowec detectors, it's coupled to the spatial derivative of the field. So here below is the summary of this as a Hamiltonian of the interaction. And we have the coupling constant. This chi of x is the switching, which is basically our dependence over time of the coupling. And a monopole moment, an operator on the qubit, and the derivative of the field at the point where the qubit is. And this is just to represent that the monopole moment now has a variable gap. So it has a more complicated expression that involves the integral. So this model now, why do we care about it? It's because I was saying before, this model is closer to experiments while still being amenable to analytic calculations, or at least easier numerical calculations, which is what we have to use. And we can look specifically at this new feature of the experiment of having a variable gap separately from all the complexities of the experiment involves. And so we can better understand what this new effect can have over performing experiments such as entanglement harvesting. This is what I'm going to show next. This model on entanglement harvesting, what can it tell us about an experiment? Is first just to have a setup of the entanglement harvesting is as has appeared before. We can have two detectors that interact in space-like separated regions, detector A and B. And even if this interaction is space-like, they can get entangled. But there is no current experimental realization of this. And that's what, in the future, we want to do with the experimental group here in IQC. And the model, the intermediate model that I was saying before, that has the variable gap, has the following effects that are here in these plots. Basically, if we consider these two detectors to have a Gaussian switching, which is, and the cutoff of the field to be very slow, so the mode's intensity decays very slowly with frequency. And we measure the negativity of the final state of the two qubits. And here I plot the log base 10 of it. And the warmer colors are higher negativity, this is lower negativity. And here is the usual scenario where we are used to. There's more harvesting. At the horizontal axis is the separation between qubits, and the vertical axis is the time that the interaction takes. And the longer the time interaction, the farther you can get entanglement from. But once you add the variation of the gap over time, in this case, we look at the gap that when the detector is fully coupled reduces by 20%. So it's a considerable, even not huge reduction, but already has an effect that can be seen in this plot. And basically, it's harder to get entanglement far away when there is a variation in the gap, but the entanglement is actually easier to get when you have your detectors close. And with this, I just want to finish and go a little bit over everything. The first, the development that the team at IQC were able to do of having a tunable coupler can allow us to, in the future, have RQI experiments in the lab and explore new regimes. And we can also get an intermediate model so that we can understand better experiments by adding the gap variation over time to the Hrabowec detector. And in the future, we would want to have a full model of the experiment evolution over time of the superconducting detector and field. But this requires a lot of numerical computation, which we are still working on. And finally, with these numerical results, better design the parameters of the experiment to get entanglement harvesting from space-like separated regions. With this, I thank you for your attention.
Any questions?
So I have two questions. One is, when are we going to see the experiments? What's the I love asking experimentalists for this because it's never true. So.
I mean, it's a tough question, but I mean, here the two students that came also working on this hard. I cannot say much about the experiments. I don't know exactly the timeline, even though we would expect this in not the long term, but rather short term, like the order of years at most. And for the theoretical part, it's actually the work with this model that I was talking about, which also should help to design the experiment. It should be finished in the next months. And the full model of the experiment that includes the full Hamiltonian and also some extra effects that I didn't talk about, this will require more time. And I don't know if they will have any indication of how the experiments would take. Like, can they, like, do you want to say anything? Or this is a hard question.
Yeah, it is a hard question. No, I think what you were saying yeah, there's a lot of experimental things that we need to overcome, but like you were saying, it is a fairly short term within, ideally half a year, but in kind of, like you were saying, a year or 2 year time scale to realize this.
Nice, thank you.
Any other questions? Well, I have one.
So, all right, this is for a 1D entanglement harvesting method, right?
Yes.
Do you think that the setup could be generalized to 2D and maybe 3D at some point, using some sort of idea which is similar to this?
Okay. Do you mean like an experiment that would be in 2D or 3D?
Yeah, a 2D field or a 3D field.
Yeah, that's actually a question that I've been wondering myself. I have not talked with any person from the experimental group because they just didn't came up, but because also it looks complicated. But I imagine that should a superconducting plane of material work as a two-dimensional quantum field? I hope it would, but probably it might have, I don't know about the fabrication, but probably it would have some kind of complications of fabricating the chip.
Thank you so much for the presentation. It was very good. I have two questions if you have time. One is quick, and the other one is very quick. I'm going to start with the very quick one. The waveguide that you showed.
Yes.
Which quantum field does it simulate?
I see.
What's the mathematical expression of the quantum
Oh.
field that the waveguide simulates?
Okay, so basically it would be a like one-dimensional massless quantum field, and up to a good approximation, the waveguide is very long, so it's open. It's free quantum field. Like the boundaries are very far away, and not reflective. So it's basically like the equation for a standard one-dimensional quantum field, but it has one added. Sorry that I don't have the equation, but it has the added effect of having the cutoff, which basically multiplies the modes of the quantum field by a function that decays with the frequency. Sorry. Yes.
And the other question is, at the end of the day, at the end of the experiment, do you have an idea on how are you going to measure something that's going to allow you and your collaborators to estimate the negativity?
Yeah, actually, this is a part that Elena Kornick mainly is working on. This is complicated. Like, it requires a lot doing the modeling of the measurements on the qubits, because the experimental measurement that can be done is measuring the energy level of the qubit, and it requires a model because it's not there is probabilities in the middle. Like, it's not a perfect measurement. You need to estimate correctly what are the errors that you can have. And I mean, as I was saying, Lana Bozanic is the expert on this. And sorry, I lost track for a moment. What I know is that one of the best ways that she found to measure the entanglement, or to have an estimation of the entanglement, is to look at the correlations between X and Y operators on the qubits. So these give a good measure of, this is not a direct measure of negativity, but it's directly related to negativity, and is also with in some situations, like the one we are in, it proves the entanglement.
Thank you.
Yeah, you're welcome.
Okay, let's thank them again.
Thank you.
So that's the end of the session. We have a coffee break in the back of the room, and in half an hour we have the last session. Thank you.
Hi everyone, we are back with the final session of the RQI Circuit Conference. Please join me in welcoming Kelly Wurtz. She will be talking about probing the entanglement structure of quantum fields. Kelly, the floor is yours.
Thank you. Oh, this is kind of rough. There we go. Okay. Thank you for the introduction, Maria. So I'm Kelly, for those of you who don't know me. I'm a PhD student here working with Eduardo Martín-Martínez, and today I'll be talking about a paper we published earlier this year in JHEP by myself and this lovely group of collaborators here. And this looks at the entanglement structure of quantum fields in a way motivated by detector models in RQI. So we've already seen a bit today on the fact that because the ground states of QFT are highly entangled states, local probes or detectors are capable of harvesting entanglement from the vacuum. And it's possible to use this entanglement, for example, for assisting in information processing tasks or violating energy conditions, for energy teleportation, lots of things. But another thing that we're interested in is quantifying the entanglement between subregions of a QFT. And detectors may be very good for this also. And this is a problem that we do need to solve because standard methods of quantifying entanglement of a system directly typically run into lots of issues in quantum fields. For example, we get divergences in the continuum limit when we try to calculate the entanglement entropy between a region and its complement, or we have issues when it comes to finding entanglement between disconnected regions, because these are mixed states and many entanglement measures no longer apply. All in all, we don't have a general method for quantifying the entanglement between subregions of a QFT. And this could be helpful, for example, in looking at processes like black hole evaporation. Detectors, on the other hand, are inherently regular. They have a finite spatial and temporal extent and a finite energy gap, and so we will not get UV divergences. And they also easily handle arbitrarily shaped regions, even in cases with time dependence. So they seem to be a promising and operationally motivated way of studying the entanglement structure of QFTs. But your standard entanglement harvesting protocol does not give much detail on the actual structure of entanglement of a quantum field. When I say entanglement structure, I'm referring to things like the spatial distribution of the entanglement, which degrees of freedom in the field are entangled, and perhaps even the time evolution of entanglement. Now, we can't make this direct connection between the entanglement that detectors harvest and the entanglement structure of a quantum field. For one, because the efficiency of detectors is hindered by local vacuum noise. Also because detectors have a finite number of degrees of freedom, whereas the entanglement in a quantum field is distributed throughout its infinite dimensional phase space. And finally, there's a priori no way to know if the detector's entanglement is in any way capturing all of the entanglement present in a field. And so we'd like to figure out how to use detectors to faithfully capture the entanglement structure of a quantum field. And to figure out how to do this, we can be motivated by the fact that one detector is only a single mode system, or we can define it to be. And this limits the amount of entanglement that it can pick up through any interaction with the field. But through this, we can recognize that the most efficient interaction that we can do is perform a perfect swap interaction with a field mode of our choice. This will fully transfer some field mode of our choosing into the detector and the detector state into the field. Now, it will be the case that no single mode of the quantum field will be able to capture the full entanglement structure, as the entanglement is, in principle, spread throughout all the modes. But we can figure out the minimum number of detectors that we need, as well as the exact couplings that these detectors should have to fully capture the entanglement present in a subregion. And what this paper does is provide a recipe for doing exactly that. So in this process, we model a free scalar massless quantum field as a lattice of quantum harmonic oscillators with nearest neighbor coupling. Using a lattice discretization is equivalent to introducing a UV and IR cutoff in the theory, which is convenient because it allows us to use the tools of Gaussian quantum mechanics in studying this. Our paper also discusses the generalization to the continuum limit, or how our results generalize in that way, but I won't quite have time to get into that today. So this lattice has the following Hamiltonian, where omega is the free frequency of each of the oscillators. Alpha is the coupling between lattice sites. So we can see we're coupling just the position degrees of freedom of, this represents summing over nearest neighbors here. And then Q and P are the position and momentum quadratures of each lattice site. And those are related to the discretized versions of your standard field operators, amplitude and momentum, in the following way, where epsilon is the UV cutoff and n is the number of spatial dimensions. Now, because this Hamiltonian is quadratic in position and momentum, which means it represents a Gaussian state, there exists a corresponding covariance matrix, which is a matrix of the covariances, or one could say correlations between all the degrees of freedom in the system. And we usually will call this sigma. Now, sigma is the covariance matrix representing our quantum field, which, remember, we've effectively put in a box by imposing a UV and IR cutoff. And we bipartition it into two subsystems that we can call A and B. Then we can find the entanglement entropy between region A and B in the following way. First, we find the reduced covariance matrix on A by tracing out the part of the covariance matrix corresponding to region B. We could also do the reverse because the entanglement entropy is symmetric in this sense. And then we find the symplectic eigenvalues of the matrix that results, and then we just effectively add them up in the way that the formula for the entanglement entropy dictates to get the full entanglement entropy between the two subregions. So that's how we find the full entanglement between complementary subregions. But let's remember our goal here. We're not just trying to determine this entanglement. We can only do that by hand in this because of the simplicity of this lattice system. But what we're trying to do is devise a method of measuring entanglement in an operationally motivated way, which will provide a framework that we can extend to systems beyond what we're actually capable of calculating from the lattice or the field directly. And we'll use that idea of the swap interaction to determine the specific modes within a subregion that are most entangled with the other region to get the maximum amount of entanglement in a single interaction. And I should specify in this paper, we'll just be considering the case of entanglement between complementary regions. So let me be precise about what I mean when I say modes. So when we obtain the reduced covariance matrix for subregion A after tracing out subregion B, we're free to express it in any basis that we want. So our modes could simply be the modes of all the local oscillators by themselves. Or we could construct modes that are linear combinations of these degrees of freedom. Or we could find the basis in which the covariance matrix is diagonal, which would be finding the normal modes of the system. We could also take linear combinations of those normal modes. So the modes which I'm talking about here are not exactly mechanical modes in any sense, but they're rather just different linear combinations of the degrees of freedom in our system. And one choice of that corresponds to the one that would contain the most entanglement. And that mode, or group of modes, is the one or group that we'd like to swap with the state of our detector, our detectors. And so the main result of our paper here, and our paper contains the proof of this, is that the most entanglement between a region B and some group of, say, n modes within subregion A, maximizing over any possible choice of modes, in fact, is found by the n most mixed normal modes of the reduced covariance matrix of subregion A. And those most mixed normal modes are identified by those having the largest eigenvalues, because remember, the entanglement is calculated purely from the eigenvalues, and the largest ones will contribute the most to the entanglement. And so with that, we have a prescription for finding the set of n modes that a detector system with n degrees of freedom would couple to extract the most entanglement with the complement region. And now further, it only takes a simple rephrasing of this result to get the spatial coupling profile, or the smearing function, that a detector would need to swap with that mode. So the normal mode, can itself be expressed in terms of its own quadrature components, which we'll call capital Q and capital P. And those mode quadratures can be expressed as linear combinations of the local oscillator quadratures, little q and little p, where the coefficients f and g tell us the spatial profiles of the normal modes in position and momentum, respectively. And to relate this to the standard particle detector language, if we take the continuum limit of these functions f and g, then that tells us the smearing function that a detector should have to swap with a given mode. Now, to kind of visualize these two, the position and momentum spatial profiles as one, we can multiply them together component-wise to get the mode occupation function. And looking at this occupation function for the most mixed mode of each subregion in 1, 2, and 3 spatial dimensions, we get the following results, where these 3 plots down here are just slices in the z-axis of this 3D plot here. Kind of see what's going on as we go through that cube. And we can see that the support of these modes are strongly concentrated near the boundary. And this is what we expect, because our Hamiltonian only contains nearest neighbor interactions. And so the entanglement present in the ground state between the region and its complement will largely be shared between in the short distance correlations across the boundary. So now I can give a bit more detail or just mathematically show what the swap interaction between a multi-mode detector and some set of modes would look like. The interaction Hamiltonian for the operation that would perform these mappings here is given by that Hamiltonian. And this can also be expressed as a unitary operator or the swaperator. So with this, we have a complete description of the swapping protocol that we can in principle use to transfer some given mode of the field into our detector. But the question remains of how many modes we need in order to capture the entanglement structure of our field. Now, for this quantum field, the entanglement structure is that of an area law, which means that the entanglement entropy scales with the area of the subregion size. And again, this is because we only have nearest neighbor interactions, so vast majority of correlations are right on the boundary. And while the full entanglement is distributed throughout all the degrees of freedom of the system, can use the fact that it's suggestive, the fact that correlations are right on the boundary is suggestive that we might need fewer than the full number of degrees of freedom in the system to capture the full entanglement structure. And indeed, we find that we actually only need to consider as many modes as there are boundary sites for a given system to capture the full entanglement. So in one dimension, the boundary between some region and its complement in a harmonic chain will always just be 2 sites. And indeed, we find that we only need to take into account 2 modes to recover the full entanglement entropy between the 2 regions. And these percentages, which apply to both these plots here, are representing the percent of the number of boundary sites in the number of modes we're taking into account. So for example, if there's 100 sites that make up the boundary, this corresponds to taking into account 10 modes, 20 modes, 30 modes, and we find again that we only need to take into account the same number of modes as there are boundary sites to recover the area law. In 2 dimensions, we expect the area law, which is more like a perimeter law, to be linear, and in 3D, we expect this to be quadratic, which we indeed see. And so this tells us that the number of detectors we need only scales with the area of the subregion size. And all in all, this has showed us that detectors could provide a measure of the entanglement between arbitrary regions of quantum fields. We've seen that the optimal smearing function can be obtained via a normal mode analysis of the subregion. And the next steps we want to take with this work is to determine an analogous optimal protocol for non-complementary or disconnected regions. Thank you for listening.
Now we open the floor for questions. Sorry. Do we have any questions?
Thank you for your talk. So in this setup, you have this nearest neighbor interaction. And that's true for like 1D, and then you also did like 2D and 3D lattices. Like, was everything, so at the end you had a slide that said, so the scaling followed the area law. Were there any behaviors that kind of broke down as you went between the dimensions, or was everything, were the models like, did the results really carry through super well? Like, yeah. I guess I'm not very familiar with these sort of lattice models, and I was wondering like how well they generalize between dimensions. And I was wondering this question before you showed this, and you showed this, which seems to indicate that they generalize pretty nicely.
Yeah, we basically saw the expected behavior in 1 through 3 spatial dimensions. We included all of them basically just to show that these results are not just, for example, say special to 1 or 2, but in this, we have nearest neighbor interactions in all of these, and so we expected and indeed got that, the entanglement is just due to these short distance correlations, and we get the area law in both cases. And it even seems to, you can see like, for example, taking into account 10% of the boundary modes is even sort of taking into or capturing a similar fraction of the entanglement in 2 and 3 dimensions, which I guess we wouldn't know a priori, but yeah.
And I guess as another question kind of related to these lattice models, when you said like, oh, the follow-up, we're interested in these kind of disconnected regions, is this, or not, sorry, it's like not complementary. Would they still be adjacent regions, or would you have kind of like 3 regions, A, B, and then C, and you'd be looking at B and C that like somehow the correlations need to pass through B to get to C? That question made sense?
Yeah, so that's kind of the different case of maybe imagining disconnected regions that are like 1 and 2 versus 1 and 2, where 2 is a shell around it. Those are 2 examples of things we could consider and do plan on looking at. If we were considering, for example, just some region and not its complement, but a shell around that, we would not expect those results to differ from these really in any way, because the correlations past that aren't really contributing anything. They're mostly along the entangling surface.
Okay.
Do we have more questions? Okay, so Kelly again. Okay, now we will hear from Jiayue Yang, who is going to tell us about quantum information in gravity, holographic complexity. Jiayue, the floor is yours.
Yeah, thank you. Hello, everyone. My name is Jiayue Yang. I'm a second-year master's student from Mann and ISRQI Research Group. And today I'll talk about a project with my undergraduate supervisor, Andrew Frey. It is a subfield of quantum information in gravity called holographic complexity. And this is based on our recent paper, Complexity Scaling and Phase Transition here. And this is our outline. First, I will provide you with some background information, like the concept of complexity and also the ADS-FT correspondence. And then I will talk about the holographic complexity proposals. And I will give you an introduction to the magnetized ADS soliton. And then we will evaluate the holographic complexity for 3 different proposals. And then finally, I will make a conclusion. First, let's begin with complexity. You might ask this question, what is complexity? It is similar to ask how hard it is to do a task or how many steps you need to solve a problem. And in quantum circuit model, quantum complexity is defined as a minimum number of quantum gates that you need to reach a target state from our reference state. Here, psi is our target state. Oh, sorry. Here, psi is our target state, and psi naught is our reference state. And the minimum number of quantum gates, the minimum number of G's here, are the complexity. And what is ADS-FT correspondence? ADS is the anti-de Sitter spacetime. It is a spacetime that has lective cosmological constant. And in Poincare coordinates, this is a metric for the anti-de Sitter spacetime. And here, r is a radial direction, x is the spatial direction, and t is the time direction. And when r approaches infinity, it is our boundary of the ADS. And the conformal field theory is just a particular quantum field theory that is invariant under conformal transformation. And what is ADS-FT correspondence? The ADS-FT correspondence was first proposed by Marcena in 1997. The basic idea of the ADS-FT correspondence is that there is a gravitational theory in d+1 dimension and living in the bulk, and there is a conformal field theory in d dimension living on the boundary, and there is a duality, or say there is a correspondence between the 2 theories. And the quantities that can be computed in the one theory that can also be computed in the dual theory. Like a famous example of this ADS-FT correspondence is the holographic entanglement entropy, saying that the entanglement entropy of a subsystem living on the boundary is dual to the area of some extremal surface in the bulk. And by here, I want to say that the entanglement entropy is not enough. This idea was first proposed by Cednikawan in 2014. He considers 2-sided ADS black holes, and at the time equals 0, the 2 horizons of the 2 horizons meet together at time equals 0, and the volume of this wormhole or the volume of the black hole interior is 0. And as time goes by, as we can see, the volume of the wormhole or the volume of the black hole interior grows. And it will grow linearly with time, and the growth rate is exactly proportional to this area or the area of the event horizon. And but we can also know that the black hole entropy becomes a constant at a very quickly, and the entropy is saturated. So we need something else to capture the growing geometry of the wormhole. So Cednikawan proposed that the thing that we need is complexity. So this is our motivation for the holographic complexity. This is the argument that the volume of the black hole interior grows linearly with time, and also the complexity of states also grow linearly with time. So we have the complexity is proportional to some volume, and here G Newton L is just something that we added to make this formula dimensionless on the right-hand side. And the concrete statement is that the complexity of the boundary safety state is proportional to the volume of the maximal volume slice. And here are some steps to help us evaluate the complexity using the complexity equals volume conjecture. First, we need to choose a time slice sigma on the boundary, And next, we consider all the space-like hypersurfaces B that's anchored on this boundary sigma. And then we vary these hypersurfaces to find the one that has a maximal value. So we can use this maximal value to compute the holographic complexity using this formula. But as we can see in this formula, L is some arbitrary length scale, so it is a little bit ambiguous. And why can we use this arbitrary length scale here? So to avoid this ambiguity, another proposal was proposed. It is complexity equals action conjecture. It is saying that the complexity of the boundary safety state is proportional to the action of the Wheeler-DeWitt patch. And the Wheeler-DeWitt patch is just the union of all the space-like hypersurfaces that we considered before. So the boundary of this Wheeler-DeWitt patch is just the non-boundaries. So this whole region is our Wheeler-DeWitt patch. And the conjecture says that the complexity should be proportional to the action of this region. And here, the dimension of action is h bar, so we can make this thing dimensionless without introducing an arbitrary length scale L. And here are some steps to help us to evaluate the complexity equals action conjecture. First, we need to choose the time slice sigma, and then we consider the union of all the space-like surfaces, and we compute the action of this region, so we can find the complexity. And there are another proposal called complexity equals volume version 1. It is just that we consider the space-time volume of the Wheeler-DeWitt patch. And now let's move on to the magnetized ADS soliton. In our paper, we investigate the holographic complexity of the CFTs compactified on a circle. And the periodicity of this circle is called delta phi, and there is a Wilson line around this circle. And as we can see, as R decreases, the proper size of this phi circle will get smaller and smaller. And when R approaches R0, the circle vanishes. And to avoid a conical singularity here, we need the phi has a periodicity called delta phi. And let's make a comparison between the ADS soliton metric and the periodic ADS metric. As we can see, when we let the f of r equals 1 and r0 equals 0, we can reduce it to the periodic ADS case. And the ADS soliton has a cigar-like geometry without horizon, and the ADS is a cylinder-like geometry with a horizon. And now let's evaluate the complexity using the three different proposals. For the CV conjecture, the volume of the maximal volume slice is just this integral. It's very easy. And as we can see, when R0 equals 0, it is an ADS case. And but here is a problem. There is a divergence in this formula. Rm will approach infinity. So in order to cancel this divergence, we introduce the complexity of formation. It is just the complexity of the magnetized ADS soliton minus the corresponding complexity of the ADS. So our complexity is just proportional to this part. It's proportional to R0 to d minus 1. And as we know, R0 is proportional to 1 over delta phi. So we can get that the complexity is proportional to 1 over delta phi to d minus 1. And if we plot this complexity, we can get this diagram. It is a function of the Wilson line, and when we increase the Wilson line, we will find that there is a phase transition from this ADS soliton to the ADS case. And for the CV version 2 and the CA conjecture, we need to find our Wheeler-DeWitt patch. And this diagram shows the shape of our future light shades, this area. And we can also have past light shades. So this figure helps us to define our Wheeler-DeWitt patch. And so if we have a space-time volume in this region, we can compute this integral. And if we plotted this CV version 2 versus the Wilson line, we can get that the ADS soliton also scales as 1 over delta phi to d minus 1. And there is a phase transition at this point from this ADS soliton to the ADS case. And for the CA conjecture, it is a little bit complicated, but we just need to evaluate the action of this weighted part region. It has a bulk action and also the boundary action for these non-boundaries. And there is also a joint action term. For the joint is just the intersections of our non-boundaries. And if we plot the CA versus the magnetic flux, or say the Wilson line, we can also observe the phase transition from the ADS soliton to the ADS. And here are just all the proposals that I put together in one slide. As we can see, they have the same scaling behavior and they have the same phase transition behavior. So in conclusion, we evaluated the holographic complexity for CFTs and compactified on a circle with a Wilson line. And for all the 3 different proposals, we find the same scaling behavior and the same phase transition behavior. So these are the common features that they all share. That's all. Thank you. Yeah, that's a very good question. And the motivation for introduce the magnetic flux is just that we want some parameter to help us observe the phase transition. Like if we want to investigate the phase transition of the space-time, we need some parameters. So here we just choose this magnetic flux. And if we vary the magnetic flux, we can observe a phase transition between the 2 different space-times. So this is our motivation.
So, so basically the paper is about like checking 3 models by looking at the phase transition behavior of magnetized ADS.
Yeah, right.
So,
Yeah, maybe there are some other methods to check, but we just choose this method to work on. Yeah. Yeah, thank you. Yeah, right.
So, if you have other methods except for phase transition, do you have any idea of how to check the validity of the complexity model? So, for example, right now you have 3 models for complexity, right?
Yeah, right.
And you want to check, or at least like, you want to see the difference among these 3 cases, and you use the phase transition. Now, ultimately, we want to see the correct complexity model. And in your opinion, do you have any idea to how to check which one is the correct? Like, is there like any idea?
Yeah, in our paper, we just said that for the 3 different proposals, they can all be the candidates for complexity. So basically, we find the common feature that they all share. And there is also another paper called complexity equals anything. So in my opinion, complexity is not that we find which one is correct, but there are a bunch of definitions, a bunch of complexity that can be the candidates to capture the geometry of the wormhole. Yeah.
So maybe they are equivalent as well, right? Like maybe in some sense, like there's a map between these models. And
Yeah.
you can say, oh, they're in equivalence class or something like that.
Yeah, I think so.
Also explain, so what's the origin, so in the original paper by Susskind, you know, as title says, you need to have that complexity. Could you again explain why complexity is needed, or why the authors are that's the case?
Yeah, Susskind consider a two-sided ADS black hole. And at time equals 0, the 2 horizons meet together, right? So the volume of this wormhole is just 0. But as time goes by, the volume of this, the volume in between these 2 horizons will grow. And but entropy is always a constant. Entropy is just the area of the event horizon. And so that means that for this case, the black hole becomes a thermal equilibrium very quickly and has a constant entropy, but the wormhole is still growing. So we need something else to capture, to describe the growing geometry of the wormhole. So what something else is still growing at late times. So complexity is the thing to capture this growing geometry. It is still growing at late times. Yeah, thank you.
Okay, so let's sing Jiayue again. I turn it off. Oh.
No, it's on now.
Do you need it? It's okay.
It's for the recording.
This one is for the recorder. This one is for the recorder.
Oh, okay.
Yeah, so you don't know.
Yeah. Can you hear me? Okay, very good.
Okay, and now we welcome our last invited speaker, Professor Achim Kempf, who will tell us about representations and the emergence of a space-time.
Yeah, can we make this picture bigger?
If you go bigger, you won't be able to transition. Like, okay.
Yeah, it's just that this was distracting, but it's gone now, so it's good. Is this okay? This? Okay. All right. Okay. Thank you for the kind invitation. So I will talk about representations and the emergence of space-time. Let me start by reminding you of what is a representation in mathematics. So traditional representation theory is about representations of Lie groups and Lie algebras, where
we have a map into matrices that act on vector spaces. The point of a representation is that it is preserving the algebraic structure that it is representing. So for example, in the case of a Lie group, we have that whether we first multiply two elements of the Lie group and then represent that as a matrix, or we first represent both elements of the Lie group, A and B, as matrices, and then multiply those matrices, that should be the same. And then we speak of a representation. Now, more generally, we can view a representation to be any structure-preserving map. Oh, I see. I could also point to this here, right? Okay, so more generally, we can view a representation to be any structure-preserving map from some algebraic structure A into some other structure B. Examples are, for example, vector spaces. They're the abstract axioms of a vector space. That's an abstract thing. Any concrete vector space is a representation of it. In fact, in mathematics, there is a theory that is dedicated to structure-preserving maps, or representations, as we may also call them. And that theory is called category theory. And there they have objects that are called functors, and every functor can be interpreted as a structure-preserving map, so it's a representation in our sense. But I don't want this to be constrained to pure mathematics. For example, in quantum mechanics, we have abstract states and abstract operators, and they have representations, for example, position representations, momentum representations, and so on. In this particular case, they are equivalent by the Stone and von Neumann theorem. And then, more generally, there are approximate representations. An example is the classical phase space. We know that nature is actually described by quantum mechanics and its Poisson algebra. And yet we work with classical phase spaces when it comes to spacecraft engineering, for example, for flight path engineering, and many other circumstances in engineering where we still use classical phase spaces. So the classical phase space is an approximate representation of what is really going on, which is the quantum Poisson algebra. Also, for example, when an experimenter sets up a quantum circuit, what it is in the sense here is an approximate representation of an underlying quantum algorithm. For another example, we know that spacetime has curvature. We're not sure whether it has torsion. There is no evidence, no positive evidence that spacetime has torsion. But if one day super accurate measurements reveal that spacetime has torsion, then in hindsight, we will realize that the way that we have been dealing with spacetime so far, namely torsionless and with curvature, was just an approximation to the real deal that was a spacetime that actually had curvature plus torsion. The point I want to make on that slide is that approximate representations can be really good. But in some regimes, these approximate representations can become bad approximations, or in some regimes, no such representation is even possible. For example, let's look at the first case, classical phase space approximating being an approximate representation of the quantum Poisson algebra. When it comes to the dynamics of electrons around a proton, then the classical phase space is really useless. It just doesn't work as a representation. It's not even an approximation anymore. Okay, so the point here is that approximate representations can have their regimes in which they're good, but in other regimes, the abstract structure just doesn't have this approximate representation. Now, let us talk about what we know for sure in physics, and they are quantum field theory and general relativity. And if we put the two together, we get quantum field theory on curved space-time. That's as far as we know physics for sure. So let's look at quantum field theory on curved space-time. Could it be that it is a representation of something more abstract? If that's the case, what could happen. What could happen, for example, at higher energy regimes that we have not explored yet? Well, what might happen is that at these high energy regimes, this underlying structure, this underlying theory of which quantum field theory and curved space-time is a representation, it could be that at these higher energies, quantum field theory and curved space-time may no longer be a good representation. Or it may be useful as a representation, but maybe with a different dimension of space-time, or maybe something else changes. It could also be that at extreme scales, for example, the Planck scale, it could be that the theory, the abstract underlying theory, would be in a regime where it simply doesn't have a representation, even an approximate representation anymore in terms of quantum fields on a curved space-time. It would still be the same underlying theory. Just in one regime, it has this kind of representation, another regime, another kind of representation. And in some regime, it may not have any representation of the type that we know. So let's try that out. Let's search for an abstract, simpler structure of which quantum field theory and curved space-time is an approximate representation. And then when we have that underlying structure of which quantum field theory and curved space-time is an approximate representation, then let's see whether that underlying structure also has other representations in other regimes. Let's start with observation 1. There are 2 observations, and then we put them together. So observation 1 is that matter is completely describable through correlators. That's not news. If you've studied quantum field theory, you know that everything about it can be encoded or is encoded in the endpoint correlation functions of the quantum field theory. Now let me go off on a tangent for just a minute. We could now say, okay, that's cool. Everything about the dynamics of matter is encoded in endpoint correlation functions. That's information theoretic. And we could study now these correlation functions information theoretically. Quantum field theoretical interactions are classical and quantum channels. When one particle collides with another particle, then it transmits information automatically, classical information. There's a classical channel that's established when 2 elementary particles interact with each other. But also a quantum channel is established. If, for example, one of the collision partners was previously entangled with an ancilla, we can ask, where did this entanglement go? Which of the collision partners took away the entanglement? Or which one took more, which one took less of the entanglement away? These are questions of quantum channel capacity. And one of the things we are looking into in my group is to describe all of the interactions of quantum field theory of the standard model information theoretically only. Normally, we think of interactions as being about the transfer of quantum numbers like momentum and energy and so on, but maybe the whole thing can be rephrased in terms of the classical and quantum channel capacities. And I think that's natural because the building blocks of this study are just the endpoint functions, they're correlators. And correlators are primarily information theoretic. But now let's move on to observation number 2. Observation number 2 is that not only matter is described by correlators, but also space-time is describable through correlators. And of course, many of you know that already. Namely that the metric can be expressed through the 2-point correlation function in this way. You differentiate it, take it to some power, differentiate it, take the coincidence limit, certain prefactor, you get the metric. Why is this possible? Well, it's possible because the 2-point correlator is, in the ultraviolet, a function that of the geodesic distance. And if you have geodesic distances, you can calculate the metric, because the metric just gives you infinitesimal geodesic distances. So this means that space-time, the space-time metric can be reconstructed from the 2-point function, or put it differently, a space-time is normally viewed as a differentiable manifold with a metric, but it can also be viewed as a differentiable manifold with a 2-point function. So the summary so far is this. Putting together observations 1 and 2, we find that both matter and space-time are expressible through the quantum field theoretical endpoint functions. Now, is this the deep underlying theory that we were looking for here, of which quantum field theory and curved space-time is a representation? Hardly, because we just look at things differently, but it's not that we have removed the representation aspect of it. What we want is to see quantum field theory on curved space-time as a representation of something more abstract. What could that be? Now here we notice that these endpoint functions are functions of a bunch of variables. And these variables are space-time coordinates. This assumes that there is a space-time manifold to start with. Is there a more abstract coordinate-free formulation of these endpoint correlators? And there is, and it's not mathematically all that new. Remember that in quantum mechanics, a Green's function, and these are in quantum mechanics, these are just 2-point functions. In quantum mechanics, a Green's function can be written in any basis. I can write it in the position basis, momentum basis, or any other basis, or no basis. For example, if this is the Green's function for the time evolution, then the abstract thing underlying it is just the time evolution operator. And the time evolution operator is an object unto itself. If you choose to express it in the position basis, you get the Green's function, but you don't have to choose a basis. It's an abstract operator on the Hilbert space, an operator with 2 arguments. And now here too, in quantum field theory, the correlators are written in a position representation. But really I could change coordinates in any which way we want. I could even Fourier transform or do Hilbert transforms on it. It doesn't matter. It's an operator. It's just that it is no longer an operator that has only 2 arguments. It's an operator that has n arguments, but it's still living on a Hilbert space of fields, just like this one was on wave functions with the battery is failing here. So in quantum mechanics, it was the Green's function acts on wave functions. In quantum field theory, it acts on fields. But mathematically, we can take out the representation. We can look at the abstract object that's behind the Gn, and of which this is just a position representation. So let's look at these Gn, these abstract Gn, operators on a Hilbert space of fields, which take n arguments. Now that gives us a coordinate-free description, an abstract description of quantum field theory in curved space-time. Or does it? Does it really constitute an equivalent way of describing quantum field theory in curved space-time? In quantum mechanics, we know that the time evolution operator does the job. I can just choose the position basis, and I get back my Green's function. But here, what basis do I choose to get back those endpoint functions? Can I just choose a position basis? Well, what is a position basis? We don't have position operators in quantum mechanics, so we don't have the ability to pick position basis on the basis of they are the bases in which the position operators are diagonalized. We'll have to think of something else. So if the abstract Gn are supposed to be an equivalent description of quantum field theory in curved space-time, equivalent to actually writing them down as functions of position coordinates on a manifold, then we need to be able to get back to from the abstract Gn to the Gn of x1, x2, x3, etc. As I said, in quantum mechanics, it would be easy to get from the time evolution operator the Green's function in position space. I just diagonalize the position operators, and then I obtain a position basis, and I can write my time evolution operator as a Green's function, and everything is as it was. Here, we can adopt a similar strategy even in the absence of position operators. Namely, what we can do is, first fix this typo here. So what we can do is we can use the locality of interactions in quantum field theory to recover the position basis. Namely, the Gn for n larger than 2 describe interactions, and they are local. So instead of diagonalizing position operators in quantum mechanics, in quantum field theory, what we can do if we start in a basis-independent framework is that we can diagonalize the vertices. We can diagonalize the interaction terms, which we know is possible because interactions are local. So the coordinate bases, the position bases, are identified as those bases in which these endpoint functions are diagonal. We're relying here on the locality of the vertices, which is not a mathematical necessity, it's a physical necessity. So if the theory's interactions are indeed local, then the vertices for n larger than 2 are diagonalizable. Diagonalizing them, we obtain the bases in which those higher point functions are diagonal. And in particular, these are position bases, so we can write down these endpoint functions as functions of positions on a manifold again. Now, we use the vertices to determine the position representations, and that the vertices are for n larger than 2. But once we have the position representation, we can then also apply that to write down G2 with 2 arguments in the position basis. So that's this one. And that's great because from it we can recover the metric. So this means that indeed having just the abstract objects means we have all the information that was previously in the concrete Green's functions, because we can go back and forth between the abstract and the concrete. It also means, by the way, that you can hear the shape of a drum. You just have to drum it harder. Because if you drum a drum really hard, then it gets into the nonlinear regime. And the description of that is, if you describe the solution of that differential equation, nonlinear differential equation, what you do is you write down Feynman graphs. I mean, effectively, that's what you do when you solve for a nonlinear drum. And what we just showed is that if you have the vertices, you can actually get from the spectrum of the second derivative, from the 2-point function, you can get the metric. Now, the drum, of course, is a flat case spectral geometry. Is more interesting when it's about the shape of a vase or shape of an object, but the same argument applies. So as long as you get into the nonlinear regime, you can recover the shape from the sound. Okay, so now we have an abstract description of quantum field theories on curved space-time. But given let's say you start with these. You give yourself some operators, G superscript n, where n indicates how many arguments this operator takes in. You just pick arbitrary ones. Can they be represented as in terms of a quantum field theory that lives on a curved space-time? In general, of course not. And that's because the endpoint functions for n larger than 2, so the vertices, the interactions, they have no mathematical reason to be diagonalizable. So in general, no, the abstract structure doesn't have a representation in terms of quantum fields that live on a curved space-time. We know from physics that in some energy regimes, the actual Gn do have at least an approximate representation, which is we know that the vertices of quantum field theory are diagonalizable, at least to the extent that we can measure locality, at least down to about 10 to the minus 21 meters, which is what the LHC can resolve. So we know from experience, from experiment ultimately, that the actual Gn that rule what we know they are approximately diagonalizable in the low energy regime. But we also know that in general, generic Gn have no reason to be truly, fully diagonalizable. Which means that in general, if you just pick some random Gn operators on some Hilbert space, then they do not possess a representation as quantum field theoretical correlators on a space-time. At best at low energies, but in general, no reason that they would. So the summary so far is that space-time and matter are describable by a collection of abstract endpoint correlators, which are just operators on a Hilbert space with n arguments. And a priori, the set of all representations of the Gn that we obtain from the physics as we know it, So if we take the standard model and we lift it to this abstract description that doesn't rely on a position representation anymore, then this abstract structure may also have other representations other than the ones we usually use. For example, quantum reference frames might be just other representations of the same abstract structure. Who knows, maybe even dualities such as ADS-CFT are just instances of an abstract structure having two representations. So this is about the GN that we lift from the standard model of physics. However, generic GN, if we just pull some out of the hat, if we just make up some GNs, then they're at best approximately representable as quantum field theoretical correlators on a curved space-time, at best at low energies. In general, there's no reason to expect that they really are diagonalizable, the vertices, the higher point functions, the interactions, and therefore we do not have an exact representation in terms of quantum field theoretical correlators on a curved space-time. So in this way, quantum field theory could be an approximate representation of a more general theory that we might call pre-geometric, because it doesn't assume that there's a manifold underlying, but it allows it to happen in regimes where the vertices are diagonalizable. So what could be a theory of these abstract GNs? I won't say much about it here, because I want to give an explicit example later, but abstractly what we can say is this. The GNs are the Taylor coefficients of the partition function. So all of them together can be handled at once by just looking at the partition function. The partition function, on the other hand, is the Fourier transform of e to the power is. If you didn't know that before, let me tell you, to solve a quantum problem is to do a Fourier transform. To solve a classical problem is to do a Legendre transform. What we see here is that to solve a quantum problem is to obtain the partition function. And how do you do it? You Fourier transform this. This is the function to be Fourier transformed, S of phi. And here we have the Fourier factor, e to the power of I times j phi. This is the old variable. This is the new variable of the Fourier transform. It's just continuously infinitely many Fourier transforms all at once. The point is, Fourier transforms are invertible. And yes, you can calculate from the classical action what the partition function is, but you can also do the Fourier transform of the partition function. That's another path integral, and you get the classical action back. It's one-to-one. And a priori, there's no reason we should get hung up on the classical action. Yes, we've started with classical actions for more than 100 years. But this is where the music plays, right? This is what we really want, the endpoint functions, the coefficients, the Taylor coefficients of the partition function. And those are described information theoretically. Why not do the information theory of that? You see, a one-point function, that's a probability distribution. This is all about von Neumann entropies, Rényi entropies, and so on. Two-point functions, we have tools for that: mutual information, coherent information, classical and quantum channel capacities, negativity, and so on. And then for 3 and 4 and higher point functions, we get the whole higher order web of informational relationships. So I'm advocating to study this rather than that. And then once we've fully understood this, we can always do a Fourier transform and reinterpret what we have in terms of that. Anyway, recently, with the two postdocs, Markus Reitz and Barbara Schroeder, we got a paper in PRL accepted. Here is it, and it's not yet out, but should be very soon. Here's the archive number. And we did an explicit example of all of this. For that, we started, and I'm just summarizing the paper because I'm running out of time. I'm summarizing the paper. We start with the theory of a number of free bosons, a number NF of free fermions, and gravity. So in principle, the bosons and the fermions are free, but they interact via gravity, and only via gravity. We did that for simplicity, not to make it realistic. It would be much more realistic to put interactions in there. But in this way, assuming the particles interact only through gravity, we were able to calculate the partition function explicitly. So we start with the theory of free bosons, free fermions, and gravity on a space-time as usual. And then we express that theory in a coordinate and therefore basis independent way. Just lift everything so it's completely abstract. And once we have that abstract theory, we can then, of course, recover what we started with, namely that theory of n bosons and f fermions on a space-time with curvature. But having the abstract theory, we can now search for regimes in which no such representation exists, or maybe a representation in terms of quantum fields and curved space-time, but at another space-time dimension. So we calculated the partition function of that, and then we calculated the space-time dimension. So whenever the abstract theory has a space-time representation, whenever the abstract theory has a representation in terms of quantum fields that live on a curved space-time, we ask, well, what dimension does it have? And let me remind you that Hermann Weyl 100 years ago already figured out that if you know the spectrum of a wave operator, then the density of the eigenvalues of the wave operator is indicative of the dimension of the manifold on which the wave operator lives. And it's this little d, that's the dimension of the manifold. So it's a particular scaling. It's quite plausible. Think of a particle in a box. One particle in a one-dimensional box has a spectral, the spectrum is n squared, for n being the integers. But if it's in a two-dimensional box, then it's n1 squared plus n2 squared. If it's in a three-dimensional box, it's n1 squared plus n2 squared and 3 plus n3 squared. And the spacing of these eigenvalues is different, and it's indicative of the dimension in which this happens. So Weyl already discovered that, and it applies for curved space too, as long as the curvature radius is smaller, is larger than the scale of the wavelengths that we are dealing with, of the wavelength of the waves that correspond to the eigenvalues in question. So what we did is we took the abstract theory, we calculated the probability distribution for the spectrum of the wave operator, and then, or wave operators, and what we found is that using Weyl scaling, the dimension, when it exists, whenever the theory has a regime in which it can be represented in terms of quantum field theory on curved space-time, the space-time has to have this dimension. It's 2 plus the number of fermion species minus n times, 2 plus the number of fermion species minus the number of boson species. Which means that it is as if there is a Fermi pressure. You see, the larger NF there's a Fermi pressure to expand the dimension of the spacetime. Not just the dimension, not just the size of the spacetime itself. We calculated that too. But also, there's a Fermi pressure to expand, to enlarge the dimension of the spacetime. And then there is a bosonic pull to reduce the dimension of the spacetime. Thank you. Right. And so what that means is, okay, so we obtain that dimension, that the dimension depends on the number of bosonic and fermionic species. But the number of bosonic and fermionic species, the effective number depends on the energy scale that we are looking at it. At low energies, you don't see all of the fermions and the bosons. At high energies, you activate them too, those that are having higher rest masses. So how many species you actually deal with depends on the energy scale that you look at it. And that means that this formula changes as you go up the energy scale, so the dimension can change. And here's an example. We start with 32 low mass fermions and 30 low mass bosons. And we get, in this case, that the effective space-time dimension is 4, so we have an approximate representation on a 4-dimensional space-time. And then we add, and then we say, okay, but maybe there's one fermion species that's really massive at like medium masses, and 3 boson species at those medium masses. And that changes the balance of fermionic push and bosonic pull, and then the dimension drops to 2. Of course, there are some regimes where we don't have a representation, right? It's like space-time boils up and then condenses again into 3 dimensions and then into 2 dimensions. Then in principle, you could imagine that as you go to higher and higher energies, the dimension might drop into the negative, so there is no representation in terms of quantum field theory on curved space-time anymore. It might also get stuck somewhere somewhere else, like in the transition regime here, so that there's no representation. In this way, space-time might emerge from a Planck scale. At the Planck scale, it just may not have the abstract structure may not have a representation in terms of quantum field theory on curved space-time, but then at lower energies, that representability is restored. And it might go through dimension changes as well. So what we found is, in the example, that space-time dimension depends on the bosonic pull versus the fermionic pressure. And this balance depends on the energy scale. And therefore, in some regimes, for example, the Planck regime, no positive integer dimension might come out, and therefore no space-time representation. It would be impossible to represent that abstract structure on, as a quantum field theory on a curved space-time. Then you let the energy drop, and then the same abstract structure becomes representable, let's say on 2 dimensions, and then at even lower energies, it becomes representable in 4 dimensions. The overall message of my talk then is this. The physics of the emergence of space, time, and matter could be, mathematically speaking, the emergence of the representability of an underlying abstract, presumably information theoretic structure, as quantum fields on a space-time manifold. And maybe Carl Sagan anticipated it all when he said very wisely that the cosmos is within us. We're made of star stuff. We are a way for the universe to know itself. Thank you. Well, those correlation functions are meant to be just those arising from the regular Feynman rules. So you start with the Feynman rules of the standard model. You calculate your correlation functions from that with renormalization and the whole thing. That's what you start with. And you typically write this in a position representation or in a momentum representation. And then you lift it and you say, well, I write it representation independently. Right? So you just have them as abstract operators now on a Hilbert space. And then you can consider the theory of those and ask, well, I know one regime where they can be represented, and that's the regime of low energies where we get the standard model as we know it. But maybe that same abstract theory also has other representations. Now, we didn't do it for the standard model, but we did it for the simplified theory of just free bosons and free fermions. And what we found is that that same theory, just the theory of bosons and fermions and gravity lifted to an abstract theory, that same theory has multiple regimes, and what regimes it has depends on the mass spectrum. It depends on how many fermions do you have of which mass, and how many boson species do you have of what masses, and from that you can then calculate regimes in which the spacetime would have this many dimensions, or that many dimensions, or that many dimensions, or also regimes where the abstract theory simply cannot be represented in terms of a quantum field living on a space-time of any dimension.
Yeah, thanks for your answer. My second question is that, you guys calculated the dimension in terms of the species of fermions and bosons, right?
Yeah.
For example, in 2 dimensions, there are anions that are natural bosons of fermions. So have you taken that into account?
No, that's a good point. In principle, one could do that. We looked only at bosons and fermions. But if you were to consider anions, you would kind of already build into it that you can have only 2 dimensions. But we didn't want to make any assumptions about the number of dimensions.
Okay, thank you.
Thales?
idea is very interesting. I think that I really hope that it works and that it's possible to describe the universe in this very simple information theoretic way. Now, if I understand correctly, the notion of dimensions that arise from this theory depends on the energy scale, right? And in this sense, it's very easy to do a very simple test of like, I don't know, like in the world that we live, what are the relevant particles that actually we need in order to describe the bulk of the things that we see? And I would argue that it's not that many, right? Because the average energies that we have, they're not, I mean, we can compute the amount of particles that actually matter, and we can get a number out of it. So have you done this calculation, and is this number 4?
Well, I gave this presentation earlier, and people were asking very similar questions, and I have to say I didn't calculate it. Others did, and they said they come up with 4. But I don't trust it because we haven't taken into account the gauge principle and interactions. Interactions mean that certain things are not independent, that otherwise would be independent. Gauge symmetries mean that the number of degrees of freedom that is apparent is not actually the real number of degrees of freedom. One should then ask, should we count before gauge fixing or after gauge fixing? I think there are a number of questions that need to be settled before we can seriously count to get the number of dimensions. But somebody said it's 4. But how did they count gauge degrees of freedom? I don't know.
Do we have more questions?
Everybody's probably very exhausted. Huh?
Okay, so let's take Achim.
Thank you. Okay, I'm actually not wired with anything. Good. Oh, no, I am. I have this thing.
Thank you. Thank you.
So that was the last talk.
Yes, it was. Yeah.
Okay. Sorry for the slow communication.
It's okay. Don't worry about it. What? Yeah, you can come here. Okay. So I just wanted to say some final remarks. Just that we are closing the RQI circuit at Waterloo. I just want to say thank you to our invited speakers, Robert Mann, Eduardo Martín-Martínez, and Achim Kempf for sharing their expertise and insights. Their talks really enrich the conference. I would also like to thank to the people that did the contributed talks. I think that you all did a great job showcasing the RQI research that we do here in Waterloo. I would also like to thank to Hans Dester, Maureen, Eri, and Haley from the Department of Applied Mathematics. They were the people that assisted us for getting the funding for coffee breaks and lunch. We would also like to thank Kimberly from the IQC and Jamie from Central Stores that help us with the logistics of the event. And we would like to wish the best of luck to the Nottingham folks and the other RQI hubs.
Yep. Well, thanks, Maria. Thanks a lot for this. Thanks, everyone, for being here. I think that we all had an amazing experience. I think that this went way better than I was expecting. We had some technical difficulties on one of the cameras, but still, I think the broadcast was followable. I think that everything worked out well. We're going to figure out everything so that the next broadcast will be hopefully even better. The 4 of you, you've done an amazing job. All of this has been organized by them. I have merely been manipulating cameras here and putting together the invited speakers, putting together everyone, collecting the abstracts, getting food and getting everything. Really, congratulations. You did an excellent job. Thank you so much.
And before we get too much I also want to highlight, oh yeah, for the people online, I want to highlight Maria's work. Like it has been a team effort and everybody's been involved, but Maria has pulled way more than her weight, even trying to move some of the tables last night single-handedly. So with that being said, I don't know whether there's any last remarks before. Okay, I'll let you do that.
The very last remark then is if you are still with us online, you're probably going to want to watch the Nottingham one happening next Friday, starting at 1 p.m. if I'm not mistaken, and in the UK in Nottingham. Of course, 1 p.m. GMT, I think after the summertime changes back. So thank you so much for watching, and hopefully the rest of the circuit will run even more smoothly than this one, and it'll be as good as this. So yeah, that's it.
Thank you.
Yes, let me cancel the screen.